morning all. This session will be chaired by Professor Arup Kumar Das from IIT Roorkee.
So should I start?
Yes, sir, we can.
Okay. So good morning to all of you. I'm Dr. Arup Kumar Das. I'm from Department of Mechanical Engineering with IIT Roorkee. You are now here in Hall 4, and this is session 4D. We will be taking 8 papers in multi-phase flow. We'll be starting with paper number 143. The authors are Harsh Kulkarni, Prashant Sharma, Avinash Gaikwar, and L.R. Bishnoi. I think Harsh Kulkarni will be presenting. The title of the talk is Development of Choked Mass Flow Model. So I request organizers to play the video.
Hello everyone, hope you've had an interesting day till now. It is my pleasure to present to you our findings on the choke flow mass rate and its modeling. We'd like to begin this presentation by addressing the simple question, what is choking? Choking can be described as the limiting condition after which downstream conditions to the throat have no effect on the mass flow rate. The fundamental reason that choking occurs is that acoustic signals after the throat can no longer propagate upstream to influence the mass flow rate. This occurs when the fluid velocity equals or exceeds the propagation velocity, which is generally the speed of sound in the medium. A physical description of this as per the Moody slip equilibrium model demonstrates with greater clarity how the pressure gradients at the throat will approach infinity when the choking is encountered, which will damp out any further influence from the downstream of the throat. While choking in a single phase is relatively easy to model and predict, difficulties arise in modeling two-phase choking. These difficulties arise as a result of the fact that the two different phases have two different sound speeds associated with each phase. As a result of this, the pressure gradients as per the slip equilibrium formulation, albeit large, are not as large as in the case of single phase flows. Hence, the damping is not as effective at removing downstream effects. Hence, modeling is more difficult for two-phase flows. The main motivation behind this is the development of the Nuclear Plant Analyzer Code NUPAC, which is AARB's in-house developed nuclear safety code. This model fulfills the requirements of a more accurate non-iterative correlation for the calculation of choking over a large range of pressures for both single as well as two-phase flows. And this model will be used particularly for the prediction of choke flow mass rates in the case of pipe breaks in different components in the nuclear reactors. The Bernal model is a popular and widely used model. It is used in many different choke flow codes as well as older correlations for choke flow. The assumptions of the Bernal model are that the mixture is a non-equilibrium mixture. There is no phase change occurring in the system. The Bernal model is used for prediction of critical mass flow rate for subcooled as well as two-phase flows involving water. An empirical correlation is used for calculating the pressure at the throat, which is then applied in the Bernoulli's theorem between the stagnation point in the throat so as to find the critical mass flow rate between the stagnation point and the throat. It should be noted that this is based on the comparison with experimental data. It was observed that this model would generally underpredict values of critical mass flux, especially for the cases involving low length per diameter ratios for nozzles. The Bernal model is a very old model, but it was recently modified by Kim in his work on finding a correlation for critical flow rate from water. These changes were adapted in the current model that we have developed so as to give a better prediction for the choke mass flow rate. The Moody's pressure pulse model is a well-known non-equilibrium model which attempted to create a physical formulation of the two-phase critical flow based on the transmission of an infinitesimal pressure pulse in the mixture. It was used to calculate the choke mass flow rate in the two-phase region in the model that we developed. The assumptions of this model are the flow is frozen, that is, there is no heat or mass transfer across the phases. The flow is isentropic and there is no heat transfer across the pressure part. Model is roughly divided into three regions. One, the subcool, the second, the transition, and the third, the two-phase region. The subcool region in the code is defined as the region having its own upstream enthalpy less than the saturation enthalpy to the upstream of the flow. The model used in this region is a modified form of the Bernal model. The required coefficients of the Bernal model which are used in this region are simply as per those given by Kim. The equation finally takes the form as given here. The second part of the model is given by a transition region. The transition region ensures a smooth transition between the mass flow rate prediction of a single phase and a two-phase flow regimes. The transition regime is defined by the upstream enthalpy given in the range as specified by this. The critical mass flux is calculated using this relationship, where f of mu is the cubic interpolation polynomial that is used to interpolate between the subcool correlation and the two-phase correlation. The value of the length of the transition region is calculated by assuming certain lengths of transition regions and finding the length which contains the minimum RMS error among all these lengths of transition regions. Here we can see when we take the length of transition region as 50% of this complete latent heat of vaporization, then we get the minimum RMS error. Lastly, for the two-phase region, this region is the region in which the curve fitting using least square regression method was applied to get a more accurate and robust model to predict critical mass fluxes for larger ranges of pressures using a non-iterative scheme. The base model used was the pressure pulse model given by Moody in his paper in 1969. The base equation for the critical mass flow rate is given as per this. The specific volume gradients against pressure for each phase are required to be calculated, and these are calculated using the Noble-Abel-Stiffen gas equation of state. This equation of state is given by the caloric laws as given here. On further manipulation of the equation in the previous page, we have arrived at the formula for critical mass flux, where the constants ZH1 and YH1 are derived using the specific volume gradients calculated using the NASG-EOS formulation. The values of ZH1 and YH1 that come out here are given here. The properties in this formula are all local properties, none of these are upstream properties. Further, we will have to convert these properties into upstream properties because the experimental data which will be used for curve fitting is mainly available only for upstream properties, and very few amounts of data is available at local properties. The final step in this process of deriving the two-phase critical mass flux correlation, we have arrived at a correlation which is valid based on upstream properties of the fluid, of the throat. We can see using curve fitting, we can obtain the values of ZH and YH based on the experimental data G, P, rho, and X. Here, the values of G, P, rho, and X are all experimentally determined values. The matrices that are represented here are the matrices obtained from the least square curve fitting method. to obtain the coefficients ZH and YH. Finally, the values of ZH and YH that were obtained for pressures greater than 5 megapascal are 1.276 and 1.340. Once the model is developed, the next step is verification. The verification of the model was done in two steps. First, the comparison of data with Kim's extended charts in the maximum slip model. Then, the model was compared with another well-known nuclear plant analysis code named RELAP5. On comparison of the prediction of the created model with the data from Kim's extended charts in the maximum slip model, you can see a very good correlation between the three models. Most of the data points lie between the plus minus 10% deviation regions for both the Kim's choke flow map as well as the maximum slip model. The only variation comes in the Kim's choke flow map for a very high experimental choke mass flow rates. The value of the calculated choke mass flow rate seems to find a constant value after which it does not increase. This is because most probably the Bernal model underpredicts, as was discussed earlier, based on the L by D ratio of the nozzle when geometrical characteristics are considered. Finally, based on the comparison of the proposed model with the RELAP5 model, we can see that both the models show very good correlation with each other. The only outlier being the 1 point with quality x equal to 0.2, where the percentage error is 18%. Other points show very good correlation between 10 plus minus 10% deviation. It can be seen that the developed code agrees satisfactorily with the various different choke mass flow rate models developed until now, while having additional robustness in its formulation, as it is based completely on experimental data and can be modified to be very accurate for different values of upstream pressure. I would like to conclude my presentation by bringing forward the future prospects of the work that we have done. These include adding more data for correlations at different pressures. Additionally, more sophisticated machine learning models can also be used to model the choke flow rate more accurately, including phenomena such as heat transfer and mass transfer between the phases.
Okay, thank you. Very nice presentation by Mr. Kulkarni. So is he here around, Mr. Kulkarni, Harsh Kulkarni?
Yes, sir. I'm here.
Okay, fine. So my question is that whenever you are having this subcooled to two-phase region, is there any matching portion? That means how you are transitioning from subcooled to this two-phase portion? You are having separate models. So are those models having some matching?
Yeah, yes, sir. So that is the function of the transition region actually. So basically we use the interpolating polynomial and we interpolate it between the subcooled and the two-phase for a certain fixed amount of part of the two-phase region in the starting line.
Right. So you have not taken any nucleation model into consideration, right, in this?
No. We have just simply used whatever choke mass flow rate equation was given before, and we have modified it, and we have used experimental data, curve fitting, and obtained for different pressures.
Okay. How many experimental data you have used?
I don't remember the exact value, but it was, I think.
Right. Okay, fine, no issue. Any other question from the audience? Anybody having any question in the audience side? Mr. Kulkarni is here, so he can answer. In that case, let me ask you one more. You have mentioned somewhere that 15% criteria is there in the transition. Can you explain it a little bit more?
You mean the length?
Yes.
Yes. So basically, the reason for that is Like we used curve fitting, and basically to obtain like what length was best, like how much of the two-phase region should be taken as a transition. So we just basically compared for different lengths, how much error comes, and least error was what was chosen.
Okay. Thank you, Mr. Kulkarni, for your nice presentation. So we can go now for the next presentation. So that is paper number 112. The title of the paper is Analysis of Multi-Component Gas Phase Diffusion Model in the Context of Droplet Evaporation. The presenter will be Professor Ashok Dey, I think, and the other co-workers are Rajdeep Shardar, Shaunak Majumdar, Arpan Shaw, Sharnendu Sen, and Achinto Mukhopadhyay. Yeah, please play the presentation.
Okay, I will come to this particular presentation, which is on analysis of multi-component gas-phase diffusion model in context of droplet evaporation. This is paper ID 1 and 2, and here is the author list, and myself is the presenting author. So there is a brief outline of the talk. So I will give you brief motivation, which will actually lead to the objective of the present work, and then just some of the key formulations that I will discuss before we go to the result section and finally conclude the talk. Now, one of the motivation behind it is that see, droplet evaporation is very common, fundamental natural phenomena, and it is widely used in various industries. I mean, combustion-related industry, fuel preparation, DNA spotting, nanofabrication, inkjet printing. I mean, all these where the droplet evaporations which are required. Now, of late, there is a use of multi-component droplet has become quite popular because these droplets are made of several chemical compositions. And I mean, sometimes, I mean, especially this industrial application, the liquid fuel which are of use, they have some multiple chemical compounds associated with that. And so they are characterized by different thermal conductivity, diffusivity, volatility, and all these things. So it is quite important for researcher to understand the fundamental principle of this multi-component droplet. In that context, present work deal with this evaporation characteristics of bicomponent ether and water droplet. I mean, so here our primary focus is on the modeling of the gaseous diffusion. So since there are bicomponent, and there are two different approximations for this gas diffusion, which kind of have been implemented and also compared. And the results are compared with for these things and looking at the comparing with the experimental data as well, just to see how these different approximations for gas diffusion actually behave. Now here the other important thing which is that here we are conducting, I mean the whole work is conducted assuming a lump system model. So that means there is no internal temperature gradient exists inside the droplet. So also it is assumed that the quasi-steady evaporation takes place with no internal concentration gradients in the liquid droplet itself, so that each quasi-time step the droplet is assumed to be well mixed. Now, the other thing which is also been considered for the validation cum verification purposes, that the droplets are of the larger size, they are not the smaller. So the since they are of the larger size, the non-equilibrium effect is also kind of eliminated or rather not considered. Now, earlier models they have largely considered evaporation individual species of each other in mass transfer equation. Now we use two models for diffusion velocity in gas combustion study. One is the Hertzfelder's law, which given by these particular equations, and the other where the is the trace component in the diluent could be using the diffusion velocity Vi can be represented. So I mean, in a simplification form, this Hertzfelder's law reduces to this. So the other part which is important is that the enthalpy diffusion. Okay. So enthalpy diffusion, which is not applied in many models, and the typical the heat flux is model using the heat conduction equation. Okay, so now also in heat conduction equation, the D for heat flux is neglected. Now the thing here, using a full model which uses this Hurst-Felder's law and enthalpy diffusion, I mean, are termed as a full model, which is the M2, and the other model where we use is, so this chart clearly shows what diffusion model, which is um, correspond to the previous slide, that which diffusion model that we are using. So one case we are also considering the enthalpy diffusion, and these cases, and the one case we have not considered the enthalpy diffusion, but then we are looking at the different diffusion model, and the detailed derivative of these are the already documented in the paper. Because of the kind of shortage of time, I'm not going through those equations. Now here the two different models which are already implemented, and they are solved. These ODEs are solved, and the droplet temperature is updated, and the second order schemes are used. So then we have, and the other thing is that here is the one of the, based on the assumption that especially the physical properties independent of temperature. That means the temperature dependent properties are not considered here. So there could be some effect on that, and also we have used, I mean, rather adopted an equilibrium model for the initial droplet size is quite large. So to calculate the mass fractions and all this, so these are there. So with that, now let's move to some of the. So first, we look at the surface area evaluation. So here is the time versus D2, and there are two different temperature. One is the 400, 475, and this is for now here one can see the solid line correspond to M2 and the dotted line is the M1. So that uses two different diffusion model, as we have already shown in that. And we can see that, I mean, they quite well predict the experimental data, and but there is some deviation from between M1 and M2, and this is where different line corresponding to different ethanol mass fraction. Zero means it's sort of, it's only pure water. When ethanol is one, that means there is no water at all. So that means the water has been evaporated. So some differences which we have observed here, which could be attributed to the use of calculated thermodynamic property for ethanol, and simplifications like no temperature gradient exists in the droplet, perfect mixings like that. Also, experimental inequities tend to arise with ethanol, since it's hygroscopic in nature, and consequently water vapor tends to interface in the manner. Now with that, now here is also, this is the evaporation at gas temperature 400. This is water evaporation, and this is the ethanol evaporations. So we can see there, like, um, I mean, this curve clearly shows that the evaporation, ethanol evaporation is nearly complete, and there is a significant increase in water evaporation. So consequently, due to some gradual change in overall liquid thermal properties, the average droplet temperature is found to increase from a lower temperature to near standby temperature obtained for pure evaporator. So to see this effect, now this is also evaporation at 475 with the similar behavior which are observed here. And another thing that we have considered here is that we have looked at M2 without the enthalpy diffusion, and you can see some impact is there when you use without enthalpy diffusion. I mean, neglecting enthalpy diffusion, there are some effect is there. For some volatile component like ethanol, the rate of evaporation is almost independent of the model you consider, except some pure case. Now to see these things, now to see this, now, I mean, this is also the temperature evaluations, how it takes place. and this is at the 475. So uh, uh, now, so what we can conclude here is that both the models able to qualitatively predict the overall characteristics, and the evaporation rate for bicomponent droplets decreased significantly with the increase of ambient temperature, but not in accordance with the D2 law, which usually we see in the single component droplet. And so the steady temperature difference is order of 5 Kelvin. Diffusion model tend to affect some evaporation dynamics for the less volatile component like water to a greater extent. For more volatile component, the dynamics largely model independent. The enthalpy diffusion has a percentage of the Fourier conduct is half the magnitude of the Nusselt number corrections, and they tend to increase with the increase in gas temperature. So this is the initial study, and there could be further improvement which could be made with this particular work, like taking the temperature dependent properties, which thermodynamical property, which could be of very useful, and the other things like when you go to smaller size droplet, then the non-equilibrium effects, things like that. So those are something used for future work. So that I would like to thank you.
Thank you, Professor Dev, for this nice presentation. It is having a great deal of application also, I believe. Any question from audience? First, let me take. Anybody from audience? Any query, any doubt? Well, in that case, let me ask that how you feel that this kind of model will be faring in terms of the numerical modeling of this conjugate droplets of ethanol in water. Is there any plan for doing numerical modeling, complete numerical modeling of these small droplets? Am I audible?
Yes, sir, you're audible.
Okay. So, Mr. Day is around. Has he listened to my question? Mr. Day? Well, so let us.
So most probably attending from the.
Okay, fine. So let us keep this question for the future. I think we can ask in some another forum. So we'll be moving on to the next presentation, but we have 2 more minutes to wait because it is supposed to start at 10, right? So let us wait for 2 more minutes. So at 10, we'll be starting our third presentation. Are you taking participants from other forum also? Like not from Teams? Can they attend through some other medium apart from Teams? Organizers?
Sir, we have shared the Teams link, Teams meeting link only.
Okay, fine.
So we can't hear you properly.
Am I not audible? Am I audible?
Yeah, it's audible, sir. Yes,
Okay.
sir.
Yes, you are audible.
Okay.
You are audible, actually.
Thank you. So let us take the third presentation of this session. This is paper number 120. The topic of this presentation is bubble size analysis in a two-phase counter-current flow in the 2D column. Okay, so this work will be presented by Mr. Ritesh Prakash, and this work has been done along with Bongliva T. Sankham, Santosh Dev Verma, and Kali Charan. So I request you to present the work.
Good afternoon to all of you. I am Ritesh Prakash, working in the Applied Multi-Phase Process Research Laboratory under the guidance of Professor Subrata Kumar Majumdar and Professor Anugrah Singh in Department of Chemical Engineering, Indian Institute of Technology, Guwahati. Today, my topic of presentation is bubble size analysis in a two-phase counter-current flow in the 2D bubble column. Okay. Industrial processes based on the interfacial contact between the gas and liquid phase are useful in numerous industrial practices. The two-phase bubble column reactor are useful in the various chemical, biochemical, petrochemical, and wastewater industries. Bubble column reactors are widely used because of ease of operation, simple construction, higher transport processes, etc. The interpretation of the hydrodynamic characteristics in such bubble column reactor is of paramount importance because of its usefulness during the design, operation, control, and scale-up of the system. The hydrodynamic characteristics such as the gas holdup, frictional pressure drop, mixing characteristics, as well as the bubble size and its distribution are important for an in-depth understanding of the behavior of the system for process intensification. Okay. The aim of the present work is to enunciate the influence of dispersed phase and continuous phase velocity on short-turbine bubble diameter, and second aim is to study the effect of axial zones on short-turbine bubble diameter at large variations of gas and liquid flow rate in the counter-current mode dense bubbly flow. Here it is the schematic diagram of the experimental setup. The experimental setup consists of a 2D column, pump, electromagnetic flow meter, gas rotameter, solenoid valve, storage tank, gas asperger, air compressor, flow valves, needle valves, light source, and a digital camera. The range of dispersed phase gas velocity was 0.044 to 0.321 meter per second, and the range of the continuous liquid phase was 0.019 to 0.058 meter per second. Here it is the 3D view of the experimental bubble column here, and the length of the column is around 0.63 meter, width of the column is 0.19 meter, and depth of the column is 0.03 meter. And the physical properties of system is given here. Basically, the surface tension of water is 71 millinewton per meter, and viscosity of water is 0.797 millipascal second, and the viscosity of the air is 0.018 millipascal second. Okay. Typical outline of the photographic technique is shown in here in this figure. A black sheet was kept backside of the column to obtain a good quality of images. When the system reaches to the steady state, generally 3 to 5 images were captured at the moment, and the further enhancement and the measurement was performed using the image analysis software, that is Digimeasure. All the images were captured by the digital camera. Okay. For each experimental condition, approximately 300 to 500 bubbles were marked in each axial zones to find out the short-term bubble diameter. Okay. The whole zone in this 2D column is divided into 3 different zones: zone 1, zone 2, and zone 3. And the distance of the zone 1 was 3 to 18 centimeter, and the distance of the zone 2 was 18 to 33 centimeter, and the distance of the zone 3 was the 33 to 48 centimeter. Okay. Most of the bubbles were ellipsoidal in the shape, as we can see here in this figure. Okay. To determine the equivalent bubble diameter of the ellipsoidal bubble, okay, the major and minor axis of the bubbles were measured, as you can see here in this figure. Okay. And finally, after calculation of the equivalent bubble diameter, the shorter mean bubble diameter was calculated using this formula, where summation I equals to 1 to the power n ni into dvi to the power 3 divided by summation I equals to 1 to n ni into dvi square. Okay. Here, the influence of the axial zones on shorter mean bubble diameter can be studied here in the first figure. Okay. So, as observed, the shorter mean bubble diameter increases as the height of the axial zones increases. The whole flow field in the column was divided into 3 different zones. Okay, and each zone have the same area, which facilitate the fair comparison of the shorter mean bubble diameter axially. Zone 1 and Zone 3 are the bottom and top zones respectively, while the zone 2 is the middle zone. The increase in the bubble size with an increase in the axial height is due to the bubble coalescence and the reduction in the pressure. The generated bubbles through the asperger move upward along the length of the column due to the buoyancy and interact with the other bubbles in the flow field. The interaction of the bubbles causes bubble coalescence. As a result, bubble size increases. Okay. The other reason for the increase in the bubble size is a reduction in the hydrostatic pressure with an increase in the axial height. Here in the second figure we can see the variation in shorter mean bubble diameter as a function of gas and liquid velocity. Okay, as observed, the shorter mean bubble diameter increases substantially with an increase in the dispersed phase velocity, while it decreases with an increase in the continuous phase velocity. The increase in the shorter mean bubble diameter with increasing the superficial gas velocity is attributed to bubble coalescence. The increase in the superficial gas velocity increases the turbulence and scattering of the gas bubbles. As a result, interaction among the bubble enhances. The enhancement in the interaction between the bubbles and the another fluid medium increases the bubble coalescence rate. The reduction in the shorter mean bubble diameter with an increase in the liquid velocity is due to the probable reason. First reason may be the decrease in the rising velocity of the gas bubble. Second is the breakup of the bubbles coalescence. Okay. Now we have also performed the error analysis. Okay, and we have tried to analyze the relative standard deviation during the image analysis technique. Here we can see that in case of the smaller bubble size, the relative standard deviation is high, but when we start to measure the larger bubble size, the relative standard deviation decreases. The maximum relative standard deviation is 10.47% and the minimum relative standard deviation is 2.61%. Okay, we have also attempted to develop an empirical correlation to interpret the shorter mean bubble diameter, and during the experiment we have seen that the shorter mean bubble diameter generally significantly influenced by the superficial gas velocity, superficial liquid velocity, liquid density, gas density, liquid viscosity, gas viscosity, axial height, and the acceleration due to gravity. So finally we can define the shorter mean bubble diameter in this form here. dvs is function of all these variables. Okay, and after that we have applied the Buckingham pi technique, and finally we have shown the equation here. You can see dvs upon z into lambda, the first dimensionless group to the power alpha, second dimensionless group to the power beta, and third dimensionless group to the power gamma. Finally we have done the linear regression analysis, and after applying the multiple linear regression analysis we have find out the value of lambda alpha beta as 1.575 into 10 to the power 5, and alpha value of alpha is minus 1.714, and the value of beta is minus 0.125, and value of gamma is 0.946. Here we can see that here it is the parity of the shorter mean bubble diameter. On the x-axis it is the experimental one, and on the y-axis it is the predicted one. Here we can see that the error range between the experimental and predicted is less than plus minus 20%, and the absolute average relative error between the experimental and predicted shorter mean bubble diameters are around 7.87%. Here it is the ranges of the correlation for the ranges of the correlation, and for the correlation here. Now come to the conclusion here. The experimental results show that the shorter mean bubble diameter is strongly dependent on the axial height and operating variables. The range of shorter mean bubble diameter is noticed to be in the range of 2.65 to 5.84 millimeter, and the shorter mean bubble diameter observed to increase as the axial height and the dispersed phase gas velocity increases, while it decreases with the increase in the continuous phase liquid velocity. And the generalized empirical correlation is also developed for the enunciation of the shorter mean bubble diameter in the terms of the gas Reynolds number, liquid Reynolds number, and the Froude number. And the developed correlation is suitable to interpret the experimental short-term bubble diameter in the range of plus minus 20% and in the absolute average relative error range of 7.87%. And the present research work will be helpful for the intensification of the process involving mass transfer through the bubble flow in a countercurrent mode. And here it is the references. And thank you.
Okay, thank you. Very nice presentation by Mr. Dikesh Prakash. So, is there any question from the audience side?
Yes, I have a question.
Yeah, please.
Actually, you have used a 2D bubble column, but you can see, I mean, in actual practice, there is no such 2D bubble column used in industry. Then what is the reason of using a 2D bubble column for your research, please?
Yeah, Mr. Ritesh. Mr. Ritesh.
Hello, sir. Yes.
Yeah, please.
Yeah. Actually, this was air and water one we have actually performed, and other experiment also we have performed using this surfactants also. But for this current one, this is this is like a new works. We are just trying to find out the path. Like how does it work?
No, my question is, I mean, in actual practice in industry, you will not find any 2D bubble column, but in your research, in terms of research, in laboratory research, we generally use 2D bubble column. Many people have done. It is, I mean, being used since many years. So what is the reason behind it? I mean, what is the advantage of working on a 2D bubble column in laboratory?
Means what do you expect in terms of the physics changing in case of 2D and 3D, and what is the motivation behind working for a 2D bubble column in laboratory scale?
Correct.
That's a question from the audience. I think the major reason is that obviously, the extent of experiment, whatever we are doing, and finding out the bubble sizes, etc., in 3D cluster of bubbles, that will be little difficult. Costly experimentations are required, visualization techniques are required.
Yes, sir. I am aware of those things. Actually, I just wanted to know whether the person, I mean, the author, person who has performed that thing. I mean, I have done rigorously on 2D bubble column, so I just wanted to. He also should know these things. Actually, I have a little one more question. Do you have some time? I mean,
yes, please.
In slide 6, he has shown some one result, one plot D32 versus, I mean, shorter mean diameter versus velocity, where we can see the trend is not that good. Sometimes it is getting down, sometimes it is going up. So can he explain something on that?
Yes, Mr. Ritesh. Can you respond?
Okay, no problem, sir. Maybe some communication.
Yeah.
Okay, thank you.
Anybody else having? Thank you. Anybody else having any query, doubt? Ritesh's presentation. Please.
I have just a question extended to the earlier question. He has done the experimentation in 2D. Is he aware, or is there any planning for him to see what will be the effect when this 2D will turn into 3D, so that it can be more practically used in industrial fields?
Is Ritesh available here in this forum to take these questions? Okay. So far, I know Professor Subrata Kumar's research lab. I think they are having some effort going on in that direction to develop a 3D column and then take experimental data. So maybe you can browse his webpage and find out at IIT Roorkee that what are the situations. You can directly write to him also and get the information. I believe the student is not getting connected due to some technical difficulty, so he is unable to take our questions. Right? But let the interaction carry on. So we'll be having some more presentations also scheduled in this session. Okay, thank you.
Thank you very much.
Okay, so let us move on to the next presentation. So next presentation is paper number 150. So this is about free surface vortex and associated air entrainment at the intake of a centrifugal pump. Okay, so this work will be presented by Rahul Kumar Mandal, and he has done this work along with Sharedeep Guledia and Dr. Pramod Kumar. So let us play the video.
Hello everyone, my name is Rahul Kumar Mandal. I am a PhD student. I am doing my research work under the guidance of Dr. Pramod Kumar. My presentation topic is free surface vortex and associated air entrainment at the intake of a centrifugal pump. Outline of the presentation is introduction, literature survey, experimental setup, air separator system, results and discussion, conclusions, and final acknowledgement. Now come into the introduction. Entrainment is a phenomena in which one fluid completely enters into another fluid. There are some examples in our daily life where entrainment phenomena occurs. During mixing of tea, air bubbles appear at the surface of tea. When we pour water into an empty glass, some bubbles are observed. Water comes as a droplet from into atmospheric air. Entrainment phenomena are also occur due to vortex generation such as plug hole vortex, tornado vortex. Now come into the definition and types of vortex. Vortex is a region in fluid where the flow is spin around an axis. In vortex, only tensor velocity exists and there is no radial velocity. If you apply the velocity condition in two-dimensional incompressible continuity equation, after solving it, it is found that the tensor velocity function of only radial location. There are mainly two kinds of vortex: free vortex and forced vortex. A free vortex are the vortex in which the total mechanical energy is constant throughout the fluid field. Tensor velocity of the free vortex is inversely proportional to the radial location. Pressure distribution equation is similar as a Bernoulli equation in the free vortex. A forced vortex is a rotational vortex where the total magnetic energy is constant at a particular radial location, not the entire flow field. Tensor velocity of forced vortex is directly proportional to the radial location. Pressure distribution equation of the forced vortex is found from the ideal equation of motion. Rankine vortex is another kind of vortex that is a combination of free and forced vortex. Hurricane and tornado are the example of the Rankine vortex. Now coming to the literature survey. Ahmed and Leaf have done the study of air core vortical induced by a plug hole vortex. The experiment has done in a rectangular tank in which a hole has created at the bottom center of a tank for accommodating the transparent pipe. A high-speed camera is used for capture the phenomena of plug hole vortex and its consequences into drain pipe. Before reaching the critical height, the free surface of the water behave like a flat, and after reaching the critical height, the free surface behave like a dent on the center. Finally, free surface take a shape of pendant shape. When the surface dip enter into the outlet pipe, it takes the shape of an inverted cylindrical column with the cone-shaped free surface, and droplet-shaped bubble are pinched up from the cone-shaped free surface. Droplet-shaped bubble is converted into donut-shaped bubble ring due to different velocity distribution in the cross-section of outlet pipe. Donut-shaped bubble ring is converted into bubbly flow. Further, bubbly flow is converted into slush flow, and slush flow is merged with other ring. It is converted into annular flow. Cristofano et al. Have done an experimental study of unstable free surface vortices and gas entrainment onset condition. During experiment, different stage of vortex is found. In first two stages, there is no air entrainment, and last two stages are air entrainment, while the third stage is unstable state, and fourth stage is continuous air entrainment. From the past literature, it can be found that these studies were limited to observe the different stage of free surface vortex in the water pool above the tank base. Our present study is focused on the development of the air entrainment phenomena inside the flush-mounted outlet pipe at the base of a tank, and the effect of excess air entrainment on pump discharge characteristics result are quantified in this present presentation, which is not explored as quantified wise in the past literature. This makes our study unique as compared to previous literature mentioned. The generation of free surface vortex is known to cause lots of problems for hydraulic machines. They are such as decay in the performance of hydraulic devices, fluctuation in the flow rate, erosion and cavitation in the turbine and pump blade, local temperature increase in the noise level, reduction in the safety system performance. Now come into the experimental setup. The skating diagram of the experimental setup is shown in this slide. A transparent rectangular tank is kept at 5 feet above from the ground on a rigid structure. At the bottom center of the tank, a hole has created for accommodating the acrylic pipe whose inner and outer diameter is 25 and 32 mm. Another end of pipe has been connected with air separator. A view box is attached to the acrylic pipe which is just below the tank. The outlet of air separator is connected with centrifugal pump. Entrapped air from the air separator is removed with the help of super vent and vacuum pump. Outlet of pump is connecting to tank by passing through turbine flow meter and rotameter. A high-speed camera is kept in front of experimental setup, and DC light source is kept just behind the tank and view box. To minimize the effect of excess air entrainment on the pump discharge characteristic, an air separator system has designed. At low entrainment, entrapped air is removed from the super vent. At high entrainment, entrapped air is removed from the vacuum pump. Using Arduino 712 volt and non-contact liquid release sensor, vacuum pump is automatically remove air from air separator at high entrainment. Now come into the experimental results. During the experiment of free surface vortex, 4 different vortex profile identified. No vortex stage is obtained generally at low flow rate and high submergence of water in tank. Vortex stage 1 is obtained on further increasing the flow rate. Depending upon the H value, a small dimple of 1 size appear with fast circulating motion around the dimple on the water pool. Air entrainment does not occur at this stage. On further increasing the flow rate, a well-developed vortex start to appear in the axial direction. Air core is also present within the vortex. The shape of vortex in this condition look an inverted cone, positively very sharp like needle. The depth of vortex at this stage is approximately greater than 2 mm. Surface tension is also important in this stage for gaining a definite shape of the vortex. The stage of 3 vortex is extended version of stage 2, in which some bubble are pinched from the tip of the vortex and pulled in the outlet acrylic pipe. This stage is unstable vortex stage because after sufficient bubble detached from the tip of the vortex, it goes back to stage 2, which is stable. The vortex tip at this stage remains above the outlet of pipe. Sometimes this stage further develop into the stage 4 if the flow rate is slightly increased. This stage appears at a greater flow rate compared to observed stage 2. Stage 4 is almost fully developed stage 4 stage when the tip of the vortex is reached within the outlet of pipe, and sometimes the transition from the occasional air entrainment to continuous air entrainment occur at this stage. In this case, excess air entrainment in the outlet pipe is going, so the efficiency of the pump decreases and the flow rate goes down. This further leads to a decrease in flow velocity. Vortex tend to stage 2 by passing unstable stage 3. During no air entrainment occurred in stage 2, the pump once again reach high efficiency and the cycle has repeated. Based on the earlier studies, the dimensionless parameter like Wavir number, Reynolds number, and dimensional critical height is developed. A regime map is developed between different vortex stages. The plot between the dimensional critical height and Reynolds number and the dimensional critical height and Wavir number is plotted. It can be noted that the lower critical height are dominant by stage 4 and other stages are not visible. Other stages are come into picture with increasing the dimensional critical height. It is also observed that the present work is well matched with Christopher et al. Results. Air entrainment phenomena are not happened from no vortex to stage 2. That is the reason no bubbles are seen in the outlet pipe. In stage 3, bubbles are pinched from the tip of the vortex intake, which is seen into the outlet pipe. Bubbles are marked by the red arrow. The tip of vortex stage 4 touched the inlet of outlet pipe. At initial condition, continuous bubbles are pinched into the outlet pipe, which is seen in the pipe. After increasing the slight flow rate, the relative instability are seen on the vortex thread. Further increase in the flow rate lead to expand vortex thread from relative instability in the rest of the outlet pipe. The vortex almost expand to the diameter of the pipe with wave that appears similar to relative instability on its periphery along the vortex length. The expand air entrainment region collapse after a certain distance to form a bubble cloud. The last substage of stage 4 is marked by complete air entrainment in the pipe. This case leads to change in the efficiency of the hydraulic pump and a decrease in the flow velocity at the pipe outlet. The obtained vortex profile at low submergence is thicker as well as wider compared with high submergence. Well-developed vortex profile is generated at low flow rate at low submergence. The bigger size of bubble are pinched from the tip of the vortex at low submergence. Two different experiments have done in stage 4 vortex at higher entrainment. One has done in the presence of air separator system, another has done in absence of air separator system. After completing the experiment, it is found that the pump discharge flow rate is less fluctuate in the presence of air separator system, while the pump discharge flow rate is more fluctuate in the absence of air separator system. Now coming to the conclusions. Concluding, my experimental study of free surface vortex and air entrainment has been performed with different water height, flow rates, and a single diameter of outlet pipe. 4 stages of free surface vortex are identified within the tank. The free surface vortex is observed to be showing for additional stage of stage 4 on having oscillation through a flush mounted transparent acrylic pipe. The presence of relay plateau instability seems to play a transiting role from less entrainment to a bulk entrainment. Transformation of bubble shape to annular liquid film has also seen within the outlet pipe. The pump discharge flow rate less fluctuate with excess air entrainment in the presence of an air separator system. A regime map is presented between the dimensionless critical height and Reynolds number and dimensionless critical height and Weber number. Thank you for your attention.
Well, thank you, Mr. Rahul Kumar Mandal, for this nice presentation. First, I'd like to take some questions from audience, if they are having any. From audience, anybody?
Yeah, I have some
please.
feedback, suggestions, and one question. First, I'll ask the question. Mr. Rahul, you have mentioned about the free surface flow. So it is the gravitational force which comes into picture, and in fact it is predominant. But you have not mentioned a Froude number in your study. What could be the reason?
Yes, Mr. Rahul.
Yes, sir. Hello. Am I audible?
Yeah, you are audible. Have you listened the question?
Hello?
Have you listened the question? You are audible, Mr. Rahul. Have you listened the question? Rahul, you are audible.
Yes, sir.
Have you listened the question?
Hello. So
can I repeat it?
Rahul, can you listen us?
Yes, sir.
Rahul, can you listen us?
Sir, can you ask one more time question, please?
Yeah, please.
Yes.
In your dimensionless numbers, you mentioned about the Reynolds number and Weber numbers. A free surface flow is predominantly gravitational flow.
Yes, sir.
So Froude number comes into picture. Actually, Froude number predominates this fluid flow phenomenon. So what could be the reason you have not mentioned or considered Froude dimensionless number?
Sir, because sir, in experimental we have not currently a major instrument which measure the free surface velocity with respect to height. So we not measure here, sir. In computational we try to make same explore in a computational, then we calculate the free surface velocity with respect time, then we calculate and export, sir.
This last slide was mentioning about the height of water column. It means it is the Froude number criteria, which is to be there.
Okay, so to add on this, probably what you are doing, Mr. Rahul, I think though it is free surface flow, but it is predominantly driven by the that pump intake, I believe, right? So it is actually the inertia which is actually driving the mechanism. Though Froude number will be definitely important for gravitational stratification. What do you think, Mr. Rahul?
Inside, we try to measure the free surface velocity with respect to time in computational work, sir. Because in experimental, currently no any instrument available to measure the free surface velocity with respect to time and decreasing height. So, sir, we not exactly mention here.
With relate to this, I have one feedback. Please go through some more literature. You will find very good papers, and they will guide about the Froude ratio, because in any experimental studies of my 30 years of experience in kilosquare others, we always follow Froude criteria, and we keep Reynolds number and Weber numbers in control so that we can have a better model analysis. Thank you.
Thank you. Yes, so any other question from audience? Any other question from audience? If not, then let us thank Mr. Rahul Kumar Mandal for this nice presentation. We will be moving to the next presentation now. So that is paper number 151. The paper is talking about investigation of flow pattern of spray from solid cone nozzle. And the presenter is Rajshekhar K. And he has done this work with B. Raja. So I would like to ask the organizer to start the presentation.
My best wishes to all. I am Rajshekhar, research scholar from IIITDM Kanjipuram, Chennai. My today's presentation is all about an investigation of spray pattern of solid cone pressure nozzles. My purpose in doing this work is to analyze the effect of spray inclination of nozzle on the spreading behavior if it is used as an atomizer for spray drying applications. So before discussing the objective, it is useful to get to know about its application. The automation mainly used in the spray drying process and the necessity of automation and sprays are discussed here. The spray drying is a method of particle production which comprises the transformation of a fluid material into dried particles. The process happens in a gaseous hot drying medium. The hot gas may be co-current, counter-current, depends upon the need of the application. It is initiated with the feed solution atomization in small droplets due to a decrease of surface tension when it is flowing through the atomizer. Breaking up the initial solution into many droplets increases their surface area, optimizing therefore the heat and mass transfer between the heated drying gas and the liquid particles. The motivation for the present work is observed from the literature survey on spray drying reveals that the cone area of spray spread caused by the atomized spray plays a vital role in the productivity, particle size and spray dryer design. And there is a scope to study the flow dynamics of the atomized spray with the different spray inclinations, including normal to the target surface, to study the spray inclination effect on the spray cone dimensions. The spray inclination increases spray length at one half of the cone at downstream, allows the droplets to split up further beyond critical Weber number. The critical Weber number is the number beyond which further split up of droplet will occur, thus produces fine droplets. It also provides the higher wetting area with increasing inclination up to a certain extent. Thus, the effect of spray inclination on spray dynamics and the subsequent parameters is experimentally validated with previously established analytical relationships to improve the process performance. The main objective of my study on an investigation on spray pattern of solid cone pressure nozzle is to understand the behavior of spray produced by the solid cone nozzle, to study the effect of inclination on the droplet spreading inside the spray chamber, influence of spray inclination on the droplet size, influence of inclination on the spray impact pattern, to decide the chamber diameter for the desired operating conditions and a nozzle when it is used in the spray drying applications. This is the experimental setup constructed to study and validate the spray inclination effect on the spray pattern. A low flow rate Coriolis flow meter, which has plus or minus 0.1% accuracy, is used to measure the flow rate. A 24-volt DC magnetic gear sealless motor is used to propel the liquid through the circuit. The flow rate of the water is maintained between 0.5 to 1 liters per minute. The pressure of the fluid regulated by adjusting the voltage and the current to the motor. A pressure sensor is mounted before the nozzle inlet to measure the inlet pressure. The liquid bath and spray space temperature measured with the two T-type thermocouples T1 and T2. A graph table was used as the target surface to capture the spray impact pattern. Two full cone nozzles used are with the orifice diameters of 0.75 and 1.25 mm with spray angles of 60 degree at 40 psi operating pressure. The strainers are placed before the nozzles to filter any contaminations present in the liquid. The target surface is made up of a glass and a transparent graph sheet was pasted at the bottom of the target surface, and it will be used as a known dimension when we are measuring the size of the impact shape. a 60 fps camera was fixed below the target surface to record the nozzle's spray pattern at various spray axis inclination. A computer is used to record the output of the digital camera to process it further. This is the custom-made mechanism to facilitate the spray inclination in order to study its effect on the spray pattern, where a protractor is fixed on the head and a swivel base, which consists of the telescopic tube, is made to rotate on the fixed protractor as shown in the figure. The nozzle is mounted on a telescopic tube to facilitate the nozzle to surface distance, which is also called as a spray penetration length adjustment. The travel distance of the tube is 55 mm and it is operated by means of a worm and worm wheel arrangement inside the telescopic cylinder. This arrangement provides a spray inclination of nozzle for all 360 degree. The operating parameters and the nozzles I have used during my study is shown here. The N1 and the N2 are the nozzles I have used in my experimental studies. The nozzle diameters of N1 and N2 is 0.75 and 1.25 mm. The nozzle spray angle for nozzles N1 and N2 is 60 degree at 40 psi operating pressure. The spray penetration length I kept in my study is 5 and 10 mm. The test fluid is deionized water and the test fluid temperature is 30 degrees Celsius. The flow rate of nozzle N1 and N2 is set as 0.46 and 0.68 grams per second. The operating pressure is 4.2 bar. The impact pattern of spray on a target surface depends on the spray inclination and spray angle. The spray impact shape become circle, elliptic, parabolic and hyperbolic if they falls into the following categories, which is defined by Peng Zhang. The geometric parameters for a spray is elaborated here, where alpha is spray inclination in degrees, theta is spray angle in degrees, h is spray penetration length in mm, 2a is major diameter of the shape produced by the impact of the spray on the target surface, which is in mm, 2b is the minor diameter of the impact shape produced by the nozzle spray in mm, and to get a circular impact pattern, the spray should be normal to the target surface, that is spray inclination should be 0. The deionized water, which is flowing from the container, passes through the mass flow meter and reaches the spray nozzle. The pressure at the entry of the spray nozzle is measured. A strainer is used to filter the contaminations present in the fluid. Before starting the experiment, the pump input voltage and the current were set at a value to provide a specified flow rate and a pressure using the DC power supply unit. The operating procedure is same for both the nozzles. Initially, the nozzle is set at 0 degree, that is normal to the target surface. When the spray hits the target surface, it makes its impact area distinctly and the camera captured the wetted region produced by the spray. Image software is used to analyze and measure the shape and the dimension of the various spray patterns. Subsequently, the spray axis inclination angle with the normal to the target surface is varied, and the same procedure followed for other inclination angles and different nozzles. The image of the spray impact area is captured and further processed with the image to measure its parameters. The graphical representations shows the effect of spray inclination on the spray area, major and minor diameters of the spray impact area. It is observed that at higher angles of inclination, the spray produces a higher wetting area and changes the impact shape from a circle to parabolic to hyperbolic. Most of the spray droplets do not spread in the flow direction and the same moves in the lateral direction, causing the droplets to adhere to the wall. Thus, the effect of spray inclination for parabolic and hyperbolic shapes will result in the producing scattering pattern during the spray drying process. In parabola and hyperbola, part of the spray is not hitting the surface during the process Hence, its ability to spread through a cylindrical chamber is uncertain. So the experimental pattern study for the parabolic and hyperbolic shapes omitted from the present study. Figure 6 and 7 shows the effect of spray inclination on the impact area. The spray area is seen to gradually increase for smaller increments in inclination angle up to 30 degree. Beyond that, the spray area is observed to increase drastically. Even a small increment in the spray inclination causes a larger spray impact area until it reaches the condition for parabolic curves. The tests are conducted by changing the nozzle's spray inclination while keeping the penetration depth as constant by 5 mm and 10 mm. Theoretically, when penetration depth increases, the cone angle must remain constant. However, in experiments, it is observed that as penetration length is increased, there is a reduction in angle along the spray direction due to air entrainment into the spray. Also, the experimental spray impact area is compared with the analytical relations. Figures 8 to 11 show the analytical and measured values of major diameter, minor diameter for circle and ellipse. Increasing spray inclination translates the circular impact area into elliptical to parabolic to hyperbolic. During this transition, the major diameter along the direction of spray increases drastically, whereas the minor diameter is gradually increasing as shown in the figure. Such an increase may cause the particle to move towards the wall of the chamber. Further, there is a reduction in the impact area on one side of the spray. Such an event is implemented in a spray dryer design will cause uneven utilization of energy from carrier gas flow, leads to the increased energy consumption. Figure 12 shows the deviation analysis between the analytical and experimental values, and the deviation found to be plus or minus 5%. These are the conclusions I have made from my experimental study. In spray pattern studies, the spray inclination plays a predominant role in producing the impact pattern. Increased spray area is observed during increased spray length up to a certain extent. Change in the impact pattern observed with increase in spray inclination. Influence of nozzle diameter on the impact pattern is minimal. Favorable conditions of spray inclination is observed for spray drying process.
Okay, thank you for this nice presentation, Mr. Rajshekhar. So, any question from audience? First, let us take. Any question from audience? Are we monitoring the YouTube channels also, where somebody may have some question also? Am I audible?
Yes, sir.
Okay, okay. So, any question from anybody? Okay, so in that case, let me ask few. This work, whenever you have done, have you seen flying of droplets? Whenever the spray is there, the droplets are flying away from the, that elliptic zone, impact zone, whatever you have showed. Apart
Yes.
from that, have you seen flying of droplets? Yes, please.
Yes, sir.
Okay, so what is the extent of flying? Is that dependent on the, that inertia of the jet or the nozzle diameter? Can you comment on that?
From few literatures, I have seen based on the Weber number, it is bouncing back or it is sticking on the surface.
Well, so after releasing from the nozzle, it is directly hitting the surface. Then
Yes.
it is bouncing back. Is it right?
No, sir. At the surface of the cone, it is producing the nozzle producing the cone.
Okay.
And the surface of the cone, few of the droplets are flying away.
Okay.
And at the starting stage of hitting the surface, few particles are flying away. And when it is continued, the particles are sticking with the liquid because liquid is deposited on the surface. And so due to surface tension forces, it is not flying continuously. Initially, it was flying.
Okay. And you have done experiment with the water, right?
Yes, sir.
Okay. So is there any plan to extend it for some other fluids like, diesel or, some other fluids which are actually being used?
Yes, sir. Actually, my plan is to spray dry the electrode materials, lithium iron phosphate and on another electrode material. I am doing the process now in my laboratory, sir.
What do you expect in those situations? This spray region will be increasing with volatility and viscosity of the material?
When viscosity increases, as we know that the spreading will be reduced. If viscosity is less, the breakup of liquid will be more, and also volatility of the precursor also will play a major role, because the inclusion of non-volatile material into the precursor will change the viscosity of material. Further, that it will change the spreading area of the cone.
Thank you once again. I think there is no question further. So let us thank Mr. Rajshekhar K for this nice presentation. Thank you. So we'll be now moving for the next one, which is paper number 155. So this is about revealing the anomalies associated with droplet spreading dynamics. This will be presented by Deboshi Devnath, and he has done this work with Dr. Pramod Kumar. Let's play the video, please.
Hello everyone, my name is Deboshi Devnath, and today I'm going to discuss about the topic revealing the anomalies associated with droplet spreading dynamics, and I have performed this study under the supervision of Dr. Pramod Kumar of School of Engineering, IIT Mandi. I'm going to discuss briefly first the introduction, then the existing literature review, then the methodologies that I have used for my numerical simulations, boundary conditions. Then I'm going to discuss the results and discussions on which I'll discuss the contact radius evolution, drop shape evolution in the spreading dynamics, and I'll draw some conclusions. Drop spreading on solid substrate is very common phenomenon in day-to-day life, such as raindrops falling on different surfaces, falling on leaves, then hydrophobic feet of insects, coffee stains on different surfaces, etc. And drop spreading is a basic mechanism of many technological and industrial processes such as spray painting, coating, inkjet printing, etc. Drop spreading has been studied for a long time. It is very complex and rapid in nature. Due to this reason, the drop spreading dynamics is not yet fully understood. Tanner first proposed a power law evaluation of drop spreading dynamics, which is also known as Tanner's law, which states that contact radius of the drop R will be scale as t to the power 1 by 10, where t is the time scale. And this power law behavior is only valid at the later stage or the near to equilibrium stage, because the assumed geometry of the shape in this study is taken as a spherical cap. But at the initial stages, the shape of the drop is not a spherical cap, it is quite different. As we can see, the initial stages of the drop shape of the drop is quite different. Now Bians found that spreading at early times is inertia dominated, and it agrees with the scaling of drop coalescence. As we can see, contact radius is scales as t to the power half. So here the exponent value, power law exponent value is half, and at the later stages the power law exponent value we have already seen as 1 by 10. So we can say that contact radius overall follows a power law scaling, and the value of power law exponent changes from inertial to Tanner's regime. Yeah. Results of bird. These are the results of experimental observation of bird. As you can see, the initial shapes of the drop for different substrates. Their experimental observation also agrees with the inertial scaling that has been observed by Bians, where value of the power law exponent is half. And also, they also found that inertial scaling of contact radius of drop depends on the equilibrium contact angle of the surface. So apart from this, studies where the inertial regime is mentioned to be the initial or early regimes, and later it goes into the Tanner's regime with an exponent value of 1 by 10. But some recent study done by Mitra et al. Has found that there is a separate regime with a higher exponent value of 0.85 before the inertial regime. And that is mainly for low to medium viscosity liquids. Now, the computational methodology that has been used for the numerical simulations is called volume of fluid method, which is very suitable for interface tracking in any multiphase flow problem, which involves flow between two immiscible fluids. And the equations that are solved in this solver is that the continuity equation, then momentum equation, then advection of the term alpha. Alpha is known as volume fraction. The volume fraction is the fraction of volume occupied by a particular fluid in a discretized cell. And this advection equation is modified by adding a compression term to make the interface sharper. The surface tension force at the interface is calculated by continuum surface force model, and the fluid properties are updated by inclusion of the term alpha or volume fraction. And interface, the solver that is used in this numerical simulation is Interform in OpenFOAM package, and the interface reconstruction technique that is used is PLIC method. Now, instead of equilibrium static contact angle, the dynamic contact angle model is used. There are several dynamic contact angle models available, and we have used the Kistler dynamic contact angle. This the contact angle correlations are given where theta d is the dynamic contact angle, fh is the Hoffman function, and all other values of the correlation and expressions are taken from standard literature. And the values, input values of advancing and receding contact angle theta a and theta r is also taken from standard literature. This is the simulation domain. An initial condition of the drop where y is the axis of symmetry, and on x-axis the drop is spreading. The simulation domain is taken in such a way that the drop doesn't get exceeded from the domain. These are the different fluids used and their physical properties. So as we can see from the recent study of Mitra et al., they have introduced or predicted that there will be a viscous regime with a higher exponent value before the well-known inertial regime with exponent value of 0.5. In our numerical simulation also, we have found that at very early stages for a 1 mm drop up to nearly 0.4 millisecond, the value of exponent comes to be 0.85, and then it crosses over to an inertial regime which has an exponent value of 0.5. And this present simulation is in good accordance with the experiments of Mitra et al. This is the comparison of present simulation result with another result of Winkels et al., where Winkels in their experiments found that throughout the initial stage the exponent value is 0.5, but in our present simulation we have found for very initial stages the exponent value is much higher than 0.5, and later it converges with the results of Winkels, where the value of exponent is 0.5 and which is an inertia dominated regime. So in this case also we can see that at the very initial stages there is a viscous regime which is a very high exponent value. This comparison is done for DBP oil drops, where also we can see the initial best fitted lines for initial phase is giving a very high exponent value of 0.95, and then later it crosses over to the inertial regime where the exponent value is 0.58. So for a little bit higher viscosity fluid than water, also this initial viscous regime is being observed. These are the drop shape evaluations and velocity profiles near the interface and inside the drop. As we can see, these are the very first row is the very early stages of drop spreading. We can see the capillary wave generation and the propagation of the capillary wave, and also the velocity profiles and recirculation of the fluid near the interface. And one interesting thing also, we found that due to the propagation of the capillary wave, the necking phenomena is happening, and one satellite drop is being separated from actual drop, and then it coalesces with the main drop after some time. The pinch of time for 0.5 mm water drop is found to be 3.51 millisecond, and these simulations are done for the advancing contact angle of 22 degree. Now, as we change the value of the advancing and receding contact angle at the solid substrate, the dynamics of capillary wave propagation and the satellite drop pinch off is being changed. As we can see in the first case, for advancing contact angle of 52 degree at 9.7 millisecond, we are getting one pinch off, then it coalesces, and then at 14.9 millisecond, we are getting another pinch off, and afterwards it's coming to equilibrium. But for the advancing contact angle of 42 degree, we're getting the first pinch off of satellite drop at 9.97 millisecond, but afterwards it coalesces with the main drop and comes to equilibrium at around 15 millisecond. In this case, the second pinch off is not observed. Now this is the evaluation of contact angle values with time. As we can see, for different advancing contact angles, simulations are performed, and these are the change of contact or variation of contact angle values with time. These perturbations in the contact angle values are present due to the propagation of capillary wave across the interface. Now, from the above study, we can draw this conclusive remarks as our numerical simulation indicate towards an initial viscous regime, and then it crosses over to the well-known inertial regime, and then to Tanner's regime to equilibrium. And during the inertial regime, where the inertia is the main acting force of drop spreading, a satellite drop is generated, and this generation of satellite drop is changing with the change of dynamic contact angle values. And certain fluctuations are observed for contact angle variation in time for dynamic contact angle simulations. This is due to the propagation of capillary wave across the interface. These are the references. Thank you.
Okay, thank you. This was a nice presentation by Mr. Devarshi Devnath. So now we are open for questions from audience. Anybody having any question, please you can ask Mr. Devnath. Well, if you are not having anything, then let me ask that how you have implemented this advancing and receding contact angle in volume of fluid framework, Mr. Devnath. Is he available around to take the questions?
He is in mute condition, it looks like. He has to unmute it.
Mr. Devnath, please unmute yourself.
Yes, sorry, my speaker was muted.
Fine. So, question from my side is that how you have implemented the advancing and receding contact angle in your volume of fluid framework?
So in the volume of fluid framework, the Kistler contact angle is implemented by taking some defined libraries for the interform solver.
So means you are whenever the drop is actually spreading down, so at that time you have given the advancing contact angle criteria.
Yes, sir, exactly.
It is receding back, you have given the.
Yes.
But how you are predicting this when it is advancing, when it is reduced, receding, depending on the velocity of the front?
Yes, sir.
So are you tracking that one dynamically?
The velocity of the interface.
Velocity of the front, which is actually advancing or receding.
Yes, that has been tracked in the Kistler model itself.
Okay, fine. Any other question from audience? Well, if there is no other questions, let's thank Mr. Devoshi Devnath for this nice presentation. Thank you.
Thank you, sir. Thank you.
We'll be moving to the next one. So next paper is paper number 156. That work is on numerical analysis of aeration mechanism in plunging liquid jet. And the presenter is Nirav Chaudhary. He has done this work with Rahul Jha and Dr. Jyotirmoy Banerjee. So I request organizers to play the video, please.
Hello everyone, I am Nirav Chaudhary, and in this presentation I will explain our work on numerical analysis of aeration mechanism in plunging liquid jet. Including myself, other authors for this paper are Mr. Rahul Jha and Dr. Jyotirmoy Banerjee. We are from Mechanical Engineering Department from SVNIT, Surat. Aeration is defined as the process in which the gases are mixed and dissolved in a liquid by introducing small bubbles of air, which are either introduced naturally or with the help of agitation or aerator devices. Here are some examples of aeration phenomena occurring in our day-to-day life, like pouring water into the glass, aerator devices in the fish tanks. Aeration can be found desirable in most of the natural processes, but in the field of turbomachine, aeration is found to have adverse effect on the hydraulic system in the form of cavitation. Aeration can be found in some natural processes like breaking of sea waves, transfer of oxygen in water bodies through surface, plus some daily life experiences like pouring coffee from height to add flavor, giving texture to the milkshake, releasing flavor of wine while pouring it. It also can be found in industrial applications like filling bottle of shampoo, dishwash, antacids, etc. They have to avoid underfilling or overflow due to foam formation. It is also found in wastewater treatment plants to supply more oxygen. Cavitation in turbomachine are caused by aeration only. Air bubbles trapped inside water causes cavitation on surface of plates. Out of all the available devices, plunging liquid jet is considered in the current study to simulate aeration phenomena due to simple design. To study aeration through plunging liquid jet, these are some challenges that we have to overcome. Complex interaction between two fluids leads to a large-scale deformation of the interface, which has a broad range of length and time scale. It is a two-phase phenomena where the surface tension is dominant, which requires us to develop a methodology to track the evaluation of interface with time. The experimental investigation of aeration through plunging liquid jet requires highly sophisticated equipment to produce and investigate the jet due to uncertainties in the dynamics of flow. Also, in the experiment, it is difficult to analyze how the variation of a particular property affects the phenomena, as changing the test liquid will change the value of almost all the properties simultaneously. Through the commercial softwares, numerical investigation is generalized, but they are not flexible enough for the implementation of latest techniques introduced in the field. The present research aims towards development of an accurate numerical strategy to specifically capture the physics of aeration. Some important experimental work in this field are as follows. In 1966, T.J. Lin used high-speed photography to capture entrainment, and he showed mechanism for entrainment for laminar and turbulent jet. In 1976, Weber formula was used to measure breakup length at low velocity, and a relationship of breakup length with jet diameter and velocity was shown. In 2000, the mechanism of air entrainment was explained, and it was stressed that surface roughness is mandatory for air entrainment in plunging liquid jet. In 2016, Sanjay explained bubble kinematics inside the liquid pool with the help of high-speed camera, and it was found that variation of entrainment depth with time is proportional to jet strength. In 2018, turbulent shear layer was found to enhance air-water mixing. Now for the numerical work, it starts with Q. He did work with image processing and level Z method and got a result on how high flow rate leads to more surface instability and more entrainment, but smaller depth of penetration. In 2015, using multi-phase Euler foam solver from open foam, maximum droplet size was determined by critical Weber number. Pedro in 2016 did work on 3D jet and used explicit term to find bubble generation and entrapment. He also found that free surface amplitude was based on turbulent length scale radius. In 2018, effect of variation of jet length on velocity field was studied with the help of VUF and K epsilon model, along with high-speed photography and digital imaging. Objective of the present study is to develop and validate a numerical algorithm such that it can capture the aeration phenomena in plunging liquid jet. After successfully capturing aeration, next is to analyze various stages of entrainment by understanding the dynamics of the interface and bubble motion. Next is to quantify the phenomena of aeration using penetration depth as a parameter, and to study the effect of various parameters on the penetration depth of plunging liquid jet, which strongly influences the aeration phenomena. Equation to be solved to get appropriate results for this problem is shown here. This is velocity transport equation in integral form. All the terms shown in this equation are self-explanatory. Only the last term is new. It is surface tension force, which is essentially line force, but it is converted into volume force here. This integral equation is later on converted into discretized form to solve it numerically. Discretization is done on collocated grid with finite volume method, and equation is solved using semi-implicit pressure-linked equation, also known as simple algorithm. Complete flow of entire solver is shown in this diagram. First, the solver is created to solve single-phase Navier-Stokes equation. This flow solver uses simple algorithm as mentioned in previous slide and weighted essential non-oscillating scheme, also known as VANO, as an advection scheme. Then, geometric Blick VUF algorithm is implemented to solve problem associated with two-phase, and later on, both models were coupled to make the two-phase flow solver. The surface tension module was added to make complete flow solver. Appropriate surface tension force treatment were also applied. In this work, we used height function method to calculate curvature of interface. All of those modules were tested and validated with multiple available standard cases separately and after coupling also. Plunging jet is defined as a moving column of liquid that passes through a gaseous space before striking on the free liquid surface. Here, rectangular liquid tank of appropriate dimension is shown in this figure. Here are some fluid properties at initial condition: density and viscosity of two fluids, which are water and air, with water being primary fluid, surface tension between air and water at 26 degrees Celsius, initial jet velocities of 1.5 meter per second in negative y direction. Domain is discretized in grid size of 300 cross 520, which gives Tx and dy equals to 10 to the power minus 3. Total runtime is of 0.62 seconds with a time step of 10 to the power minus 6 seconds. To evaluate currently developed model to capture aeration phenomena, it is tested qualitatively and quantitatively with the experimental results of Q in his paper. This figure shows images captured by Q with his experiment and results with current developed model at the same time. For the quantitative validation, plot of normalized velocity and normalized depth of cavity is obtained and matched with the results of Q. A satisfactory agreement has been found with the little deviation around 1 point, that is due to interaction of vertices with the cavity, which decreases the velocity of bubble. Aeration can be divided into 4 stages. First stage is interaction of jet with surrounding fluid. Air won't entrain inside jet without disturbance in it. Disturbance will grow as jet travels further down. There should be sufficient length for this disturbance to grow. Disturbance travels down as in waves with increasing amplitude. So gas within its boundaries tracked along with the jet by the shear force. In the second stage of aeration is impact of jet. Jet energy and surface disturbances creates cavity on impact. Then jet transfers its momentum to the pool, which creates inverted meniscus at the surface of pool. This penetration depends upon velocity of jet only. Then the third stage is inertia dominated region. After impact, this depth increases as kinetic energy of jet converts into potential energy. Long step cylinder type cavity evolves as depression increases. After the critical point, cavity tries to gain the equilibrium and it separates from the jet and takes shape of bubble. Separation generates pressure wave which travels up and contract the cylinder which was formed earlier. And the last stage is surface tension dominated region. So after the initial cavity closes, different size of bubble starts to form due to continuous entrapment of air, and bubble plume which was formed initially will turn into cluster of bubbles. Later on, this bubble begins to rise and join with each other and ultimately releases air entrapped to the surface. So some parameters which strongly influences aeration phenomena are discussed here. First is effect of jet velocity. High velocity jet dominates surface tension and controls the jet disturbance. Higher velocity will leads to more disturbance of jet, but it also generates larger bubble and higher number of bubbles. So the rise in number of bubbles leads to reduction in depth of jet as shown in this graph. With increase in length of jet, disturbance will increase, which leads to more pre-entrainment of gases. Shorter jets will be smoother and longer jets will have more disturbance on it. Smoother jet will not be able to make more bubbles as in longer jet. Lesser the bubble, lesser will be energy dissipation, so greater depth will be generated as shown in this graph. This effect is studied with two surface tension coefficient. At lower value of it, inertia force dominates over surface tension force. Higher inertia force creates large number of bubbles with the bigger size. This will reduce penetration depth as shown in this graph. So these bubbles will rise quickly to the surface, which reduces duration of mass transfer. So to conclude, we built a code that gives the result for aeration in plunging liquid jet, and those results matches with the experimental results. 4 stages of aeration was captured clearly and explained with the results. With the parametric study, it was shown that high jet velocity increases bubble formation but reduces depth of penetration. Longer jet creates more disturbed jet, and eventually that leads to more bubble and shorter penetration depth. And in the last, it was shown that lower surface tension coefficient leads to shorter penetration depth. That's it from my side. Thank you for being an audience.
Thank you, Mr. Neeraj Chaudhary. So, very nice presentation. In fact, that is actually the area of interest from our group also. So let us first listen from audience if there is any question from audience side. I request, yes, please. Please carry on.
Have you seen some effect of buoyancy in this study?
No, actually, no. Am I audible?
Yeah, please carry on.
Yes, sir. Actually, buoyancy effect will be generated like we haven't incorporated separately. There is no separate module for buoyancy effect added in this code.
But your, this buoyancy force is added in the momentum equation, right?
No, sir. It means not separately. Means if it is generated with the because of the air property, because of the air density and viscosity. So not just separately, but it is incorporated in the Navier-Stokes equation.
Okay.
It means the bubbles, whenever it will be forming and it will be actually generating due to pinch off of the bigger bubble, larger size bubble, it will be coming up in the free surface 1 second back.
Yes, sir.
Am I right?
Yes. Yes, sir.
Yeah. Yeah. But I did not see this term. That's why I thought, let me ask.
Yeah,
okay. Thank you.
Any other query from audience? Well, so in that case, let me ask you, Mr. Chaudhary, that whenever you have seen all regimes, you are saying that all stages you have seen for the aeration. So what do you mean by stages? Can you name once again, please?
Sir, stages means like the first stages is interaction of jet with surrounding fluid. Means when it is starting and impinging on free surface of water.
Right.
So first stage is that. Second stage is impact, when the jet impacts in the pool.
Okay.
Then the third stage is when the inertia force of the jet will dominate the surface tension force.
Have you named in a separate manner this regime or this stage?
What's that?
Like you have said, the jet instability and then impact The third stage, have you named with some terminology?
No, sir. It's like inertia dominated region.
Inertia dominated region, right?
And the last stage is surface tension dominated region. Means surface tension force will dominate the flow. Then inertia.
So between the third and fourth, where you see that more number of bubble pinch-offs are happening, because it is aeration process, right?
Yes, sir. It will be in the final stage actually.
Last stage.
In third stage, there will be large bubble, and due to the surface tension force, in final stage, it will be converted into small bubbles.
Okay, okay. Thank you. So thank you once again for your nice presentation. We'll be now moving on to the last presentation, which is paper number 164. This will be talking about study of solidification process of PCM with shrinkage void effects in an annular. This will be presented by Jayantra Sutradhar, and the work has been done by Rohit Kothari, Anuj Kumar, and Dr. Santosh K. Shahu. So please play the video.
Welcome to all. Myself, Jayantra Sutradhar. Currently, I am pursuing my MS in Mechanical Department at IIT Indore. Today, I am going to present a study of heat transfer process of PCM with shrinkage void effect in an N+. Now, outlines of my presentation contains introduction, objectives, theoretical investigation, resultant discussion, and conclusion references. Now, at the beginning, I would like to give a brief introduction about PCM. Now, what is PCM? Phase material is a substance which absorbs or releases sufficient amount of energy during phase transition, which is useful in our day-to-day application like heating or cooling. These are some applications of phase material like electronic heating and cooling, solar heating and cooling, space heating and cooling, solar cooking, waste heat recovery, ice storage, and conservation of and transport of temperature-sensitive materials. These are the other applications of PCM. The question comes, why phase material is used in thermal energy storage systems? Because it has some good properties which can help in store sufficient amount of energy in a small volume, such as isothermal. It has isothermal phase change, storage and dissipation of large amount of latent heats. It freezes without much undercooling. It has ability to melt concurrently. It has certain excellent properties. It has no segregation. It is chemically stable and high heat of fusion. Now, in case of classification, PCM can be stored in two ways, either in direct large container or in a micro in the encapsulated container. So in case of direct or in large container, we have some disadvantages, such as smaller surface area for heat transfer. It has less thermal stability. It has high chances of leak due to thermal because it has a chance for high area of contact. Chemically unstable. Uniform heat transfer cannot be obtained from this type of PCM container. But in case of micro encapsulation PCM, we have some advantages, such as it is less reactive with the environment because it has less chance to contact with the environment. It's more chemically and thermally stable because it can make it has less contact with the environment. It takes less volume for heat transfer. In a small area, it can store sufficient amount of energy or more energy, greater surface area for heat transfer. So our present analytical model is all about the micro encapsulation, because it has more advantages. Now, these are the phenomena which will take place during solidification of PCM in micro encapsulation. During micro encapsulation, filling of PCM in micro encapsulation, air gap will be present near the boundary wall site. In our current model, we consider air gap near the cold wall side. Also, during shrinkage in solidification or during expansion melting, voids are created near the boundary wall side. So we all know that air is an insulating material. Therefore, during heat transfer, it will affect the efficiency of the container. Now, our objective of the present investigation are develop a theoretical model to analyze the effect of air gap on void on the heat transfer performance of PCM inside the cylindrical annulus, analysis of various parameters such as cold wall temperature, radius ratio, and temperature distribution of different domains of thermal energy storage systems, and to predict absolute and solid interface position for PCM inside the cylindrical annulus. Now, this is the flowchart of our analytical solution process. Now, coming to problem definition, which is effect of shrinkage void on thermal performance of phase change materials based thermal energy storage system. from theoretical question, we are analyzing solidification process of PCM. Our model consider three domain, mainly air domain, solid domain, and liquid domain. We are going to use separation variable method, and boundary condition are constant temperature boundary wall at the left hand side, and right, and all other three walls are insulated boundary. Result to be analyzed, temperature distribution and air solid and solid liquid interface position. Now, during our solution process, we are assume that PCM is a pure material and its melting is isothermal. 1D and conduction dominated heat transfer in PCM and effect of buoyancy and gravity are neglected. Air gap of negligible amount, that is 0.29 mm, is considered from the inner radius of the inner radius and near the cold wall, and solid interface is assumed at 0.3 mm from the inner radius. That is, air solid interface for the initially air solid interface is assumed at 2.299 mm from the center of the annulus, and solid interface is assumed at 2.3 mm from the center of the annulus. Constant thermophysical properties of air solid and liquid domain are considered. Here you can see figure 11 is the our problem domain. Left figure is the cylindrical annulus, and right figure is our three domain. You can see first domain is air domain, then second domain is solid domain, and the third domain one is liquid domain. All the three boundaries are insulated, but the left boundary is considered at constant cold wall temperature. Equation number 1A1B1C is our governing equation, and equation number 2A, 2B, 2C is the initial and boundary condition for the air domain. You can see at R equal to R in, that is at inner radius, TC, that is cold wall temperature, is considered. At R equal to R is at air solid interface, TP, which is called air solid interface temperature. At initially TAO is considered for whole of the air domain. Equation number 3A, 3B, 3C is the initial boundary condition for solid domain. At R equal to R is at air solid interface, TP is considered. At a solid liquid interface, we assume that that is constant temperature, melting temperature is considered, and at T equal to 0, that initially TSO is considered for the whole of the solid domain. Equation number 4A, 4B, 4C are considered for initial and boundary condition for the liquid domain. At solid liquid interface, TM is considered R equal to RSL, where at R equal to R out, insulated boundary considered, and at T equal to 0, TLO is considered as initial temperature. Now, equation number 5A is the heat balance equation for solving the air solid interface temperature. Equation number 5B is the heat balance equation, which is called Stephan condition, which is used for the finding the air solid interface position. And equation number 5C is a mass conservation equation, which is used for the finding the air solid interface temperature, which is useful in finding the shrinkage effect or shrinkage effect during solidification. You can see after using separation variable method, these are the final temperature distribution of three temperature domain. Equation number 6 is the final expression for the air domain temperature. Here AM is a constant, which is found by the equation number 6B. Similarly, equation number 7 is the solid domain temperature distribution. PM is a constant, which is found by the equation number 7B. Similarly, equation number 8 is the expression for solid domain temperature, and constant CM is found by the equation number 8B. Here, capital R is a function of R. Here, capital is a function of R, and N is called non in the separation variable method, which I will show in the next slides. These are the steps involved for finding the solution for air domain temperature. Here you can see equation number 9 is the governing equation for air domain temperature. Here we are using separation variable method, and for that, as it is a cylindrical coordinate, so we are using Bessel function of zero order for zero order. So capital R is function of R, as we said earlier, and it is expressed by the Bessel function of zero order. For finding the eigenvalue, that is time, you used equation number 9C, and the non N is found with equation number 9D. Similarly, for solid domain, equation number 10 is the governing equation. Capital R is a function of R, which is expressed by the Bessel function of zero order, which you can see from equation number 10B. And equation number 10C is used for the finding the eigenvalue E time, and equation number 10D is used for the finding a norm for the solid domain. So similarly, you can see equation number 11a is used for the governing equation for the liquid domain. Capital R is a function of small r, which is expressed by the Bessel function of 0 order j0 and y0. For finding the eigenvalue, we use equation number 11c time, and the norm can be found by the equation number 11d for the liquid domain. These are the properties and dimension of the enclosure. Now we are comparing our result to the experimental work of Agun et al. So from the figure we can see that maximum error of 2.055 is found from the comparison, which is in good agreement with our present analytical model. Now coming to figure 13, we can see spatial variation of temperature with radial changes at different times. Here we use 500 seconds, 700 seconds, 1100 seconds for plotting the graphs. So for 500, 700 and 1100 seconds, air solid interface is at 3.4 mm, 3.5 and 3.6 mm respectively, and solid liquid interface is at 7.2 mm, 7.4 mm and 7.8 mm respectively. So you can say as you increase the increase time, air solid interface moves toward the right hand side, towards the interflow boundary, and solid interface also moves toward the right hand side. So as solidification is increasing, shrinkage is also increasing. Coming to figure 14, here you can see a temperature variation with radial distance for different cold oil temperature T equal to 1000 seconds for density to 1.16. Now here we use cold oil temperature 293 Kelvin, 303 Kelvin and 313 Kelvin. So we can see from the figure that for cold water temperature 293 Kelvin, 303 Kelvin, 313 Kelvin, air solid interface is at 3.7 mm, 3.6 mm, 3.5 mm, and solid interface is at 8 mm, 7.7 mm, and 7.4 mm. So we can see as we increase the cold water temperature, air solid interface, movement of air solid interface is decreasing, and also solution rate is decreasing. So you can conclude that for lower value of cold water temperature, shrinkage is more, solidification rate is more. Come to figure 15, temperature variation with radial ratio for different radius ratio is showing. Here we use radius ratio 0.1 and 0.2. So for radius ratio 0.1 and 0.2, air solid interface is 2.3 mm and 3.6 mm, and solid interface is at 4.4 mm and 7.7 mm respectively. So we can see that if we increase the radius ratio, solid fraction is increasing, that is solution rate is increasing by 40.79%. Finally, we can conclude that an analytical model with constant temperature boundary condition in loss is developed to analyze the solidification process of a PCM, which is in good agreement with the existing experimental results. We analyze the various parameters such as cold wall temperature, radius ratio, and temperature distribution during the solidification process. During our we obtain temperature distribution of 3 different domains: air solid and solid interfaces for different times, for different cold wall temperature and different radius ratios. Finally, we obtain that shrinkage as well as solidification rate increases with the decrease in the cold water temperature and increase in the Stephan number. Lastly, we summarize that for the lower value of cold water temperature and higher value of radius ratio, the effect of shrinkage is more prominent. These are the references. Thank you. Allow me to present my analytical work.
Thank you, Mr. Shutrodhar. So this is nice work. First, let us take questions from audience if there is any. Okay, so in that case, let me ask Mr. Shutrodhar that whenever you have given the analytical model, so have you given any sort of model for the dendritic growth of the solidification front?
No, sir. No, sir.
So it's simply a straight solidification front is propagating, right? With Stephan equation, right? Stephan
Yes, sir. Yes, sir. Yes, sir.
Okay, okay, fine. So any other question from audience? Okay, so in that case, let us thank Mr. Shutrodhar for this nice presentation. And with this, we come to the end of this session. So over to you to the organizers.
I thank Professor Arup Kumar Das for chairing the session. Thank you, sir.
Thank you. May I log out now?
Yes, sir.
Thank you.
Thank you, everyone. The next plenary lecture will start from 11:45 a.m.
A very hearty welcome to Professor Drust, organizers and participants of FMFP. It gives me immense pleasure to introduce Professor Drust and sharing this session of FMFP. Thanks, Professor Dalal, for giving me this opportunity to share this session of Professor Drust. It's not easy for me to introduce Professor Drust with a few sentences. I met him back in 2002 at IIT Guwahati, just in front of the guest house, which was used temporarily as a conference hall at that time. I came to know about this person a lot when I worked with him at his institute for a longer period of time. He headed this institute of fluid mechanics with more than 80 staff, out of which probably about 50 plus people were basically PhD students, postdocs, and many guest professors. More interestingly, there were always a lot of Indians in his institute at any point of time. If you see any of the old IITs in India, you'll find at least 2 or 3 faculty who worked with Professor Drust at some point of time. If you see, he's a professor full of ideas, full of enthusiasm, extremely hardworking, and one of the renowned person in fluid mechanics in Europe. A brief bio about him. Professor Drust studied aeronautical engineering at the Technical University of Stuttgart in Germany and completed his MSc and PhD degree at the Imperial College of the University of London. Afterwards, he worked as a special research center at the Technical University of Karlsruhe, Germany, before he became a full professor at the University of Erlangen-Nuremberg, also which is in Germany. After retirement in 2007, he opened up his own company, FMP Technology, as a CEO, where he is still active. He continued there his research work in fields like laser Doppler anemometry, laminar and turbulent flows, extended Navier-Stokes equations, microchannel flows, coating and drying equipment, etc. For his work, he obtained various national and international prizes and is a member of 5 scientific academies. I request Professor Drust to start his lecture, which is Solutions of Some Unresolved Problems of Fluid Mechanics. Professor Drust, please.
Thank you. Good morning, everybody. Welcome to my presentation on solutions to some unsolved problems of fluid mechanics. I'm glad you could come. Usually I see in the audience whom I am talking to. That's now not possible, but I hope that quite some people will listen to this presentation. Let me start out to thank Professor Dalal and the organizing committee to invite me to this presentation. And I was hoping that I can use the conference as an excuse to visit India once more and meet many friends here who usually come to this meeting. Let me now briefly explain what I mean with solutions and unsolved problems. But before I do this, let me show you some historical picture here. I have drawn here on this picture the names of the various contributors to fluid mechanics. As you can see, it is quite a number of people who have contributed to the development of fluid mechanics. Usually we start out with Leonardo da Vinci, up here, and go then down through Bernoulli, through Euler, through Laplace. But I think the major contributions and the ones most important for my presentations is Navier and over here Stokes. They derived the Navier-Stokes equations, and we are using them these days for getting solutions to fluid mechanics problems. I'm asking whether they are really problems. Are they not just tasks which we can now solve with these equations, and we can solve them with numerical methods, analytical methods, and experimental methods? We are in this time now, where the necessary methods for measurements, methods for computations have been developed. The golden age of fluid mechanics exists, but as you will see, there are still some problems we cannot solve properly in fluid mechanics. Let me start out to explain the kind of problems I would like to tackle, at least to introduce you to some ideas about these problems. A problem does, in my opinion, not exist if you can solve it analytically, if you can solve it numerically, or investigate it experimentally. That is a fluid mechanics task, and we can get a solution by these methods we have available and the suitable equations or the test equipment. But a real problem is in fluid mechanics if we get theoretical solutions by solving the Navier-Stokes equations here, the continuity equations and the energy equation. And if you then investigate the flow experimentally and there is a difference. And now you have to decide what is the problem. You have two solutions. Both solutions are correct, but there is a difference. That are the kind of fluid mechanics problems I would like to talk about. Here now, one of these problems, micro-channel or micro-capillary flows. Here you see on the left-hand side, the results of Maurer for mass flow measurements, the mass flow through the microchannel. Theoretically, solving the Navier-Stokes equation, we get this solution, a parabolic velocity profile. If you go to smaller and smaller channels, and of course, higher and higher pressure differences, as you can see here, you find you get a difference between the solution to the Navier-Stokes equations and the measurements. This is now the kind of problem we have. And of course, we can not solve this problem really by modeling, because we would have to model the molecular interaction with its rough surface. So here is now the kind of problem I think we have and we need to solve somehow. You get a higher mass flow rate through a small channel than you should get solving the Navier-Stokes equations. Now, very often we think this is a microchannel flow problem particular to this flow. This is not the case. Have a look here. There is no channel. You have an obstacle in a supersonic flow, and you get a shock. And this shock wave, as it's called, has now an ideal solution, which is this line here. So the pressure, the density in this case, changes at this location. Experimentally, you find a change given by these points. And the line is the solution coming from the Navier-Stokes equations. The difference is there between experiments and theoretical solutions of the equations. And of course, now we have the kind of problem we would like to solve. There is a third problem I've indicated. This is a flow through a pipe. The flow is turbulent and it is heated from the wall. You can see this from the temperature distribution. Of course, as you go downstream, what you have is the velocity U increases because of the expansion of the flow, and also the temperature increases because the flow is heated from the walls. And again, you see now the theoretical solution and the experimental findings disagree. Of course, here now it can be that the K epsilon equation is incorrect, but some hints are also there that we have a similar problem to microchannel flows, and this is what I would like to explain to you. Have now a look at the equations. See if the equations, the predictions are not agreeing with the experiments, and we have the initial conditions and also the boundary conditions correct, then there must be a defect in these equations. And this I would like to point out. Let us start out with the Navier-Stokes equation. You have here on the right-hand side, you have the molecular transport of momentum. Don't call it friction. It is the transport of molecules of momentum. Similarly, you have in the energy equation the molecular transport of heat, of energy. But have a look at the equation here of the mass. There is no molecular mass transport in these basic equations of fluid mechanics. This is the major reason why we get these defects in some of the flows. Some of them I have indicated. So with a conventional Navier-Stokes equation, we have no mass diffusion. And if we now introduce this mass diffusion, we get the extended Navier-Stokes equations. And I will use these shortenings here to explain which kind of equations I'm using. Here now, the explanation for the missing term of diffusive mass transport, so molecular mass transport. Have a look at this checked area. Through this checked area, this can be the area of a cube. Through this checked area, you will find that molecular motions will transport mass. So there's a mass transport from here to through the checked area. It's indicated at that point. The last time the molecules interact with other molecules is one mean free path away from the checked area. So then the properties UM and rho at this location are transported up. There's also a transport of the molecules down through this, from this upper area. And this is now that combination of properties that enters the mass transport by molecules. Minus if the transport is downwards, plus if the transport is upwards. UM is given here for, you can now take series expansion, and then you will end up with these terms. And you can now build the products between these terms, and when two terms are different, have these difference operators in them, we take them out, being smaller than the terms that consist of these terms here, or combinations of one term with a gradient. At the end, you end up with this mass transport by the molecules. And you can see it depends on the mean molecular velocity and the mean velocity of the molecules, and the gradient of density, or the density and the gradient of the velocity. So you end up with this equation. Now you can use the ideal gas law and get now the correct derivations here expressed once in density and temperature and once in pressure and temperature. Outcome 2 term, this is fixed mass diffusion term. And then the temperature term here is Sore's mass diffusion term. So both terms are known, for example, in physical chemistry, and they are used there, but we are not using them in the mass transport equations of fluid mechanics. If there is mass transport, there is also energy transport, heat transport. So we can now do the same thing. There is heat transport from the bottom, there is heat transport from the top, and this is the top one down, and this is the bottom one up. And you can again take the difference, and then you get the diffusive transport of heat by molecules. Again, you can now derive this expression, and you might see that this is the mass transport, and multiplied by Cp times T gives you now the additional heat transport there is. This heat transport comes from the mass transport, which we are missing in the in the mass transport equation. And at the end, you get an expression here for the ideal gas, and you can do it also for the ideal liquid, as I show later on. As the last term, we have the transport of momentum. Here you can see the transport of momentum we usually have. It's this frame one. And then you have now again, due to the mass transport, which we are missing in the continuity equation, times uj and ui, that are the momentum transport terms that you get additionally in the Navier-Stokes equation. So we have different equations, and they are now shown here. And you can, they are very similar, but in this velocity, you have now the convective velocity and the diffusive velocity. Here also. And this is now the tau Ig term, which is also expressed in terms of total velocity. If you now put in the ideal gas law, you get this equation. And then you end up with a full set of equations you can also solve, but for total velocity, you get the convective and the diffusive velocity. Here's the diffusive part, or this is the diffusive. For an ideal liquid, this is the equation. The T here should be an XI, so I'm sorry for this. Now, let's take now this extended Navier-Stokes equations and solve it for microchannel flows. What you get now is this solution for the pressure difference Maurer used. And if you now do the computation for that pressure difference, you see that the numerical solution goes, also the analytical solution, which is possible here, goes directly through the data of Maurer. We do not need any modeling. We do not need to take care of this complex structure of the wall in order to get slip flows introduced. I can also not imagine how you can deduce slip flows from this kind of a rough wall interacting with molecules. Now, let's look at the shock wave. Here you see the Navier-Stokes equations. That's the ideal gas without any viscosity, you would lie here. Then if you take the solution by the conventional Navier-Stokes equation, you end up with this line. So there's a difference between the experimental results and this numerical solutions to solve shock waves. Of course, you can now model again what I have done here with a combination, but you don't make it quite. But if you now solve the extended Navier-Stokes equations, the line goes straight through the experimental results of Maurer. Here now let's look at the turbulent case. The dark points are the numerical solution with a classical K omega model. The points here, the circles, these large circles, are the experimental results. And if you now take the extended equations and you solve it with the K omega equation, you get some improvement. Of course, it's not perfect. Part of this might be due to the modeling of the K omega equation, which is the conventional one, and it should possibly be modified to when you use the extended Navier-Stokes equations. Nevertheless, you get an improvement, and more work is needed in this field in order to see how one can get better predictions when high temperature gradients exist in heated pipe flow. Let me now come to a second problem. In the first problem, basically there was a defect in the Navier-Stokes equations, and I explained this, and I showed that you can overcome this defect. We can extend these equations. I'd say, why did nobody else find this? The reason is, in my opinion, quite simple. We have a tendency to believe these equations and then find outside of the equation reasons for the discrepancies, which I have shown you on microchannels, channel flows, on supersonic flows, and strongly heated flows. The other problem I would like to tackle is indicated here. It's the laminar pipe flow. Here you see the pipe. Inside of the pipe, you see parabolic velocity profiles. And we know from many theoretical investigations that these parabolic velocity profiles are inherently stable. So you can knock them, but the viscosity will damp this disturbance out. An excellent summary of the existing work is provided by Schlichting. And if you look at this work and also some additional publications in the literature, you get these results. On this side, you get the critical Reynolds number, and at the bottom, you have the diameter of the pipe. And you can see there is not a single critical Reynolds number coming out, but a whole set of Reynolds numbers. And you also find the bigger the pipe, the higher the critical Reynolds number you can get. So if you want high Reynolds number, stable laminar pipes to be investigated, take big pipes. Of course, then you need big blowers and you need all kind of big apparatus. But nevertheless, this is what the literature presents. Now, why is this so? So there is definitely a discrepancy between the theoretical results here and the experimental findings. So we have a problem in the sense I have said I will consider them in this presentation. Here now, once again, what do we compare? We compare a pipe flow, which is infinitely long in the theoretical treatments. It has a set parabolic profile. And now we disturb this velocity profiles and the disturbances are damped away. And we compare this with a blower, which provides the flow through this test rig. It has some flow control, a diffuser, a plenum chamber, and nozzle. And then it has a long pipe, and the length is different from one experiment to the other. There's also equipment, measuring equipment, associated with this test rig, and we blow this air into a laboratory of different size. The laboratory walls are indicated here, and it's quite clear the differences which you have just seen, here in Reynolds number, come from these differences in the test equipment employed by the different investigators. Let us have a look at the cause of these differences. I start out with a blower. This is a blower which you have on one side of the test rig here, and it provides the flow through the pipe. Now, what property must this blower have to get the laminar to turbulent transition of pipe flow investigated? Here you see the friction factor of this blower is going down. At the point where the transition occurs, the friction in the pipe must go up. And this, of course, there's no means to do this. So basically, you can expect flow jumps. It finds now out it should increase the pressure, but this blower cannot do this for this flow rate. So it will go back, and at the end, you get all kinds of disturbed flow, but not the kind of disturbance you would like to have to go from this low point here up to the upper point. This is now the result. You have a laminar flow. And if you now increase the velocity by increasing the power output of the blower, you find that the flow finds, well, I should go turbulent, but then the conditions of the blower are not there to do this, so it jumps back. And this happens, and basically you get these kind of flow phenomena that are called in the literature slugs. Puffs are also there. They have a very similar behavior. Now, if you want now to study what really happens here, you must build up a test rig of this kind. In this case, we are using here a mass flow controller. So this mass flow controller can allow us to blow out air, and you use the increase on the high pressure side, the increase of the pressure, to increase the flow rate here. In this case, it is a slow process, as slow as our blower. You can, however, have another means to control this mass that is faster. So it can react very fast to the requested change in pressure or in flow rate. That's the plenum chamber. I will say something about that plenum chamber. And here you have an iris diaphragm where you can disturb the flow. We know if you don't disturb the flow, it will not turn turbulent. So since we want to study transition to turbulence, we must have some kind of a disturbance here. We have chosen this iris diaphragm to get the disturbance generated. It's automatically controlled, so you can close it, so put in a disturbance, remove the disturbance, and in this way get short disturbance, and we can see how these grow in the pipe. We used pipe between 0.5 and 8 meter in length, giving us longer times to observe these disturbance-caused flow disturbances. Everything was controlled by a computer, and we recorded everything and evaluated the data afterwards. And here's now the test rig. The test rig is, here is the test rig is quite normal apart from this disturbance element here. So what you now see is this mass flow controller. This I would like to explain here. The flow goes in the test rig here. In these sketches, I have drawn it in this direction. You have here a 3 millimeter closed ball, and this ball can be opened so that a pressure increase or a pressure can be used here to get force flow in this direction. If you increase this pressure, more flows goes. And this mass flow rate is now depending on this pressure change. If you change pressure, it is a slow change of mass flow rate. However, this mass flow controller can also be operated by changing the position of this ball. This ball is the same as here. So if you now leave this pressure constant, you can open and close this fast, and therefore control the mass flow rate by this area change. And this allows us now to see what the blower or the airflow generator is causing in terms of transition. Now, this is what happens. You open and close this device, and then this disturbance grows, and I show it here for the 8-meter long pipe. Over the distance, here you open and closed the, let's say this iris diaphragm, and then afterwards the flow, or let's say the flow grows in length, and at this point it leaves the pipe. So we only measure at the end of the pipe, and then it leaves the pipe. Before and after, the flow stays laminar in spite of these disturbances. So the laminar flow is there for the parabolic velocity profile, but there is a region where we can force the flow to become turbulent. Why that is so, I explain in a moment. Now, here is this length growth indicated. 8 meter, here you have triggered the flow. This is now the turbulent region. Here you close, not you close, here the flow leaves the pipe, and of course the flow afterwards is then laminar again. Very structured turbulent flows. It's very repeatable. This flow has about 20 trials, so 20 slugs, very precisely generated, very precisely observed, and they lie over each other. What you can also see is here, the front part of the pipe grows faster. The back part grows smaller, and this velocity difference is the reason for this growth of slug flows. So you can study turbulent flows in a well-controlled manner. Now let us have a look at some other situation. In this case, we have used the mass flow control system like this blower, and we obtained the kind of flows we knew from our pipe flow, but well controlled. And the other case now, which I would like to study, I use now here the fast change possibility of our air supply device. And I look now, in this particular case, at a plenum chamber. These plenum chambers have a tendency to oscillate. I've taken the results of Maurer. I've written the results of Maurer, and I've looked at the oscillations he measured. These plenum chambers with pipes going out behave like Helmholtz resonators. So they oscillate, as indicated here. And this oscillation depends on the length of the pipe, on the pipe diameter, on the shape of the plenum chamber. Everything influences it. If that frequency agrees with the mean velocity divided by 2 times the pipe length, you get a resonant. And it is now this resonance that controls your flow. This is what we have investigated and what we have measured. Here you can see now what you can produce with this test rig. If you run the flow now with this fast change in flow rate device, you get a completely different critical Reynolds number distribution than if you run it in terms of high pressure with a high pressure device. So this explains why you can have different results as you have them in the literature. Nevertheless, all literature uses blowers, or they use mass flow control systems, but the mass control systems are used very similar to the blower. So that's why all the data in the literature look alike. The highest critical Reynolds number we found is that of Fedinger. He used about 50 millimeter pipe, and the critical Reynolds number was measured to be about 1,000. In our case, when we run now the critical, the mass flow controller by that small ball, what you find out is you get 100,000, or you should get 100,000 if you run it with a fast control. But apparently at this Reynolds number, we already trigger some other device. So we could get this 100,000, but for some reasons, sometime later, it jumped down to a smaller value. It never jumped back again. So when you had once this critical Reynolds number adjusted, it would not go back. Nevertheless, it is interesting that you can manipulate the laminar to turbulent transition, the critical Reynolds number, by changing the blower, if you want, in this particular way. What do you now get? Here you see we have a critical Reynolds number of 7,000. That's what you get if you run this test rig with the pressure device to control the flow rate. If you now increase the flow rate, it jumps up and you get puffs and slugs. If you now use this ball bearing to encross the ball to control the flow rate, you get now oscillations. And these oscillations are fantastic, but the flow never turns turbulent. It oscillates and it stays turbulent until it catches sometimes another mechanism that turns the device turbulent. Look also at the Reynolds numbers. Before we had Reynolds numbers of 5,000 to 8,000. Now we have Reynolds numbers here of 53,000 to 41,000. And you see, sometimes you can drive that flow in a laminar oscillating manner into up to Reynolds number of 60,000. And then when you try to adjust it again, coming from the upper side, it only goes to 53,000. Nevertheless, with these fast changes, you can keep flows laminar, but oscillating, of course, up to 50,000. Let me now come to an end. I started out by explaining that the Navier-Stokes equations, the Navier-Stokes equations, the continuity equation, and the energy equation have a defect. This defect comes from the mass transport equation. There you can see 0, 0 on the right-hand side. On this case, you have on the right-hand side a molecular transport of momentum, a molecular transport of energy, but we have no molecular transport of mass. This is also the reasons that you can see in some of the textbooks on heat and mass transfer, that the heat transfer section has, let's say, 400 pages, and the mass transfer section has 50 pages. Why? There is no mass transfer. And this is, I think, a defect that we need to eliminate. I've done this for the extended Navier-Stokes equations, and I could see that discrepancies for microchannel flows can be eliminated. Discrepancies for shock waves can be discriminated. And discrepancies, or if you want, problems for heat transfer in turbulent pipe flows could be at least improved. Here are now, for these conventional equations, conventional form of the basic equation of fluid mechanics, the diffusion terms, no mass diffusion. The Fourier term represents the heat transport, and this is the Newton, the molecular transport term for momentum for Newtonian fluids. This is wrong, at least for laminar for, this is wrong, for ideal gas flows. If you take ideal gas flows, you can derive these terms. And this Mi is now introduced on the continuity equation, where on the right-hand side it was 0. This term also influences the heat transport. It influences the momentum transport. And if you put these diffusion terms into the basic fluid mechanics equations and you solve them, some of these equations that cause problems these days, the problems are eliminated. If you now look at microchannel flows, which I started out with, you can now see that the world is more perfect now. Down here, above Knudsen number 1, we have molecular dimensions in our flow cases. Down here, we are quite some distance away from molecular dimensions. And we are still using nowadays the, let's say, methods of modeling in order to get agreement, although molecular dimensions are not in place yet. This is not the case if you use here the extended Navier-Stokes equations, and as I have shown, you can get a good agreement. So my suggestion is to use extended Navier-Stokes equations, at least in those cases where you have high pressure and high temperature gradients. I hope I could show you that the Navier-Stokes equations require extensions. Use them when necessary and get good results. Thank you very much. Good morning, everybody.
Thank you, Professor Drust. It's quite an interesting discussions of extended Navier-Stokes equation. Basically, to summarize, you have considered 3 different things. One is like and of course, there is one interesting thing is that in application, in books of heat transfer, as you were mentioning, that if there are 400 pages, there are only 20 pages per mass transfer. Even in our lectures also, we do the same thing. We have 40 lectures in heat transfer and finally 2 lectures in mass transfer. So that tradition still continues now also. I think before I ask you something, I'll take it to the audience because there will be more enthusiastic people in the audience to ask you a few questions. Please go ahead if somebody have any questions to Professor Drust.
Hi, I'm Ramon here. I have a question. The extended Navier-Stokes equation for the mass diffusion, you have a term for temperature. So how does that play a role? Density, I can imagine something, but for the temperature, how does that play a role in terms of mass diffusion?
You know that the molecular motion, the velocity of the molecules, depend on the temperature. So what you have, if you have a temperature gradient, you have on one side of that checked surface I have shown, you have a higher velocity, because the temperature is in the velocity term, and you have a lower velocity just on the top of that checked surface, and that gives you differences in the velocities in the molecules, and if you enter that into the equations, you get this temperature term. This temperature term is the reason why you have Soray heat transport in fluids.
Okay, so is that equation derived from kinematic theory of molecules, kind of?
I started out with the Boltzmann equations, and I integrated and did all the kind of situations or all the kind of derivations, And at the end, I did not understand what physically happens. Then I went back and I used mean velocity, molecular velocity considerations, and I got the same results. So what I have shown you is not the treatment of each individual molecule, but the treatment of the mean motion of the molecules, and it comes out perfectly. You get all the terms right. If you look at the equations for Sorey, you also see you get the Sorey diffusion coefficient, which is amazing.
Yeah, thanks. It has been a very nice to go through your presentation. Thank you so much, Professor.
Good afternoon, sir. My name is Saroj Kumar Panda. I am a researcher in Department of Atomic Energy, Government of India. So we used to talk, my supervisor used to talk about you and your work many times during my PhD in IIT Delhi. So so it's a dream come true seeing you, listening you in a live session. So my query is, many times we generate experimental results, and also we generate predictor results from simulations. So sometimes we call it, it's a good result. Agreement is very good, and sometimes we call it as agreement is poor. So my query is, what basis we are judging it actually? Is there any parameter to judging it actually? Because that question is there in my mind since years. And what percentage error is acceptable, sir?
You see, the situation, if you do numerical calculations, presumably that's what you have done. Yeah. Now you get some additional things in. That is the accuracy of your numerical computation. So you get numerical errors coming in addition. So you first have to make sure that you get good numerical results with sufficient agreement, let's see, with the sufficient or accepted errors. And now what is accepted, that's very much depending on yourself. If you have a lot of money, you can get very precise computations. If that is not the case, sometimes in industrial computations that's the case, then you have to accept somewhat less good results. Now, there are two things. One thing is definitely the case. You can look at these n dots, which I have given here in the equations. And then what you can put in is your numerical results because you know your gradients. And if n dot comes out to be small, then you're sure you're not having these effects I was talking about. So that's possibly one way to see how good your computational results are in comparison to the real solution using the extended Navier-Stokes equations.
Okay, sir. Thank you, sir.
Now you see that sometimes when I came out with these extended Navier-Stokes equations, I got very much criticized, and I took the attitude, well, criticize. I know that these derivations are right, and if you don't accept them, then that's your business and not mine. Then I found out, however, that we have a lot of very good students doing their PhD with us in fluid mechanics, and we should point out this shortcoming of the existing Navier-Stokes equations and ask them to look into it. And I'm sure then people will find out that possibly, or clever people will then contribute to this and get this topic further. Okay. Important to me is also the second case, the laminar to turbulent transition. Basically, what I've shown there, it cannot be that we have the Navier-Stokes equations and let's say a set parabolic velocity profile, and we predict inherent stability.
Okay.
And then in the experimental case, we get turbulence. Now, why is that so? The turbulence comes from the equipment and not from the laminar profile in the pipe. I think this is also a topic one should put some clever students on it and see what comes out.
Okay, sir. Thank you so much, sir. Thank you.
Is there any more questions from audience? Professor Viswas.
Good morning, procedures. It was really, a delight to meet you again, although not physically through virtual media. I think Professor Wang is also present in the audience, Anbang Wang. This is really not a question, maybe in the form of discussion. This formation of slugs and plugs in transition, this is a very well-known classical problem started with Professor Rota, and probably it was concluded by you through your students and through very good publications. My point is that this slug formation and plug formation and this part of transition, this has really the paradigm where inherent disturbances come from ambience. Like this happened in the case of, if we go by the classical experiment of Professor Reynolds, Osborne Reynolds, that in the Cavendish lab, when he used to do experiments in the night, he used to get transition around 3,000, 4,000 Reynolds number, and in the day, and in the night, the transition used to take place. Flow used to be stable even for Reynolds number of 8,000 or 10,000. He got once 10,000. So basically, the disturbances that come from instruments, that come from surface, that comes from disturbances that come from surroundings, those disturbances can create a difference, but finally, that transition again. We get back to the laminar regime if the kinetic energy is not sufficient to support the disturbances, and this was very nicely done through this, almost like a super pipe you used, and I know all the equipment used there. Even this disturbance was created by this aperture controlling this aperture of the disturbances. Fraction of a second, it created disturbances and it went out. But with all this, I'm just, what I'm trying to say, that probably this has no apparent connection with the modification of Navier-Stokes equations that is proposed.
I agree with you. The second problem has nothing to do with the first part. So I did not use the extended Navier-Stokes equations because I felt what we are studying there has nothing to do with strong pressure gradients and strong temperature gradients, but it has to do with the equipment we apply. And we should be clear, although I didn't say this, turbulence is a question of the equipment we use and not so much of the jet we are studying or of the pipe flow we are studying. It is the equipment we have to drive the flow cannot do what the transition requires. That's basically the message of the second part. Right. So turbulence, we are trying to look at the local phenomena in a pipe and it is driven by the blower in the back. This is, in my opinion, something we should look closer at in future investigations.
Absolutely correct. And probably I can add something that the pipe which you used is really a super pipe. I mean, its manufacturing accuracy is absolutely amazing. And that is why this other, I mean, just the elimination of creation, I mean, puffs and slugs were possible. And it could be shown that it comes from the artificial disturbance that was created at the entry.
Yes, yes. I should mention Professor Pishwas was also involved in some of these investigations. Quite a number of people I did not mention here. I had one slide where I had all given them, but to get this lecture here recorded was quite something. And at the end, we had to take it out because even in the third trial to get a good presentation going, it didn't work.
No, that is not the point. But point is really, you know, having such accurate equipment like the pipe you used and your historical experiment of this backward facing step. They are also the accuracy of the positional accuracy, dimensional accuracy is really amazing. And, you know, it is to be appreciated for the years to come. I mean, creating such absolutely accurate test facility, it is probably not possible anywhere and everywhere. It was only possible in, you know, under your tutelage in LSTM. I mean, I do not know whether, you know, such equipment can be given to or you know, this are being used by others, or it should be continued such accurate equipment.
Yeah, now it is standing around doing nothing, which is a pity. Yeah.
Thank you, Professor. Thank you.
Thank you also. Thanks for the nice words.
And let me also tell other to the audience that Professor Durst, all of us can wish him for belated happy birthday. No.
Yes, thank you.
Belated happy birthday.
Happy birthday, Professor Durst.
Thank you.
Professor Dalal, you have some question.
I don't have any question. Just thank you, Professor Durst, for the wonderful lecture. I would request Professor Biswas to switch on the video, so it will be nice.
Okay.
Sir.
I thought that I know the bandwidth problem. Okay.
Yes, yes. Now it is looking fine. And also, I request Professor Wang to switch on the video. Then it will be very good.
You are muted.
Professor Talukdar, you please go ahead. Professor Talukdar.
Yeah, yeah. No, I have a simple question because I work in heat transfer. So by using extended Navier-Stokes equation, will there be a change in Nusselt number at the fully developed regime?
Ask you again, you are using the extended equation, and in which case you are asking you get the same results?
For example, in a microcell, if I apply an extended Navier-Stokes equation where you have a mass diffusion, so will it increase the Nusselt number compared to a conventional Navier-Stokes equation?
It depends. It will, because what you have is now you have also let's say if you do not have any strong temperature gradients, then it will only through the pressure term increase the transport. If you have now the temperature, and you have, let's see, if you have a high pressure gradient but a small temperature difference, you will have a higher number because of but it's driven by the pressure gradient. If you now have a very strong temperature gradient, you get an additional term coming from the temperature gradient. Okay. If you do this kind of work, take these equations in, and it is very amazing what you can see that come out. And you could see by comparison with Maya's data that
participate, it will be very nice.
I mean, I'm not really prepared for this impromptu discussion, but having Professor Durst among us is really amazing and absolute delight, because we can get ourselves enriched with his knowledge, with his suggestions, with his advice. And especially people who are planning for newer experiments, or who are thinking about converting some paradigm into correct experimental paradigm, from where the real conclusions of long-lasting value can be drawn. They can probably get in touch with Professor Durst and discuss their problems, and I'm sure they will benefit a lot. Professor Wang is also here, so I will leave the podium for Professor Wang. Professor Wang.
Thank you very much for the last words.
Yeah, Professor Durst.
Hello.
It's nice to see you, although not physically.
Yeah, thank you very much for coming to this meeting, and at least it gives me an opportunity to see you through television once again.
Yeah, it's really nice talk I've heard. Yeah. But it's only a pity. Here is a little bit in Taiwan. My system, I have some egg to disturb my hearing about this. But in any case, I saw from the slides, and to enhance the hearing program, I cannot catch quite of that. And have you any suggestion for the future, especially for the young generation, when they are making, for instance, they are making microfluidic and so? And have you any suggestion, direction for them?
One of the things is sometimes we get annoyed if we get two different results for one solution of a let's say of a flow phenomena. And we should not. We should think about the difference and see where does it come from. This was basically the message I was trying to get over. Let's say if we're doing fluid mechanics, the following, we set up numerical properties of a particular flow and we solve them. Results. Definitely, this is also necessary because we have now these fantastic methods and we can use them to solve tasks in fluid mechanics. And if we do this as an only let's say, way to deal with fluid mechanics, then we will have no progress. We need this progress that we say it's impossible that people who did not have the numerical methods available, also some of the analytical means or the means, that they have obtained all results of basic results of fluid mechanics in the 18th century. That I don't believe. We should look at these equations, the background of these equations, and see that we can use them, use the differences to find out where we can put in place and get equations, improved methods for the measurements, or for the investigations.
Okay. Yes, thank you. I think this will be a very delightful for the young generation to think about and progress further in the future. Yeah. And I heard you have birthday in this December, and happy birthday for that. And it's really nice to see you are still so healthy as before, without any change.
Well, you see, I have learned that if you want to become old, then you must have a lot of birthdays. So that's if you want to stay healthy, you must do some activities, and possibly the best activities you can have is in fluid mechanics.
Okay, yeah, and sorry, I have a meeting in 3:30, and I need to leave. And I thank all of the organizer and all participants. And I hope you could have still a very interesting talk with Professor Durst. Professor Durst, I need to leave and say goodbye to you.
Thank you for coming to this presentation. Yeah.
Yeah. Thank you. Goodbye.
Goodbye.
Thank you, Professor Wang.
Yeah.
Any discussion or any from audience? I think there are no questions. Professor Talukdar, so please go ahead.
Yeah, Professor Bruce, hopefully we'll see you very soon. When pandemic is over, definitely we'll see in Germany for sure if you are not coming here.
Yeah, I would have really come to this meeting because, as I said at the initial part of my lecture, this would be an excellent opportunity to meet you all. And I also hope it happens once more somewhere in the world.
Sure, yeah, it was exciting for me also. And and in the morning at home, I told I am going to, sharing a session for Professor Drust, which is a good news for my family too, because being here.
How's your family? Is it fine?
All good. My son is working now. He is a mechanical engineer working for a startup company in Bangalore. And my daughter is in class 11 now.
Oh, wow, they go, huh?
Yeah, we are going out.
Say hello to your wife and also to the children. My wife is also sitting there, so she also says hello to all of you. And also Professor Bishwas, Hello from myself and from my wife.
Yes, my heartfelt greetings to you, Frau Durst, and the entire family. It is, as I said, absolute delight to see you even from distance, and I look forward to meet you personally, whether in India or in Germany or elsewhere. I'm looking forward for the next opportunity to meet you.
Thank you very much. Thank you. And thanks for coming to this presentation.
Okay, then Amrez will close this session here.
Professor Dalal.
Yeah.
Yes, thank you. So I would like to thank the speaker, Professor Durst, for accepting our invitation and means delivering this wonderful lecture. And also I would like to thank Professor Biswas for attending this lecture, and Professor Wang. And I thank Professor Talukdar for chairing this session. And I thank all the participants who attended this lecture. So thank you very much. So we are now means again we will meet at 1:30 for the keynote lectures. Thank you. Thank you very much. Bye bye.
Thank you very much, and have a nice conference. Yeah. Thank you. Bye.
Have a nice day. Bye.
Thank you.
Let me quickly introduce the problem and its background and where we currently stand. Thin leaves, paper curds, they actually fall under their own weight. However, when the density ratio between the object and the surrounding fluid is near about 1, then the trajectories through which the object fall becomes complicated, and it's a subject of fluid mechanical studies. It involves complex fluid structure interaction, stability of the trajectories. In stable trajectories, the established regimes are mainly 3: flutter, which tumble, and the chaotic rhythm. To universally obtain different regions, different shapes of plates are actually unified according to the dimensionless moment of inertia, which will be defined later on. From 0.16 to 0.4, it is known as flutter, which is shown in the right here. Tumble, sorry, the flutter. The tumble proceeds from 0.4 to 3, which gives us an impression of complete rotation, and the flutter to tumble transition occurs generally near about 0.4, which is generally known as chaotic regime, which shows the signs of both flutter and tumble. In the current study, we have added multiple plates to see the effect of the proximity of each plate on the stability of the trajectories and the role of complex vorticity dynamics in deciding their trajectories. As the current study involves multiple plates, it's essential that we
Tu es trop grand pour comprendre les choses autour de toi.
Vous allez quitter à l'instant.
Qui est trop grand. On comprend les choses. Tu es trop grand pour comprendre les choses.
Vous allez lui faire un enfant. Vous allez laisser la lampe
trop grand. Prendre les choses. Tu es trop grand pour comprendre les choses.
Vous allez laisser la lampe.
I am in the correct room, right?
Yes, sir. Hello.
Yeah, I am in the correct room, right? This is
Yes,
Shabda
sir. Yes,
Srivastava.
sir.
Okay.
Yes, sir. You are in correct room.
Fine.
Hello, welcome, Professor Basu.
Hello. Hello.
Hello.
Hi. Hello.
Professor Basu.
Yeah, am I audible?
Yes, yes. Hello, Professor Basu.
Yeah. Am I audible?
Yes, you are audible. Yes.
Okay, great.
Video is coming, Professor Basu.
Sorry,
Okay.
video, yeah.
Yeah, it is coming. Yes. So let us wait for a few minutes. So Professor Pranav Mandal will be joining soon, and also few more participants will get. At the same time, always we see that participants are listening from YouTube.
Good afternoon all. I welcome you all to this session, and this session will be chaired by Professor Pranav Kumar Mandal from IIT.
Good afternoon all the participants. Heard by Professor Saptor. Professor Basu is currently DRDO Chair Professor in the Department of Mechanical Engineering at IISc. Professor Basu primarily works on multi-phase system, especially droplets at multiple length and time scales. He is a fellow in National Academy and Institute of Physics. Professor Basu is the recipient of DST Sarnajayanti Fellowship in Engineering. Professor Basu has authored many papers.
Okay, so let me share my presentation. Is the presentation visible?
Yes, please go ahead with screen. Yeah, thank you.
Okay. So I guess thanks to Amoresh for the invitation to FMFP for this talk. So my title of the talk is basically droplets and aerosols in the context of COVID-19. So this is a new area. The COVID-19 part is new, and we have tried to look at some of the phenomena from the droplet perspective in the context of COVID-19. And in this talk, we are going to cover maybe 3 of these areas. Okay, so some of the areas which are still pending, we will cover maybe in some other time. This is the team. Basically, it's a team of 3 people. Me, Professor Shetoprabha Chaudhary of University of Toronto, and Professor Abhishek Shaha, who was my ex-PhD student, now in University of California, San Diego. So this was the team who basically did all this work, sitting at 3 different locations across the globe. So let us talk about that, how basically COVID actually spreads. So as you can see that obviously you have, if you can watch my cursor, so if there is an infected person in the middle of all these non-infected person, with time you see that the number of infected persons grow, and how fast the question that normally people try to answer from an epidemiology point of view is how fast this disease actually spread. Now, the pandemic models are in general very complex, and they have very large uncertainty because of the different socioeconomic structures of the society and different other uncertain parameters. What we try to do is that, can we look at the small scale interactions, that is basically look at the droplet level scale and derive an appropriate pandemic model from the first principle. And let us see that how this actually works. So how does the person, infected person affect a healthy individual? So an infected person either through cough, sneeze, or breathing, talking, exhales a cloud of droplets, which basically migrates. It basically grows in size, as you can see, and migrates. And as the healthy individual breathes in the cloud, he can get infected. So this is how the infection actually works. So basically the respiratory events, as you can see, is obviously influenced by the ambient conditions, and we will see how. It also depends on whether you are wearing a face cover or not. The droplet clouds are basically transported and dissipated, and it depends on what is the ejection velocity, what is the ambient flow field, if there is a wind or not, all these factors. Then these droplets obviously do not remain of similar size, they actually shrink. And as they shrink, they also precipitate and leads to something called aerosolization. This happens due to the ambient weather conditions, temperature and relative humidity. So now, after all these cases, when the healthy subjects actually inhales these droplets, depending on what is the viral load and the biology and the immunity of that particular person, he can get infected. So basically, what is the respiratory or an expiratory droplets? They are basically multi-component in nature, the major component being water. Then of course you have salt, you have mucus, and you have the virions, basically the virus. And what are the phenomena or the key physics that are involved in this particular process? Obviously, it is evaporation, as you know. There is also dispersion, because droplets are exhaled in the form of a cloud. There is also settling, because of the larger droplets can actually undergo gravimetric settling. There is also evaporative cooling. That means when it's the same phenomena like the way that your skin actually cools. And then, of course, because it has salt, it can undergo crystallization, depending on what is the relative humidity conditions. So the lifetime of the droplet is a very complicated functions of all of these. So the exhaled droplets, therefore, should suffer three fates. First one is that it can infect, it can remain as droplets, and that means somebody sneezes in close proximity to you, you can actually inhale the droplets. It can transform to a nuclei, which is basically the desiccated droplets, and that also is what you call aerosolization. Then it can settle on surfaces, and this we call fomites. This is why we basically sanitize the Amazon boxes and the items that are received from Big Basket and so on and so forth. All three modes can actually cause infections. Obviously, the droplet mode remains the most dominant one. So the goal is to basically analyze the droplet physics, and the methodology that we are going to follow, and these are the three works that we are going to present. First one is experiments with an isolated respiratory drop. Then looking at the modeling process of the transport and subsequent epidemiology. And if we have face masks on, what happens on the droplet transport? So let's look at these three phenomena from a very unique perspective. So basically what we want to know by experimenting with isolated droplets is to understand first the evaporation pattern, the precipitation dynamics, and the fate of the virus in the precipitates. And this also serves as an input or validation for the computational models. So what we did was we considered and 1% aqueous NaCl solution as a surrogate respiratory liquid. We also did, by the way, experiments with real saliva. I am not going to mention the subject that was used, but the subject was a non-COVID person. And the transport and fluid mechanical aspect of the virus can be simulated using nanoparticles. These are called virus-like particles, hence the word VLP. So these are basically 100 nanometer fluorescent particles which are used as virus substitute. Because of the non-motility of the virus, this can serve as a good analogy to see how the viral loading actually, how the virus is actually distributed in the final desiccated samples. So the interesting part of the setup is that how do you generate a contact-free droplet? You use a levitator. So levitator here, it is an ultrasonic levitator, or basically what we call an acoustic levitator. The droplet size is about 500 microns. We can go higher and lower. We have done with both. And these are some of the literature that are available on the levitator work, so not going to go into the details. And there was a bunch of diagnostics that were performed, like laser imaging and high-speed shadowgraphy, to see what is going on. So this is exactly what the levitator looks like, and this is what the droplet looks like. So what happens? The global morphology, the droplet undergoes evaporation. Basically, it shrinks in size. After reaching a time of about Ti, basically, what happens is that precipitation is triggered. That means the salt starts to come out of the solution. And the precipitation is begins at this particular time scale. Then it, depending on what is the nanoparticle concentration, or basically the viral loading, it can form different types of end products. But morphologically, they look more or less similar to each other. Now look at the d by d naught plot. That means basically the diameter regression of the particles. What we see is that this particular graph shows pure water. So pure water just goes down, okay, and if you just square it, it will represent a linear line consistent with the d square law. But whenever you start adding, and this is actually human saliva, actual human saliva, and this is salt water and nanoparticles. So these are mixed here. As you can see, this is the desiccation curve. So water obviously evaporates the fastest. That is because it doesn't have any salt loading. So the vapor pressure is no longer depressed. So the water finishes off pretty fast. The salt water with nanoparticles, basically with and without nanoparticles, they show very similar trajectory because the nanoparticle loading is rather small. And they kind of mimic a very similar characteristics as a human saliva as well. Human saliva is, of course, a little bit more complicated. It has got a lot of other stuff as well. However, one key important thing that you should note over here, that the knee of this curves, that is where the precipitation is triggered, happens at around 0.2 to 0.3 of the initial droplet diameter. This is valid for all droplets across all size ranges. So it doesn't matter whether you start with a 20 micron droplet or a 300 micron droplet. The precipitation starts to happen, or the droplet diameter basically freezes at around 20% of the time scale. This is also validated by experiments with different droplet sizes. So if we look at the precipitation, as I told you earlier, it is basically independent of whatever is a nanoparticle loading. So it doesn't make much of a difference at what nanoparticle loading you are using. So within the error, experimental error, they are more or less the same. It's not valid if you actually increase the nanoparticle concentration to quite a bit. But viral loading is not that much anyways. So what happens is that this is how the droplet actually precipitates. So as you can see, there is a clear morphological change that actually happens. Interesting to note is that the solidification or the crystallization doesn't occur from the surface necessarily. It is from across everywhere in the crystal. And this is the final morphology of the crystal as it forms. This is because the salt homogenization rate and the evaporation time are very comparable. So basically you have a Peckley number which is very comparable. And as a result of that, you don't have the salt crystal preferentially coming out from the surface. So what we did after that was that we collected the precipitate, and then we did what we call a fluorescence microscopy on the sample. So as you can see that these are basically the viral loading that are within the crystal. So it almost looks like a fossil in which this is a crystal, and all the virions are basically embedded within the crystal. So they are distributed almost throughout the crystal. There is no preference basically between inner and outer, but for the most part, they are inside the crystal. And if you do an SEM, you can see the appearance of some of these nanoparticles at certain points on the crystal surface. So this basically shows that what we get is basically a viral virion-laden crystal that actually forms in the desiccated nuclei. And as we breathe this particular nuclei in, depending on our immunity and our physiological conditions, this is actually what leads to the viral outbreak. So this is the kind of the summary, in between summary. So the nanoparticles obviously do not affect the evaporation, precipitation, or crystallization, but apparently it actually resides within the crystal mostly, but also we see evidence of these virions outside the crystal as well. So this is an important finding because the virologists are very concerned about the distribution of the virions, because they obviously cannot see in a droplet cloud how the virus is distributed. So this gives a very logical outcome, and they can study the viability of these viruses inside a salt matrix, essentially. So now that we know all these things, now we are in a position to do a physics-based model of this entire phenomena, which basically includes the effect of the coughing or the breathing exercises that we do, because there is an air puff that also comes out of our mouth, not just the droplets. And it should be simple enough that it can be scaled up in a large-scale pandemic model. So the same solution was used. No need to model the virus because it is insignificant effect on the transport and lifetime at least. So what happens, as I said already earlier, so this is the famous, the regime diagram where you can see that some droplets, bigger droplets settle, smaller droplets actually aerosolize, and in between the droplets there is a very critical range, okay, where they remain as droplets for a certain amount of time. And this is one such picture which shows basically the droplet spread from the experiments of Lydia et al. So what is most important over here is that from a pandemic vantage point of view, and this is where our little background in combustion comes into the picture, this is very similar to a chemical kinetics based reaction mechanism model. In a reaction mechanism, commonly you have thousands of elemental reactions. So the chemical reaction, as we know, is all about this rate constants, that how fast the reaction goes. So in COVID-19, can one such rate constant be K, which is basically a very strong function of the droplet lifetime? So if K is a function of the droplet lifetime, then what is this particular function? That is the question that we need to ask. So we modeled it like this. For example, if P is a COVID positive person and he exhales, and this is the droplet cloud, and H is basically a healthy person. Okay, so this healthy person therefore breathes in air which is given by that hemispherical volume. Now, what happens is that the number of collisions between this healthy person and the droplet cloud that is ejected by this COVID positive person will give rise to the number of infections per unit volume, where NP and NH is basically the number of P and H respectively in that unit volume. And this is what the equation is. And depending on the number of collisions that actually happens, we have conversion of a healthy person to an infected one. So this is given by this equation. And therefore, this can be also cast in the form of a reaction rate, which is given as omega, where reaction rate which is dependent on NP by N total, where N total is the total population per that unit volume. So if you take all these equations and now you cast it into a reaction mechanism problem, you get these set of these three equations. So P and H gets converted into a susceptible person, which is a person in contact with the virus but not yet infectious. This person therefore gets converted to a COVID positive person in due course, and the COVID positive person either recovers or basically dies, with given a 3% mortality rate, which is taken from the literature. So as you can see that K1 must be greater than K3 for a rapid outbreak to happen, because you need more persons to get converted into COVID positive than the persons actually recovering. That's why in the newspapers you read that the rate of infection and the rate of recovery is so important. Okay, and then there are some incubation times in the meantime. So as you know, K3 is about 1/14 day. So this comes from the general guidelines of WHO. And K1 is basically the infection rate constant, which is the most important one. So you convert this to a system of ODEs, not going into the mathematical details. You solve P as an eigenvalue problem, and therefore you get the lambda 1 and 2. And as you can see that lambda 1 and 2 basically is dependent on this guy K1, where K1, if you cast it like this, basically depends on the droplet cloud diameter and the diameter of the breathable air. Both of these two things are determined by the aerodynamics and the heat and mass transfer of the droplets. So this is where we are getting at. Okay, so how to determine K1? So in order to do this, first you solve the aerodynamics of the droplet. So this is rather easy because the human cough is basically a puff, a jet initially, then it transitions into a cough. So you can cast this equation. So one is a jet equation and one is a corresponding puff equation with matching boundaries. So this will give you the velocity and the radial spread of the air surrounding the droplets. And the average duration of the cough is somewhere close to about a second. Actually, it's lower than a second, of the order of a second. But you look at the time scales, it scales as t to the power of half and then t to the power of 1/4 during the jet to puff transitions. Now what you do is that you basically solve for each droplet. Assume that the droplet lifetime is tau, so the average velocity of the droplet cloud is basically xp by tau. So therefore what you do is that you first solve the dispersion equation, basically the drag equation, and then you try to find out what will be the evaporation or the settling time tau for this particular droplets. So therefore this tau is basically a key parameter, and it is not trivial, as we know, because of the multi-component nature of the saliva drop. And we have already shown this picture to show that this is how the drop transforms into a crystal. So what we do in order to understand the droplet lifetime is the quest for the droplet lifetime. It can be solved in 1D or 2D. So the 1D is basically a quasi-steady model. It is given by the two limits, heat transfer limit and the mass transfer limit. Many of you are familiar with this particular formulation. Bm and Bt are the Spalding heat and mass transfer numbers. These are the corresponding mass fractions. These are actually corrected for the Raoult's law due to the presence of the salt concentration at the droplet air interface. So what you do after that is basically you solve for the instantaneous transport equation, okay? And this also takes into account the part of the heat basically goes towards raising the temperature of the droplet and towards the latent heat of vaporization. So this is the equation. Then actually after a certain amount of time, as you know that evaporative water loss leads to an increase in salt concentration. This is modeled therefore by a species balance equation. So what happens is that what is the amount of salt, if that is Y3, how fast does it actually come out of the solution to go into the crystal? This is triggered, this equation is only triggered when the concentration of Y3, basically the salt concentration, is greater than 0.393, which is basically the supersaturation limit. And the growth of the crystal is basically given by this kinetic formulation, which suspiciously looks like an Arrhenius form of an equation. And this is how we calculate what will be the crystal dimension. So packing all these things together, now if we do the modeling, you will find that we get a very close match with the experimental data. So this is model and this is experiment. And we also get the knee quite accurately. It also happens at 0.2, okay? And we also get the crystal size to the same order. So these crystal sizes, as you can see, are 60 micron or 120 micron. We get similar order size scales for the crystal size. Okay. Now, if you pack all these things together and you start calculating that what is the, for example, the droplet lifetime, you will find that the desiccation time, which is the total time for the droplet to become a nuclei, essentially is maximum for very high humidity and low temperature. So high humidity means if you have a Calcutta or a Guwahati type of a high relative humidity, the desiccation time will be rather long. This is not surprising because, yeah, things take a lot of time to evaporate. Okay, and low temperature is also for similar reasons. So cold and humid environment is a strict no-no for these kind of disease spreading. You can also do the same thing using a 2D model, not going to go into the details. It's a little bit more complicated because you solve now for the 2 dimensions inside the droplet. And so these are some of the equations, not going to go into the details. Here what you can do is that you can actually see what is the salt concentration inside the crystal, red being high and blue being low, and they almost match with the 1D code and with the experimental data to the same effect. So what happens is that now if we pack up everything, now if we determine the infection rate constant K1, which was what we were looking at, you will find that the infection rate, looking at these particular plots, you will find that the infection rate is therefore the highest for high relative humidity and low temperature. And the rate ratio, which is basically the cumulative number of positive cases on a given day to the cumulative number of cases 7 days prior, this is very, very high for high relative humidity. So as you can see, therefore, cold temperature and especially the monsoon seasons were not good for this pandemic, and which has been proven to be kind of correct, because that's where we got those peaks. And we are getting a second peak in the US and other places because of the cold environment. Okay, so this is essentially a rough summary where you can see that we have tried to understand, and of course we have a second model which is available where it takes into account the aerodynamics in the droplet in a little bit more details. This is the new paper that was published in just like a few days back. Now I'm going to end this talk with a very nice little story on the mask. So as we know that we all wear masks to reduce the distance traveled by their respiratory jets. Face mask also reduces the droplet count. So everybody says that it is very nice. But you know, in India, we also use different types of things like handkerchiefs, like many other types of bandana, for example. So this we use. How safe are those? So let us look at what happens to individual droplets when they actually impinge a mask. And this is very different from these type of studies, which looks at the total flow. We are looking at a very different mechanism right now. So this is an experimental setup. What we have is that we have a mask, and then we have a drop generator, which basically impinges droplet in the range of 2 to 10 meters per second. This is the range in which a human being actually coughs. And the diameter of the droplet is of the order of about 500 to 600 microns. So as you can see, the larger droplets carry the most volume, and therefore this is very essential to see what happens. These are the masks, so medical grade mask and locally supplied masks. These are the masks that we commonly use. These are the pore sizes of the mask. So you know, a single layer mask has got about a 30 micron type of a pore, and double layer it reduces, and then triple layer it basically becomes even lower. So let's see what happens when a droplet impinges a single layer mask, and just you can enjoy the. So what happens is that you cough, the droplet lands on the mask, and what comes out on the other side is much smaller droplets. This is amazing. You do that for a double layer mask, you still get a lot of droplets coming out, a significantly large number of droplets, and you see that they are also very small in size. For a triple layer mask, once you do that, there are almost next to none, except that one droplet once in a while that actually comes out. So what happens is that, depending on the type of mask that you are using and depending on the impingement velocity, right, you have a lot of penetration versus very low penetration. So our cough actually covers this entire range. So with a single layer mask, you have a lot of atomization that actually happens. Is it detrimental? But before that, if you can calculate the criteria for the droplet penetration just by taking a simple scaling argument, the initial kinetic energy of the droplet and the energy that is dissipated, the criterion, the penetration criteria is rather simple. Your kinetic energy has to be much, much greater than the dissipation mode. You can cast it in terms of Reynolds number essentially. So in other words, your Reynolds number versus this, which is basically the thickness and the porosity of the mask, has to be much, much greater than 1. And indeed, in the experiments, we see something very similar when the Reynolds number is high, which is the case for a single layer mask because the porosity is rather high in these cases. So you get penetration. So green signifies penetration, red signifies little to no penetration. So it kind of agrees with this nice little scaling that we have. So what happens is that as the droplets, however, comes out of the mask, you see these ligaments and you see this, formation of these ligaments. So it can be explained by a typical dispersion relationship by taking the relative instability criteria. And if you plug them in without going into too much details, you can predict the breakup time and the droplet diameter that comes out of the ligaments quite accurately with the experimental data. Now, this is perhaps the most important slide that you will ever see. So what happens is that when you actually have an initial size of the order of 500 microns, a single layer mask or a double layer mask for both types, what it does is that it leads to a significantly large number of droplets in the aerosolization regime. That means less than 100 microns. So less than 100 microns, you have a significantly large number of droplets. So all it does is that the mask, it shifts the PDF of the droplet distribution towards a smaller droplet size. Now that is very detrimental because the smaller droplets, as we showed in the earlier part of the talk, they don't settle. They actually evaporate, they desiccate, they aerosolize, and they can actually travel very large distances because they are small, and they can actually have a high potential of infection. So basically what I mean to say over here, that moment you put a bandana or you put a handkerchief, which is a single layer, what you basically are doing, you are causing more harm than good. That is because you are basically causing secondary atomization of the larger droplets in your cough to very fine mists, which can travel longer distances and can hurt. So that is the point that I wanted to emphasize over here, and this is a rather important finding, and this is valid across a very large number of experiments that we did. So this is not the typical, how much air or cough velocity, the cough profile that people normally do and see that where there is leakage from all sides across your mask. This is not that. This is direct secondary atomization, which can lead to aerosolization. So that is a rather important thing. Okay, so now the last part of the thing is that, okay, these are the stories that we have not told some other time. So we also did a lot of work with Narayana Netralaya on atomization and aerosolization in the case of eye surgeries, and this is one of the eye surgery. This is not a surgery actually. This is some, if any one of you have got what we call a glaucoma issue, you basically go to a doctor, they do an invasive procedure in which it involves an air puff hitting your tear film. And as it does that, you get a lot of secondary atomization of the droplets, which basically can contain the COVID virus. So that is a big no-no in these cases, okay, especially in these times. So it's coming from the eye, not from the respiratory tract. Similarly, we also did a lot of work on fomites. These are the two sample images that you can see. The red colored things that you see are all the virions, and the crystals and other things are basically the salts. So this is how a fomite actually is distributed, or a viral load in a fomite is actually distributed when your cough or breathe, the droplets that you breathe out, they actually settle on the ground. So with this, I basically end my talk, and I hope that I'm keeping the time. So I would be ready to take any questions that you might have. Thank you.
Thank you, Professor Basu, for such a nice talk. And I should say this is, a talk which covers state-of-the-art research topic. Now I can take a few questions from the audience.
Sure.
Someone raised his hand. I do not know. I mean, any questions from the audience?
I can see a hand raised. So.
Yeah. Mr. Sachin, can you please unmute your mic?
Sorry, actually, sir, this is hall 4, right? I have presentation number 177.
Sorry?
No. Okay. So now, keynote lecture is going on. Please wait. Any questions from the participants? I guess there is no questions. Okay, so if we have no questions, then I would like to thank the speaker once again from the organizing committee. Thank you very much for your time and talk. Thank you.
Thank you. Thank you so much. Thank you so much.
Now at the end, we thank Professor Pranab Kumar Mandal for chairing this session. Thank you all.
Thank you.
Hello everyone. So now we are going to have the presentation session. So this session will be chaired by Professor Gaurav Tomar from ISC Bangalore.
Okay, I guess we can start session 4 now.
Yes, sir, we can start.
Yeah, all right. We are starting like 5 minutes late. So just give me a second. Yeah, welcome to the second day, second session. I think this is session 5B in Hall 4. Welcome all for this conference. I would like to thank Professor Amresh Dalal and Professor Sentivellan, who are the people behind this conference. And in these times, it's any day, any time, it's hard to organize a conference, especially in these times when you have to take care of too many things that are happening online, and it's the handle on those things is not easy. To get a handle on those things is not easy. So I would like to congratulate Amresh Dalal for organizing the conference wonderfully. So we'll begin the session. The first talk in this session is by Arun Shaw. The talk would be on experimental and numerical investigation of water jet in air crossflow. I would request all the speakers to adhere to the timelines. And I think there are 8 talks in this session, and we have 2 hours for this. So I believe 15 minutes each. And you can keep your talk to something like 10 minutes and or 12 minutes and 3 minutes for question and answer. So with that, I think we can start. Is Arun is going to be presenting, or the presenting author is Saurav Sarkar? Okay. Or is it Arun Shaw? I think it's Arun Shaw. Is Arun Shaw here?
Sir, myself Saurabh Sarkar, I am present there, but the video was basically recorded by the first author Arun Shaw. So
okay,
we can play the video. If you have any doubts, I can try to clarify those doubts.
Sure, please play the video.
Hello, my name is Arun Shaw, and I'm going to present my conference topic on experimental and numerical investigation of water jet in air crossflow. I would like to thank the Mechanics and Fluid Power 2020 for giving me this opportunity to present my theme. Now, the application of a water jet or fuel jet in crossflow has major application in automobiles and gas turbines, particularly in combustion and afterburners. The better atomization of the fuel leads to better combustion since due to the atomization, it has more disintegration and all the molecules get sufficient air for combustion, and it also leads to the use of lean premix and pre-vaporized combustor because it is burning there. So the lean mixture could be used, and that lean mixture will lead to production of less NOx. And the use of this high velocity cross flow is just for to promote the disintegration, and it leads to enhance the atomization. Now, due to the effect of cross flow, the circular cross section of water jet gets deformed into kidney shape just because of the production of counter rotating vortex sphere on the cross section of the liquid column, and with the downstream of this liquid column, the liquid column is getting disintegrated, and the first disintegration is called primary breakup, and after the production of ligaments due to primary breakup, these ligaments get further disintegrated to smaller droplets. This is known as secondary breakup. Now the fundamental physics behind this whole disintegration of water jet to the effect of cross flow is the parameters that is responsible for whole this process is the jet diameter, the air and jet velocity, the air jet density and surface tension, and jet viscosity. Since they are huge parameters, so these are clubbed into some dimensionless numbers that are liquid to air momentum flux ratio, aerodynamic Weber number, and Reynolds number. So these are the 3 parameters that on which the whole process is getting dependent on. Now,
the objective. Now, the experimental test facility has been developed. It's integrated high-speed image stereography for observing all the interactions. Again, a 3D numerical model has been developed to visualize and to study it numerically. And at last, inside this 3D numerical model, high operating conditions and different operating conditions have been used for existing and compared it with existing correlations. Now, this is a typical experimental setup that has been developed in the lab test facility. Air compressor has been used to provide the cross flow, and this water tank has been used to supply the water. So the direction is perpendicular to each other for both gas and liquid. A nitrogen cylinder is used to pressurize this water tank to form a steady liquid flow, and for air compressors, it is coming from a small diameter pipe. So a diffuser, honeycomb, settling tank, and converging section has been used to make it uniform. The diffuser is used to expand the air. The honeycomb section just decreases the turbulence. The settling tank again provides the space to settle down all the settle down the air, and the converging section just converges the air flow through the cross section that is required, and it is a test section. Now, stereography setup has been used to observe all these interaction and record it. A high-speed camera that has a capacity to record at 4,000 fps has been used to study to take temporal recordings. And a LED array and diffuser section has been used for production of a uniform light source. Now, these are the parameters that has been used to for this whole experimental process. The water jet velocity has been increased from 1.3 to 2.2 meter per second, but the air cross flow velocity has not been changed. It has been kept constant. So the Weber number has been kept constant, and Q value, liquid to air momentum flux ratio, has been increased from 142 to 394. The Weber number has been kept constant because of the experimental test facility limitation. Now, these are the experimental results that has been found out. These are the locations of primary breakup that could be seen here. Here, the liquid is first getting disintegrated from the main column. This is the primary breakup section. Now, there secondary breakup could be seen here. Here, the liquid under the effect of cross flow, the liquid is getting disintegrated to form two or three droplets. It is a temporal view, and time has been and it been recorded at different time steps. Now, this green section is showing turbulent means highly unstable droplets. These droplets have tendency to break further for secondary breakup. Now, the red rectangle can be seen here. Here, the two droplets could be seen, which is collapsing to form a bigger droplet. Now, droplet collapse also could be seen in low Weber number. Because of this low Weber number, the sufficient pull force is not developed on the liquid droplet to move forward, so they are getting collapse with each other to form a bigger droplet. That is the opposite case of atomization, and also a disadvantage. And this section is where the secondary breakup could be seen here. Now, after the secondary breakup, a droplet has been formed here, and that droplet has been traced further. Now, tracing further, it is seen that it is a blue rectangle droplet has been pointed out here. It is traced, and it is shown that it follows a different trajectory than the mainstream of water, as to be seen here. The mainstream is getting collapsed here, but it is well suspended in the cross flow and moving forward. So this kind of droplets is the major objective to form. Since the Weber number is so less here, so it is not sufficient to produce this kind of droplets. So with the increase of the Weber number, this could be achieved. And further, here the droplet collapse is also seen here. These droplets is getting collapsed to form a bigger droplet. That is, I already talked. This is a disadvantage. Now, this is the thing that I told already. In here. Now, talking about the primary breakup, the primary breakup length is getting increased with the increase in the value of Q. Since Weber number is kept constant with increase in Q, the primary breakup length is getting increased since it gets more time to travel. It's getting more distance traveled for the same time with increase in Q. It is traveling a more distance before the primary breakup. But after this Q value, when it again increases to 394, then the primary breakup length decreases. This is just because with the increase in the value of Q, the turbulence due to the roughness of this nozzle exit is getting increased, so this is decreasing. The length decreases here. Now, this is also the surface wave is also seen here between these two, which is same for all these 4 cases, and it is found for value 2.8 mm. Now talking about the secondary breakup is also seen, but this is not phenomenal. This is seen very rare. So since because we have very low value of Weber number, so this is seen very less. It forms very fine particles after secondary breakup, which is advantage of using this cross flow. Now talking about this droplet size has been the largest droplet size diameter that is observed because of the droplet collapse is getting decreased with the increase in the value of Q. Now the smallest droplet diameter that is formed because of the secondary breakup, these are getting constant. Changing very less and having the order of 0.5 mm. The average droplet diameter is also at a value of 1.6 mm, which is approximately constant throughout the whole four criterion. The average breakup length, as I already talked, it is getting increased to a certain limit, and it gets decreased. Now, a numerical solution has also been observed with it is a Eulerian multi-phase UF model, and the time step is 5,000 time step, and the size is 10 to the power minus 5. This is the numerical. Now, validation. This numerical model is validated with the experimental experiment with the value of same value of Q and Weber number, and it is validating quite well. It is getting deviated after some time, but it is following the trajectory very well. Now, these are the numerical results that have been found, and it has been represented in the form. The same result, and it can be seen that the trajectory, the red trajectory, is followed by this Lee et al. And Delafre et al., which is it can be seen that it is falling very well. But after some time, when the value of Q is increased further, for Q is equal to 50, it is following only Delafre et al. So Delafre is just a correlation having value both Q and Weber number as well as Reynolds number, but Lee only have this value Q. So it will be seen here that for low value of Q, it is following both the trajectory, but as the value of Q is getting increased to 50, it is not following very well. So, so talking about the other thing, with the increase in the Weber number, as keeping Q constant and increasing the value WE Weber number, as I have increased the value WE from 100 to 120 and then 150, it is found that the trajectory does not change with increase in the value of Weber number, since all the 3 cases is depending on the Delafre and not on the Lee, because the Weber number is so high here. So all these 3 cases, it is mainly dependent on this Delafre correlation by Delafre, but the trajectory is not varying very much. The main advantage is just the Weber number is enhancing the atomization, since with the increase in the Weber number, the final droplets could be found for all the 3 cases. Means here at low Weber number, the droplets are much bigger, and with the increase in the Weber number to 150, the droplets have been found so fine in this case. So this is a major advantage of increasing the Weber number. Now this thing have been already told. Now last thing about this vortex counter-rotating vortex pair is this is the top view of in the VOF for the liquid jet, and as we increase the height, increase the cross section, taking from 0 to 6 mm corresponding to the base, then it is found that the trajectory, the cross section is changing from circular to a C kind of shape or kidney shape, since just because of the production of the counter-rotating vortex pair, as I already mentioned earlier. So thank you.
Okay. Thank you, Arun Shah. We can have questions. One question at least. Okay. I have a question. But before we move to the next talk, I think there is still 1 minute there for him. So the question that I had was, is somebody from the team here in this meeting?
Yes, sir.
Yeah. Who's this?
Sir, Saurabh Sarkar.
If you raise your hand, I would know. Otherwise, it's difficult to figure out who's speaking. Okay, Saurabh, so these are low Weber number cases. So your bond number, it's almost like when you open the tap, you have a breakup of the jet happening. It's very similar to that, no? Except for that, become. So if you would do these same experiments with right now, I think you have done with the horizontal plate and the jet is going upward. If you would have the horizontal plate in such a way that it is going downward, how would the results differ?
So I think the breakup will get delayed because in this case the gravity is opposing the upward flow. But in that case, if you are putting it in the downward direction, I think the gravity will assist. In that case, breakup will delayed. I think so.
Because the effective Weber number would be continuously increasing. So why do you say that it will be delayed? It will be accelerating, no, as it comes down. No?
No, you are talking about changing the orientation or the increasing the Weber number?
Changing the orientation, the inlet Weber number would be something, but then as it comes down, it will accelerate under gravity. And so, anyway, so thank you, Saurabh. We'll go to the next talk now. The next talk is by Sachin Janze, Kannan Iyer, Janani Shri Muralidharan, Hemant Punekar, and Vinay Kumar Gupta. They'll will be talking about development of one-dimensional model for bubble collapse. I think I guess who is the speaker here? I can't really locate.
Sachin.
Sachin.
Yeah.
Sachin is here. Okay. Please, you can play the video now.
Hello everyone, I am Sachin Janje, a research scholar from IIT Bombay presenting my work on development of one-dimensional model for bubble collapse. We are carrying out this work in collaboration with ANSYS to enhance the cavitation model, though I am presenting a part of work on bubble collapse here, but we have already carried out applicability of this model for actual cavitation applications and it gives very satisfactory predictions. I have outlined this presentation into motivation behind this work, mathematical formulation of this 1D model, its a solution methodology, and results and discussions from this work, and conclusions and future work. Motivation behind this work is to develop a generalized cavitation model. For that, if we consider a vapor transport equation to obtain generation and disappearance of vapor fraction alpha due to evaporation and condensation respectively due to cavitation, then to obtain these evaporation and condensation rates from the bubble dynamics such as Snellen's cavitation model, then we get source term as a function of dr by dt. Whereas earlier cavitation model has obtained this growth and collapse rates from the Rayleigh's expression, which is applicable only for inertial growth of collapse. Whereas there are some applications such as cryogenic cavitation where thermal effects are dominating. Therefore, we need to develop generalized bubble collapse model for generalized cavitation model as well as to study the cavitation erosion due to bubble collapse. For developing this generalized model, we are considering one single spherical bubble of radius r in a subcooled liquid of temperature T infinity and system pressure P infinity. The bubble contains a homogeneous mixture of saturated vapor with an interface temperature Tb and pressure Pb. So mass transfer rate due to condensation in this case is Q by HFG, and if we are considering bubble to be spherical over its complete collapse period, then it's a mass by volume. Bubble interface velocity dr by dt is equal to u plus v, where u is the liquid velocity at the interface and v is the liquid growth velocity due to condensation, which can be obtained from the temperature gradient at the interface, and liquid velocity can be obtained from the integrated momentum equation, which was integrated from interface to infinity by Euler's implicit method. To account for the thermal effects, we have considered the energy equation for a liquid in a Lagrangian form. Therefore, convective term is absent here. Therefore, from this 6th equation, we can obtain these 6 unknowns with the help of these initial conditions. These equations are solved iteratively and these are solved by Euler's implicit method. Based on the consideration of liquid growth velocity, which accounts for additional terms for the mass flux due to phase change, in the momentum equation, we have developed the two models. The first one is V naught equal to 0 model, which considers liquid growth velocity effect in equation 3 and 5, whereas V equal to 0 model does not consider this effect. Energy equation methodology considered in the present work is such that we are considering a spherical shell with a diffusion fluxes at inlet and outlet are D in and D out. Therefore, energy equation in the discretized form can be represented by equation 7. With the substitution of volume and the fluxes at the inlet and outlet, we will get the algebraic equation 9 with the corresponding coefficient shown. If we write the algebraic equation in a matrix form for all the cells, then we'll get the tridiagonal matrix, which can be solved by tridiagonal matrix algorithm for temperature distribution in the liquid. The domain length is maintained constant for numerical accuracy. While maintaining the domain length constant, we are conserving the energy along with the mass and momentum. Now we are obtaining the mass transfer rate due to phase change and liquid growth velocity from this restructured temperature distribution using a quasi-steady analytical solution for temperature gradient. Having developed the model for bubble collapse, we are benchmarking our models for different regimes of a bubble collapse. Floroches and Chow has classified the regimes of bubble collapse based on V effective, which signifies the ratio of time taken to collapse completely by heat transfer to that of the inertia controlled. Well, psi signifies the correction factor for saturated pressure temperature for real fluids from that of the linear variation for hypothetical fluids, and L is the thermal diffusivity. Based on this classification, case 1 is for the thermal collapse, cases 2 to 5 are for intermediate collapse, and case 6 is for the inertial collapse. We know from the transient heat conduction in semi-infinite slab that when we impose a sudden change in the temperature at the boundary, it takes certain time for a thermal front to reach the interior of the slab, where penetration depth is proportional to square root of thermal diffusivity into time. Also, we know that diffusion length required for a thermal collapse will be highest. Therefore, we have done domain sensitivity study for case 1, which is a thermal collapse case, where we can see that 10 times square root of thermal diffusivity into time is not sufficient domain, whereas 30 into square root of L into T max domain is unnecessarily large. Therefore, in the present study, the optimum size considered is 20 times square root of L into T max. Also, we have done node sensitivity where coarsest grid is of 252 nodes and finest grid is of the 3002 nodes. Also, we have done the error analysis with respect to the finest grid, and from here we can see that error for the coarsest grid is 21.7%, whereas for nodes with the 2002 error is falling below 1%. So we have considered a grid of 2002 nodes as the optimum grid, and from that we can obtain the grid size delta R from this domain length by n-2. Firstly, we have compared the numerical results from V naught equal to 0 model and V equal to 0 model with the experimental data of Floroches and Chow and numerical data of Bardia and Tugello. We have non-dimensionalized the radius with the initial collapse radius R naught and time with the T reference. From the results, we can see that collapse rate is very high initially and decreases as the collapse proceeds, where V not equal to 0 model is in good agreement with the experimental data of Floroches and Chow and is in also consistent agreement with the numerical data of Bardia and Tugello. Whereas V equal to 0 model shows slow collapse rate as compared to V not equal to 0 model. Therefore, we need to consider liquid growth velocity V for the thermal collapse cases. Slight discrepancy in the results might be due to bulk motion of the bubble in the experiments, whereas in the present work, We are considering the stationary spherical bubble in an infinite liquid. We have also compared the results for intermediate collapse case, where we can see that effect of liquid growth velocity V is very small, and we have good agreement with the experimental data except near the rebound point. This might be due to the spherical bubble assumption over the complete bubble collapse period. We have considered one more intermediate collapse case where we can see that for both V equal to 0 and V not equal to 0 model, the rebound is not taken place because this might be happening since at the minimum radius point, the pressure reached is close to critical pressure. So condensation rate is getting slowed down and growth velocity is shoots up at that point. So for rebound to take place, the maximum bubble pressure should be less than that of the critical pressure. The developed models are also compared with the inertial collapse case of Fujikawa and Akamatsu. From the results, we can see that collapse rate is slow initially and it increases as the collapse proceeds due to inertial term in the momentum equation. Also, V not equal to 0 as well as V equal to 0 model shows same results. Therefore, effect of liquid growth velocity is negligible for inertial collapse. We can see that our model are in excellent agreement with the experimental data. The conclusions from the present work are, we have developed a generalized numerical model for bubble collapse and which is in consistent agreement with the all regimes of a bubble collapse, and V not equal to 0 model is consistently showing good results for all the cases considered in the present study. In future, the work for the bubble collapse model developed will be extended to obtain the generalized collapse rate expression for cavitation applications and to account for effect of non-condensable gas content.
Okay, we can have a couple of questions. Please raise your hand if you have to ask a question so that I would know. No? Okay, Sachin, these multiple collapse you are not obtained, no?
Yes, so we are in a process of obtaining that. Like that collapse, like its magnitude will goes on reducing as we run it for more time. So we have obtained, but here since experimental data was only for the first rebound, so we only put that cases results to that only.
Does the code crash before it sort of?
No, means if radius goes to very small values of the order of critical radius, then code crash, it goes to very small value. Even in a thermal collapse case, where it continuously decaying with the time. So if radius goes to very small value, then that collapse code get crashed. Okay. Because V becomes very high, because it is a temperature gradient at that point is needed to calculate at the interface. So that V becomes very high.
Okay, fine. Thank you, Sachin.
Thank you so much.
We can move to the next talk in this session, that's on two-phase flow simulation of primary liquid jet breakup in coaxial jets. It's by Sai Kiran Asapu, Ankit Pandey, Anirudh Chaudhary, Shri Krishna Sahu, and Vagesh D. Narasimhamurthy. Who's going to? I believe Sai Kiran Asapu is going to be talking. So yeah, you can play the video now, please.
Hello everybody, here it's Ankit Pandey, the co-author and presenter for this paper. The topic of our paper is two-phase flow simulations of primary liquid breakup in coaxial jet. So let's begin the presentation with the content. First we'll be discussing introduction, geometry, domain and mesh, computational setup, followed by result section, and then finally conclusions and the references. So let's have a brief introduction first. As there are so many applications in which it is required that there should be a disintegration of the bulk liquid into small droplets. Some of the examples are internal combustion engines, aircraft engines, gas turbines, and spray painting. So this could be really interesting to study this process. And specifically in the engines, the fuel is required to disintegrate into small droplets, which give good combustion. And this process is known as atomization. And the device used for this is the atomizer. So this could be really interesting to understand this atomization process and see that how it happened. So first let's briefly discuss about the atomization. Atomization happens in two stages. First is the primary breakup stage and second is the secondary breakup stage. In primary breakup stage, the liquid jet disintegrates into the ligaments and shreds. And after that, these ligaments and shreds breaks into fine droplets. This stage is the secondary breakup stage. And this atomization process can be done in various ways. Specifically, most common are two ways: the pressure type atomization and the air blast atomization. In pressure type atomization, high pressure is given to the fluid so that there is a high relative velocity between the liquid and the medium air, so the atomization is there. And in air blast atomization, a high velocity air is given coaxially to the liquid so that there is a high relative velocity and the atomization process is proceeded. So this was the basic idea about the atomization process. And also one thing more, that turbulence plays an important role in the gas stream atomizations, because turbulence causes instability and eventually the breakup. So this could be really interesting to study the effect of various turbulence models, various models. So we are taking that also in this consideration in this study. Let me first tell you briefly about what we have done in our study. In this study, we have done the numerical simulation of an coaxial liquid jet. We have used 2D axisymmetric case in this, and we have simulated the Hogue and others paper for comparison. And we have used ANSYS Fluent and the OpenFOAM software for the study. In this we have used the RANS models, that is the Reynolds average Navier-Stokes based models, and we have seen the effects of the various turbulence models on the results. And also we have seen the effect of turbulence intensity on the results. And in this whole study, the volume of fluid technique is used to capture the air-liquid interface. This is the geometry that Hogue has used in his study. From here, liquid is coming surrounded by an air. And note that there is a presence of the lip is also there, whose dimension is 0.4 mm. And in this table, we have presented the parameters that are used in his study that we are simulating. Like liquid jet velocity as 2.5, gas velocity as 86 meter per second, Weber number as 58, and Reynolds number as 1270. Now let's move to the domain and the mesh that we have used in our simulation. For OpenFOAM and Fluent, we have used different domain and different meshes. The domain used for OpenFOAM is 50 dg into 12.5 dg, and the domain used for ANSYS is 100 dg into 20 dg. And the mesh for the OpenFOAM, we have used structured mesh with all quadrilateral cells, and in ANSYS we have used quadrilateral dominant mesh. And the mesh that we have finalized for ANSYS is 165K mesh, and for OpenFOAM it's 270K mesh. These meshes are finalized after doing the grid sensitivity test. And also in an OpenFOAM we have seen that close till 10 dg the aspect ratio we have kept as 1, and in the Fluent close to the center line we have created a fine mesh, so that the results are better. This is the computational setup that we have used for OpenFOAM and ANSYS Fluent simulations. solver used is interform solver in OpenFOAM. Convection terms are solved using second order linear upward scheme. Time derivative Crank-Nicolson. Time step used is 10⁻⁻⁶. Interface capturing in both of these is volume of fluid method. And convection term in Fluent is solved using second order upwind scheme. And time derivative terms are solved using first order implicit schemes. Let's start with the result section. In this section, first is the variation of the centerline velocity along the axial directions. In this, we can see there is a first increase in the velocity and then there is a decrease in the velocity. This increase in the velocity is due to the momentum transfer from the high velocity air to the low velocity liquid. And also we can see that in realizable K epsilon model, there is an early peak. This peak suggests that there is an early interaction between the air and the liquid. And after that, the velocity is almost constant, which is an unusual behavior. And also from these results, we can see that realizable K epsilon model is better predicting as compared to the KKL omega model when we compare the results with the experimental values. In this, we are comparing the axial velocity profile at two different axial positions, one at x equal to 20 dg and other at x equal to 32.5 dg. In this, we have non-dimensionalized the velocity with the centerline velocity and the radial position with the axial distance. In this, we can see that there is a difference between the spreading rate of realizable K epsilon model and KKL omega model. As we can see that in KKL omega model, the velocity is going to 0 at around 0.15, and in the K epsilon model and experimental results also the velocity is going to 0 at 0.25. So we can see similar thing is happening at both positions. So from this we can see that realizable K epsilon model are better predicting the results when they are compared to KKL omega model. And also we can see that the realizable K epsilon model of Fluent is more close to the experimental values when compared to the realizable K epsilon model of OpenFOAM. Figure, we are plotting the variation of the breakup length with the time. We can infer from the plot that KKL omega model is taking more time for the stationarity to reach. And also one thing that we have to keep in mind is that average breakup length for this study is calculated for statistical steady state, excluding the initial fluctuations. And we can also see that OpenFOAM realizable K epsilon model is over predicting the results, and this could be justified because in this case the liquid meets the gas flow beyond the air exit. The gas would have lost some momentum, and so breakup length is larger, which is not in the case of Aeroglow and ZOW, because in that lip is not present. As for initialization in OpenFOAM, we have used the turbulence intensity value. So in this, we are seeing that the effect on the results when we are using turbulence intensity value as 20% and the 10%. From this, we can see that in the breakup length, there is not much effect when we are taking the value as 10% or 20%. In the center line also, we can say that close to the nozzle exit, there is not much effect of the turbulence intensity. But as we go further, there is a little variations in the turbulence intensity. So, but this is not much significant in this case. These are the contour plots of the volume fractions of the water. From this, we can see that there is not a formations of ligaments in all three models. So the liquid jet is directly break up into the droplets, and this type of breakup is known as Rayleigh breakup. Although the membrane type of breakup was expected at the Weber number of 58 and the liquid Reynolds number of 1270. Let's see what are the conclusions that we can get from our study. First is that the OpenFOAM realizable K epsilon model predicts better results as compared to the OpenFOAM KKL omega model. And secondly, about the breakup length, it is saying that OpenFOAM KKL omega model is predicting comparable results to the experimental breakup length, which is unusual. And the OpenFOAM realizable K epsilon model is over predicting the breakup length, which could be due to the liquid meeting the gas flow beyond the air exit. And also it is seen in almost every case that realizable K epsilon model of Fluent is giving results which are in good agreement with the experimental value as compared to the OpenFOAM realizable K epsilon results. And also while studying the effect of turbulence intensity on the results, we have seen that there is not much significant effect of the turbulence intensity on the results, especially close to the nozzle exit. These are the references that we have used in our study. Thank you so much for your...
Thank you, Ankit. So we can have a quick question. Okay, Ankit, can you tell me, does it make sense to do turbulence? What would these turbulent models that you've used mean for these when you do axisymmetric calculations?
Sorry, sir, I didn't understand the question, please.
So you have done axisymmetric calculations, right?
Yes, sir. Yes, sir.
So you have used turbulent models for them, right?
Yes, sir.
What does it mean? I mean, are they flexible or are you just stretching it too much?
No, sir. Actually, we were trying to understand that which model is giving the better results for our simulations. So that's why we have tried to understand that which model is giving a good result. So as we can see from our study, that realizable K epsilon model is better predicting the results. So, and we have done on the RANS models only the study currently.
All right. Oh, there is a one question by Viresh Tekure. Yeah, please, Viresh. Viresh, you can go ahead and ask your question. You can unmute. I don't know. Anyway, thank you, Ankit. We'll move to the next talk now. The next talk is on optimal design of plunging jet velocity profile for higher gas holdup by Keshwar Rao Kanipuri and Panindra Jampana. Please start the talk.
Hello everyone, this is Koteshwar Rao from Indian Institute of Technology, Hyderabad. Now I am going to present on optimal design of plunging jet velocity profile for higher gas holdup. Flow of the presentation will follow like this. First, I'll start with introduction. We'll see here what is the motivation behind this work and importance of optimal design of velocity profile. And then I will discuss about estimation of gas holdup. In this work, we need to know the gas holdup at every time step. We cannot get this value from adjusted solver. We developed an algorithm and added to the multi-phase solver in OpenFOAM. I'll give a brief discussion about this algorithm. And then I will explain how to create a systematic bulge formation on jet. Then I'll give brief details of geometry of the plunging jet and governing equations. And then I will explain what are the optimal values of rise time and time gap values to get optimal velocity profile. Finally, I'll give conclusion made by this work. Improving the air entrainment is very important in many applications. In gas-liquid reaction, it will increase the interfacial surface area that results in improvement of product quality and quantity. In wastewater treatment, it increases the oxygen content and decreases the organic solvent. More aeration is more favorable in biological processes. And it improves the dissolved oxygen concentration for aquaculture ponds. Primary interest of design a plunging jet flow experiment is air entrainment. There is a significant research done on geometry of plunging jet
and design of jet inlet nozzle. But air entrainment also depends upon flow parameters. There are many parameters affects the air entrainment, like inlet velocity, jet length, turbulent length scale, and angle between jet and free surface. Jet velocity is one of the vital flow parameter which can significantly influence the amount of air entrained. As we know, higher jet velocities will produce higher gas holdup, but it needs excessive power to maintain high jet velocities. We observe that initial impact of jet will create the large size cavity which leads to generates more air entrainment. Experimental studies reports that we can obtain the similar effect when bulge on a jet impacts on free surface. Algorithm for estimation of gas holdup contains 4 steps. In step 1, based on alpha values, we'll extract the interface cell label data. In step 2, using connected components algorithm, we'll get the free surface cell label data. We'll get many connected components, out of which first 2 largest connected components represent the free surface in 2-dimensional simulation. The largest connected component will represent free surface in 3-dimensional simulations. In step 3, once we get the free surface cells data, we need to estimate the free surface locations. It exists between 2 adjacent free surface cell centers. One should have alpha value less than 0.5, other should have alpha value greater than 0.5 or vice versa. Then, using a midpoint rule, we can estimate the location of the free surface. In step 4, we develop the local free surface curve. For simplicity, we use linear fit. Then estimate the amount of gas holdup by summation of volume fraction of the air contained cell below the local free surface curve. For enhancement of amount of gas holdup, we use the periodic and optimal size of roughness. When there is increase in jet inlet velocity, that leads to outflow of liquid on jet surface. Due to this, the bulge generated on jet. In this work, we use the jet velocity profile as shown in the figure, where Vj is nominal velocity and Vd is disturbance velocity and Tb is rise time. It defined as the amount of time disturbance velocity is active, and Th is time gap, and that defined as the amount of time there will be 0 disturbance velocity after formation of bulge. We conduct the numerical simulation for different velocity profiles to estimate the optimal inlet velocity profile. For this, 2-dimensional plunging jet flow simulations carried out by volume of fluid approach with K epsilon turbulence model. The geometry of the plunging jet shown in figure, where tank top is open to atmosphere, tank width is 0.3 meters, height of the tank is 0.5 meters, and outlet velocity is calculated based on inlet velocity so that water level in tank is constant. Governing equation. Continuity equation used as a pressure correction equation. Momentum equation used as a velocity estimation equation, where tau ij is viscous stresses, tau Tij is turbulent stresses. Turbulent kinetic viscosity calculated based on K and epsilon, and alpha estimated from phase fraction equation. Transport equations for turbulent kinetic energy and energy dissipation rate given here, where dk and de are effective diffusivity for K and epsilon respectively. P is kinetic energy production rate, and C1, C2, C3 are model constant. And density, surface tension force, curvature estimate as follows. These governing equations solve in open form following approach. The momentum and continuity equations are solved implicitly using PISO algorithm. Then explicitly estimate alpha value using volume fraction equation and turbulent kinetic viscosity using transport equation of K and epsilon. This is visualization of formation of bulge on a jet and its impact. Images corresponding to time at 0.02 seconds, 0.04 seconds, 0.06 seconds, and 0.09 seconds after disturbance velocity active. The size of bulge only depends upon rise time when jet length is constant. Using kinematics and observations from the simulations, we find the optimal rise time. In this case, it is 0.1 second. If we increase the rise time more than optimal rise time, there won't be any much increase in air entrainment. It is obvious that larger bulge will generate the larger size cavities. We are interested in increasing a gas holdup, not to generate a larger cavities. Therefore, we also perform the simulation studies by generating a smaller size cavities. We can generate two medium-sized bulges with rise time TBO by 2 instead of a single maximum size bulge. Similarly, we can create smaller size bulge with rise time TBO by 4. When bulge impacts on free surface, it generates the cavity. It will take time to entrain the generated cavity. That's why we need to give some time gap between two successive bulges. We estimate the optimal time gap for all three cases that we can see in figure 1. From figure 2, we can observe that the medium and maximum size bulge generates nearly same average gas holdup. But the medium size bulge gave the maximum average gas holdup. Conclusion made by this work. We investigated the gas holdup for different rise time and time gap. We observed that behind the optimal rise time, there is no significant change in size of the bulge for given jet length. We also estimated the optimal time gap value for maximum, medium, small size bulge. We observe that optimal time gap value depends upon size of the bulge. The maximum and medium size bulges generate significantly more gas holdup. The medium size bulge gave the highest average gas holdup. All bulge cases provides more gas holdup than undisturbed jet. These are the papers used in this work.
Okay, thanks, Koteshwara. We can have one or two questions. Please raise your hand if you want to ask.
Yes, sir.
Yeah. Who's this? Yeah, we can have a couple of questions. Are there any? Okay, fine. I think we'll move to the next talk. Thank you, Koteshwara. All right. Okay, the next talk is on shear deformation of ferrofluid droplets under uniform magnetic field in a Hale-Shaw cell. This presentation is by Akash Punia, Varanasi Sai Subhankar, Amit Kumar, and Sandeep Saha. It's not clear who will be presenting this. We'll know. Okay. Can you start the talk, please?
Hello everyone, I am Sai Suvankar from IIT Kharagpur and I will be talking about shear deformation of ferrofluid droplet under uniform magnetic field in a Hale-Shaw cell. So let us know something about ferrofluids. These fluids are colloidal fluids and are composed of nanoscale ferromagnetic particles. They also become highly magnetized in the presence of a magnetic field. Some of the magnetizing action on the ferrofluids can be seen in the right-hand side pictures. Now, these ferrofluids have found numerous applications in the recent years. They have been used in medical sciences for the MRI contrasting agent. They have also found their application in rocket propulsion as ionic electron sprays. The rheology of ferrofluids has been a hot topic of interest and it has been studied experimentally, numerically and analytically over the years. Asymptomatic theory is used to calculate the ferrofluid deformation in the presence of magnetic field. The KH instability at the interface of the magnetic and non-magnetic fluids has been solved analytically by Miranda and Widom. Now, Fluent Theory Guide of 2018 helped us to set up the simulation of the ferrofluid drop in the presence of an external magnetic field in the Hilly-Shaw cell. This is our rectangular computational domain with the ferrofluid drop at our desired location XC and YC. The computational domain is of the size 30R cross 30R, where R is the radius of ferrofluid drop. All the walls are imposed with no slip impermeable wall condition. The top and bottom wall are given adequate velocities as and when required. The main challenge associated with the handling of multiphase flows is to accurately capture and track the interface shape. So for that, we have used coupled volume of fluid and level set method on a fixed Eulerian grid. The level set method more or less shares the ideology with the WOF method. WOF method, on one hand, doesn't account for accurate reconstruction of the interface shape, but in case of level set method, we see that the interface shape can be reconstructed identically. The disadvantages attributed with both LS method and WOF method can be handled well with each other. So that's the reason why we have resorted to coupled WOF LS method for further computations. The magnetohydrodynamics aspect is also considered by combining Ohm's law and Maxwell's equation. We will also look at some of the non-dimensional numbers. One is the magnetic bond number, which relates the magnetic force to the interfacial tensile force, and the other is the capillary number, and the third one is the shear rate. So we have considered two sets of grids, D1 and D2, for our computations. The grid on the left hand side is considered for the deformation case only, but on the right hand side we see a grid which has been used for position tracking of the ferrofluid drop. Now on grid A we will be doing further grid independency test. So we have used three sets of grids as can be seen in the table below, and we have considered the value of deformation parameter to choose which grid is the most appropriate one for our computations. The deformation parameter D gives a fair estimate of the droplet shape at the steady state. Now on the middle figure we see the shape of the interface at steady state for all the grids. At the coarsest grid the shape is not accurately captured. Instead we see some sort of wiggles or wobbles in the interface shape. But as we increase our grid resolution, we see the smoothness of the shape is increased. At the same time, we have also plotted the mass flow residual across the interface for all the grid sizes we have considered. And we have seen that as we are increasing our grid size, we can see almost 50% drop in the residual values across the interface. So to save some of the computational time while maintaining the accuracy of the computations, we have chosen the grid 200 cross 200 for further computations. So we have considered three cases: deformation under simple shear, deformation under both shear and magnetic field, and position tracking of the ferrofluid drop under external magnetic field. The results for each case will now be discussed. So first we will look at the deformation under simple shear. Viscosity ratio is defined as the ratio of viscosity of the ferrofluid drop to the viscosity of the background fluid. Now we have compared our results for two sets of viscosity ratio to that of Taylor's theory. Now Taylor's theory gives us an analytical expression for the deformation and the capillary number. At higher viscosity ratio, we see that our results are in good agreement with those of Taylor's theory. But at lower viscosity ratio, there is some discrepancy in the results obtained. Also, at higher capillary number, the deformation increases because the relative strength of the surface tension decreases compared to imposed shear, and hence its ability to resist the deformation decreases. We will now look at the behavior of the ferrofluid drop under both shear and magnetic field. We have validated our results with asymptotic theory. Now this is in the case when B and Y is equal to 1. At higher capillary numbers, we can see that our results are in good agreement with the asymptotic theory. Now, if we look at the overall picture, we will find that the deformation increases linearly with an increase in capillary number. This is due to a decrease in the relative strength of the surface tension force that resists the interface deformation. Now, this deformation is more significant when the magnetic field applied is in the same direction as the imposed shear. We can also see that with change in magnetic bond number, the value of the deformation parameter do not vary significantly. So the variation of alignment angle theta with capillary number is shown here. With increase in capillary number, the shear rate increases. With increase in shear rate, the wall velocity increases. Now when the wall velocity increases, the clockwise circulation in the cell becomes stronger, and this stronger clockwise circulation forces the droplet to align itself with the direction of the shear, and hence the alignment angle theta increases with increase in capillary number. We also see that the value of alignment angle theta does not vary significantly when the magnitude of the bond number is increased. And similar to deformation parameter, we also observe that theta is more when the magnetic field and shear imposed are in the same direction. In this case, it is the x direction. So far we have discussed our steady state results. Now we will be looking into our transient results. To ward off any buoyancy effects, equibuoyant fluids are chosen. Viscosity is deliberately kept higher than 0.1, which is actually 1 in our case, to avoid any instability in the droplet interface. The droplet is predefined at minus 13.5 cm, 0 cm in the D2 grid that we have seen earlier, and it is suspended in a magnetic field which is uniform all over the computational domain. In terms of bond number, we have varied the value from 10 power minus 1 to 10 power 6. The magnetic field intensity applied in the x direction results in an upwards motion of the ferrofluid drop. Now, this upwards motion is solely attributed to the pressure difference that is created along the y direction. Now, if we look at the pressure along the x-axis, we see that there is no appreciable pressure drop across the x-axis. Hence, we can conclude that only the pressure difference along the y direction causes the bubble to move in an upward direction. Here, the bond number is kept low in the range of 0.2 to 10, and the average y velocity is obtained for each case over a time interval of 2 to 8 seconds. An increase in the magnetic field strength results in faster motion of the ferrofluid drop due to the increased magnetic force and the pressure gradient. The average velocity in this case is increased from 0.02 cm per second to 0.25 cm per second when the bond number is increased from 0.1 to 10. In the right hand side GIF, we see the initial back push and wobbling while it travels upwards. Here we look at some of the results at very high bond numbers for 200, 500 and 1000. It can be observed that in the presence of higher magnetic strength, the bubble traveled a longer distance along the y direction. The oscillations observed in tracking as the bubble approaches the upper boundary is due to the combined effect of surface tension and magnetic forces. The distance traveled by the bubble in different magnetic fields is shown in the figure. It can be seen from the plot that there is a lag in the motion of the bubble during the initial phase where the bubble squeezes towards the left before its vertical motion. This lag seems to increase with increase in bond number initially, and then it seems to decrease with further increase in the bond number. After a specific time interval, all the distance time plots are seen to be linear and parallel to each other, which make the average velocity independent of the bond number. Now this average velocity is around 0.3 cm per second. However, further analysis is required to understand in detail the underlying physics. Here we look at the process of position tracking. First we obtained our simulation video, then we converted into grayscale image, and then we enhanced it. Now we obtained the bubble centroid coordinates and we converted those coordinates in meters from pixels. Now once we obtained those coordinates using the below formula, we estimated the velocity of the ferrofluid droplet. So this brings us to the conclusion of our present work. First, we studied the deformation of ferrofluid droplet under simple shear flow and obtained that there is more deformation for less viscosity ratio. We also studied deformation under shear and magnetic field, and we found that the deformation is more when the magnetic field is along the shear direction. We also calculated the angle of inclination of the droplet. We also tracked the position of droplet under magnetic field only, and we found that the velocity saturates at around 0.32 centimeter per second. We are very much thankful to the Department of Aerospace Engineering, IIT Kharagpur, for providing us with adequate computational resources. We are also thankful to Mr. Nilakas Biswas and Mr. Shobit Mishra for their great contribution. So these are the references.
Okay. Thank you, Shubhankar. We can have a couple of questions. Is Shubhankar here, or Akash, you will be answering the question?
So we both are here, and we'll try our best to answer.
Okay. So can we have a couple of questions on this, please? Okay. Yes. So okay, if let me ask you about, do you think the deformation is there? It's okay, but do you expect that if you increase the magnetic field, you would also, there's a possibility of breakup happening, pinch off happening of a very small droplet from the edges of the droplet?
It depends upon the magnetic strength actually. In fact, in experiments, we have seen that in literature it has been reported such pinch off being happening. And they have found it in experiments where they have considered very high magnetic field strength. But we have not considered that much, so we didn't see that phenomenon here.
I see. Okay. Nice talk. Thank you, Akash. We'll move to the next talk. The next talk is by Govind Sharma, and it's on Bunny Ray.
Everyone, my name is Govind Sharma, and I am presenting quantitative and qualitative assessment of circular and square particle sedimentation. Particle sedimentation is ubiquitous phenomena in nature as well industrial processes. Settling of particles in quiescent air, settling of carbon and plastic element ocean, slurries, biofluid dynamics, flow through nasal cavities. These are some of the common examples of natural occurring phenomena. Industrial wide applications such as fluidized suspension bed, erosion of metal, conveying of cold particles, particle flow through channels. Here we showed two pictures that are taken from internet. First one is a erosion of the sand bed, and other one is fluidized bed reactor. Fluidized bed reactor is one of the most common example of industrial application where we find fluid particle interactions are occurring exclusively. For modeling the fluid particle interaction numerically, fluid and particle are defined on Eulerian and Lagrangian field respectively. Distributed Lagrangian multiplier DLM translates presence of particle in terms of force as a source term in the governing equation of the fluid. First, I show how particles are represented on Eulerian map using in sketch.
Is that a problem with the audio or in the video itself, or?
These are orthogonal grid lines, and this is circular region of the particle. In DLM, particles are represented using Lagrangian marker instead of a solid surface. These Lagrangian markers can form any specified geometry, circular, square, triangle, any shape. We use IBM, open source tool that is a image boundary adaptive mesh refinement. In IBM, particles are represented at finest level of the mesh hierarchy. We define two Reynolds number, RET, that is based on the terminal settling velocity, and REC, which is based on convective velocity, nothing but a gravitational settling velocity, which encompasses density ratio of the particle to the fluid. These are 5 set of equation of the fluid particle system. First equation is a conservation of the momentum. This FV term is nothing but a representation of the particle in the fluid as a source term. This FV is known as a Lagrangian force in fluid particle interaction. This equation and this last equation, these are exchange of the variable between the Eulerian and Lagrangian field. This equation is a representation of no-slip condition at the particle surface. All variable with the capital are Lagrangian variable and smaller variable are Eulerian quantities. We validated our modeling for a circular particle settling and compare with the Hakan et al. And find that our results are in good agreement. We present results of our work circular and square particle sedimentation at Reynolds number 163. Normalized velocity of both square and circular particle are plotted against the non-dimensional time. Horizontal component velocity of both particles are contrasting. For circular particle, it reaches constant value and settles down, but in case of the square particle, after reaching a certain value around 1.3, it start fluctuating around a mean value. Normal component of velocity of circular particle make constant fluctuation with a steady value, but in case of square particle, it also makes fluctuation but with a larger and smaller amplitude, and same pattern followed by the angular velocity of the both particle. Angular velocity of circular particle has same pattern, normal component but with lesser amplitude, and in square particle it follows same pattern as the normal component velocity of a square particle. In this slide I show trajectory patterns of the both circular and square particle as seen from the figure itself. A square particle has some random type motion, or we can say random fluctuation, and for the circular particle a smooth motion with steady oscillation around the mean value. At Reynolds number around 190, circular particle show 2D characteristics, and beyond the 200 it moves to 3D characteristic. And in case of the square particle at lesser Reynolds number, it leaves the 2D characteristic and moves to 3D motion. Trajectory of circular particle has smooth oscillation. Square particle has random motion because of its angularity of the particle and for sharp corners of the particle. If we see trajectory of the square particle at Reynolds number 29, 70, 29, it has constant value around the mean value, but as with increasing Reynolds number it starts fluctuating, and higher Reynolds number at same circular particle 190, it has random motion and particle doesn't settle at the center of the domain. In this slide we show drag coefficient of the both circular and square particle. In figure, CD and RET relations are shown for square circular particle. At Reynolds number up to we can say around 120, both particles show same trend, but at increasing Reynolds number they are not same. and that difference can be due to the computation of the UT, terminal settling velocity, and angularity of the square particle, which in fact changes the formation of the vortices. Sharp corners of the square particle generates a vortices different than circular particle. That causes the differences in drag coefficient of the both circular and square particle as higher Reynolds number beyond the 120. These are some of the references that we use frequently in our work for comparison, for the validation test, and for DLM. We acknowledge Dr. Amit Bhalla and Dr. Nishant Nagia for their needful suggestion. They are developers of the IBMR tool. Thank you.
Thank you. Can the forum is open for full of questions?
Hello. Yes.
Yeah. These IB methods, they also lead to a lot of fluctuations, and do they really, like, for example, if I have to ask you about like the Beckett force that acts on the wake or the history of the particle motion,
Yes.
did you sort of try to see whether you can verify that with the experiment?
Yeah, with the experiment, yes, we can verify. Actually, large fluctuation, it occurs only when any particle has sharp corners. As we have seen in circular, there is no sharp corner. So up to 200 Reynolds number, we cannot see that much fluctuation. But in square particle, at even lesser Reynolds number, we see fluctuation, and we can validate with the experimental. And I have read some research articles. They have done this experimental level.
Yeah, added mass force would be very different for the two cases, right? For the square versus the silver.
Yes. But at the added mass is they're different, but it is not that much required at this mass because anyway.
Because in I would have understood, but because you're dropping them in liquid, right? You're looking at the sedimentation.
Yeah, in viscous fluid.
Play an important role. What is the Stokes number like that you normally all that kind of range that you explode?
Yeah, Stokes number that we are reaching is around almost 100.
It's large, right? So in that case, yeah, okay. All right, okay. Thank you, Govind.
Oh, thank you.
Yeah. Okay. We'll move to the next talk. Let me look at the title because it's not visible in the slides. This talk is on influence of water pool temperatures on the direct contact condensation. It's a numerical study by Deep Guleria and Pramod Kumar from IT Mandi. So you can start the presentation, please.
Hello everyone, I am Shredeep Guleria, working in School of Engineering at IIT Mandi under Dr. Pramod Kumar, and today here I will be presenting the influence of water pool temperature on direct contact condensation. We are presenting here a numerical study based upon ANSYS Fluent using volume of fluids method. So this is the outline of presentation. Initially we will be discussing about the introduction, then about the numerical methodology we have used, and after that we will be discussing the results and discussions, and in the end we will be giving the conclusions of present analysis, and in the end we will be giving the references for the present study we have used. So introduction. What is the condensation? We know that the change of gaseous phase to the liquid phase is known as the condensation. But what is the direct contact condensation? In direct contact condensation, we bring the steam or any hotter liquid directly in contact with the colder liquid in order to condense it or cool it down. So this is the condensation. So we are condensing the hotter liquid. So in the figure we can see that steam is injected in the water pool through a pipe. So it has various advantages because there is a large heat transfer is possible from steam to water, and it can directly condense as compared to the surface condensation, and it doesn't need much area. So there is not so much pipes are involved. There's directly one tank is there. So there's less chance of corrosion as compared to the other type of condensation phenomena. And since the area is less required, so the cost is less. But we know that as we can see that the two fluids are mixing, so we can't perform this phenomena where mixing is not possible, or it is not advantageous to our use. So one more thing can happen, that whenever we are injecting steam at low flow rate, that water can enter to the pipe chaotically whenever the steam temperature is less and its flow rate is less, flow injection rate is less. Water can enter chaotically within water pipe, and it can cause the water hammer, which can break this pipe. This shock wave due to water hammer can break the pipe. So that is the one of the limitation which we are currently trying to study here. What are the applications? It can be used in the nuclear power plant or other power plants. How? In nuclear power plant, what happens in reactor core, that due to the high temperature, the pressure of the steam within reactor core increases, and we don't want our reactor core to burst down and nuclear radiation to leak outside. So we inject that steam directly to a water well within a reactor core, so that pressure can be immediately reduced within the reactor core and can reach to the safer level. So it is used wherever we want to attain faster pressure reduction and high energy transfer, so that we can attain as a safety within that power plant as early as possible. So what we are doing, that we are using this ANSYS fluid volume of fluids approach. We are taking two phases, steam and water. Both are incompressible. So these are the standard continuity equations, standard momentum equation. In the continuity equation, the primary phase is taken as the vapor, and secondary phase is taken as the water. And this is the energy equation. But we can see that the energy continuity equation, and in the energy equation, we have the source mass transfer term and volumetric heat source term. That is due to whenever there is a condensation happen, the mass from one phase enters to the another phase, and it is incorporated by the heat transfer effect. So source terms are added to this equation, and these source term we have calculated using the UDF. In addition, we have taken turbulence modeling. The standard turbulent K epsilon model we have taken, which is already given in the ANSYS fluent, with standard constant values already given in there. We have used the heat phase change model provided by Welsh and Wilson, where he has given the mass transfer term. This mass source term equals to the heat transfer in liquid plus gaseous phase, that is vapor phase, multiplied by normal to the interface across towards liquid phase, multiplied by interfacial area divided by enthalpy of vaporization. But what we have assumed that earth vapor always remain in a saturated state, so Qg will become 0. So the remaining heat is calculated as compared to as per the liquid heat transfer, that is heat conduction phenomena in liquids, and the interfacial area is calculated as per the gradient of volume vapor fraction, and the normal is calculated to the gradient of vapor fraction divided by magnitude of vapor fraction. Volumetric energy source is equal to the area, mass transfer, that mass source term, that is we have calculated as per the previous expression, multiplied by the enthalpy of vaporization. So we have written a user defined function which is a C code basically, which has different macros. Different mass transfer macro is used to calculate these source terms in continuity and energy equation, and there are other two macros which are used to calculate the cell temperature gradient and to calculate the normal and interfacial area density. So that is what we have incorporated in the ANSYS fluent. So this is the initial and boundary conditions and the geometry in which we are studying the direct contact condensation. What we are doing, that a pipe of d diameter and length which is equal to 3 times of the diameter of pipe. From this pipe we are injecting steam, which is already filled of steam. We are injecting steam to a water pool water pool which is having width 18 times of diameter and length height 9 times of its diameter, and having outlets of 15.9 nm across its ends, as we can see as I am showing as per the pointer. So steam is ejected at 20 meter per second and the temperature is 100 degrees Celsius. This is injected to a water pool, the temperature of which we have varied in the present analysis. And these are the numerical procedures we have used. We have used explicit view of method, and pressure velocity coupling we have used using simple algorithm, and other discretization schemes also we have given. And the convergence criteria, for the quantity we have taken 10⁻⁻3, for other equations we have taken 10⁻⁻6. So grid independency test, what we have done that we have tried to calculate the area entered by the steam within water pool. So for the 0 degree of subcooling, that is the steam when steam temperature and water pool temperature is equal, for that we have tried to calculate the grid independency test. We have changed the element size, that is 1.5 mm, 1 mm and 0.8 mm. We found that for 1 mm and 0.8 mm element size, the area entrainment plot show almost similar characteristics. So we took element size equal to 1 mm. And these are the nodes and elements, number of nodes and elements in the which are used in the present analysis calculation. These are the results. We have calculated the phase diagrams, that is the red phase is the steam and blue one is the water. So for different degree of subcooling, that is the steam temperature minus water temperature. For 60 degrees of subcooling, we observed that steam is not able to entrain within water pool, but there is a higher rate of condensation and water directly enters to the pipe, as we can see here in this pointer, as I'm trying to show in different times, it directly enter to the pipe. For 50 degree of subcooling, we see that there is small entrainment, which is very less visible, but yeah, there is small entrainment, and after that air directly enters, means the rate of condensation immediately increases after small entrainment, and that water enters to the pipe, which is, I have earlier discussed, is the chugging phenomena. Basically, that water enters within a pipe chaotically, that causes a water hammer, it's the chugging phenomena. So we are observing here the chugging phenomena for 60 degree, 50 degree, as well as the 40 degrees Celsius of subcooling. And for different time we have observed. For the 30 degree subcooling, we saw that there is a area entered by the steam initially, but it decreases, and after that it increases. So there is a initial increase, after that decrease, means the condensation increase, means the rate of injection is there greater than the, when there is an increase, rate of injection is greater than compared to rate of condensation. But here rate of condensation increases and injection is there, but condensation is greater than compared to the injection. But after that there is a certain increase observed. Similarly, think about for the 20 degrees of cooling as well as for the 10 degrees of cooling, there is a greater areas entered as compared to the 30 degree Celsius, and it decreases for a while and then again start increasing. For 0 degree, we saw that there is no decrease observed, that there is always an area increase entered. Area entered is there is always an increase is observed. So these are the area plots for different degree of subcooling we have used. That for the lower, that is 60, 15, 14, there is a very less area entrained, and that is raised to power 10⁻⁻4 scale meter square. So that is almost zero, no area is entrained and directly enters to the pipe. So these are the chugging phenomena, 60, 50 and 40. Whereas for the 30, 20 and 10, 30 and 20, we can see that there is a small areas entrained, and after that there's a decrease and again it start increasing. But whereas for the 0 degree Celsius, there is just increase is observed. So what we can see that there is no condensation for the 0 degree of subcooling, basically, as the temperature become equal. So we need to have a moderate temperature degree of subcooling in order to attain effective condensation, that is near about 30 to 20 or 10. Whereas for a lower degree, we can have this chugging phenomena. So we don't want that to happen here. These are the temperature plots. For the 30 degree of subcooling, we can find that chaotic temperatures, fluctuations, sharp fluctuations are observed at different heights below from the base of the tank we are observing in. That there is a more chaotic temperature variations are observed in the different heights. For 30 degree of subcooling, for 20 degree of subcoolings, there is a less chaotic phenomenon as compared to the 30 degrees Celsius. But for 10 degrees Celsius, we can saw that this chaos temperature fluctuation all decreases again. So that this is what we have observed from the temperature plots. So what we can conclude that with increase in subcooling leads to the chances of chugging that we have seen in the plots, and rate of condensation increase with increase in degree of subcooling. So hence what we have observed in the chugging. But for the 20, 30 and 10, 20 and 30 we have observed that there is a efficient without chugging the condensation is happening. For more temperature we have observed that for high degrees of subcooling there are more temperature fluctuations are observed, but for 0 degree of subcooling it is not as effective. So we need to have an effective degree of subcooling we need to have effective degree of subcooling in order to have efficient and safe direct contact condensation phenomena. So this is what we have observed in the present study. These are the references for the present study we have used, and thank you.
Okay, thank you, Sherry. Have a couple of minutes for questions. Okay, Sherry, I have a question. I mean, can you sort of explain to me why you are getting asymmetrical growth that you see in your simulations at lower subcooling?
Sir, at lower subcooling, actually this phenomena was quite chaotic, sir.
Yeah, okay, but then I see a lot of fingers appearing, but at the same time, yeah, there must be some sort of, it becomes chaotic, but there should be a reason behind that, right?
Yeah.
Okay, fine. Maybe you can think about it. Yeah. All right. Okay. Thank you, Sherry.
Thank you, sir.
Yeah. So we'll move to the last talk of this session. It's on a comparative study on industrial multi-phase flow measurement techniques by Prateek Grover, Yuvraj Singh Malhi, and R.N. Ponnalagu. It's not clear who's going to talk, but anyway, we can start the talk now, please. Thanks.
Hi, this is a presentation for the paper Comparative Study on Industrial Multi-Phase Flow Measurement Techniques by Prateek Grover, Yuvraj Singh Mali, and Dr. R.N. Ponnalagu. With increased necessity for multi-phase flow measurement devices in the oil and gas production industry in the past few decades, several research organizations and oil production companies have been researching various technologies for flow measurement that differ in designs and functionalities. These flow meters can be broadly classified into two categories: the conventional single-phase metering solutions that fully separate the constituents of the multi-phase mixture and then use phase-specific measurement techniques, and multi-phase flow measurement technology, which enable the measurement of multi-phase mixtures very close to the point of extraction of oil without the need of separation of each phase. There are a variety of industrial multi-phase flow meters available that utilize numerous different technologies. This paper has been written to assist researchers working in this field to find the optimal flow meter for a particular application, taking into consideration the installation costs and the benefits it would provide. We shall proceed to discuss single-phase and inline multi-phase flow metering solutions first, and then a comparison based on the accuracy of measurement and range of operation is performed. The conventional technique used for multi-phase flow measurement is as shown in the figure. It involves two major steps. First, the separation of flow into its components, and then using single-phase flow measurement to measure each phase separately. Some commonly used single-phase flow meters for this purpose are Venturi meters, turbine meters, and Coriolis flow meters. One of the most famous conventional techniques are Coriolis flow meters. Its working principle relies on the Coriolis effect generated by the fluid flowing through the vibrating tubes. A Coriolis flow meter, as shown in the figure, contains a tube which is energized by fixed vibration. When the fluid passes through this tube, the mass flow momentum will cause a change in the tube vibration and the tube will twist, resulting in a phase shift. If rho, omega, and the meter's cross-sectional area are held constant, then the twist angle is proportional to the mass flow rate of the fluid flowing through the meter. And the given equation helps us in finding the flow rate. Another important flow measuring technology is tomography or cross-correlation velocity measurement, which can be used in challenging mixtures like highly polluted liquids and extremely hot gases and liquids. Tomography-based cross-correlation velocity measurements rely on calculating the transit time of signals passing through the multiphase mixture obtained from ultrasonic or electrostatic sensors. Next, we have differential pressure transmitters that are essentially based on the equation of continuity and Bernoulli's equation. Venturi meters, as shown in the figure, are DPTs, which utilize the fact that reducing the area of flow can increase the velocity and thus substantially reduce the pressure at particular points. In a Venturi meter, the differential pressure obtained is proportional to the kinetic energy of the mixture passing through and the volumetric flow rate Q, as shown in the equation. Conventional test and separator arrangement requires a significant number of valves, piping, and duplicate instrumentation on each separator. Due to redundancy and limitations in the conventional setup, one-for-one arrangement is considered in which each well has its own dedicated separator and measurement system. This setup has significantly less piping and requires less manual intervention. It provides continuous real-time measurement instead of periodic testing and results in a cost-effective and reliable solution. To appreciate the concept of inline multiphase metering, it is necessary to understand the parameters involved in it. A set of 4 equations relates the mixture's permittivity, conductivity, and density to the corresponding parameters of individual phases. Solving any 3 of the equations given here, the fractions of permittivity, conductivity, and density of each phase can be obtained. A number of scientific methods have been applied to solve this set of equations, a few of which we shall discuss ahead. A leading technology used is electrical impedance tomography, which consists of 2 parts, capacitance measurement and conductance measurement, using the setup shown here. Impedance measurement provides the solution to the set of equations for capacitance and conductance, and thus the phase fractions of the components of the mixture are obtained. The permittivity of hydrocarbons is much less than that of water, and thus the measured permittivity can be used to split hydrocarbons and water. Another technique is one which relies on measuring the decay of gamma rays when passed through a fluid. In cases where the gas volume fraction exceeds 0.85, gamma ray attenuation method can be used to solve the system of equations. It is based on principle that gamma radiation's intensity decreases exponentially when it is passed through a matter as expressed in the equation. Knowing the strength of radioactive source and measuring the gamma radiation with a detector on the other side of the media shall give us the density of the media. In magnetic resonance signal decay and imaging, the multiphase mixture is first magnetized and subsequently excited by pulses of radio frequencies. The hydrogen atoms of the different phases respond to these pulses and send back echoes which are recorded by sensors. The amplitude of the echoes and the rate at which they decay is used to calculate the flow rates of oil, gas, and water as shown in the figure. Looking head-on to the flow of liquid, velocities per small slices are observed and magnetic resonance imaging is performed to obtain the amplitude and velocity of the 16 individual slices. Continuous research in the field of multiphase flow measuring technologies have led to the development of hybrid MPFMs. These combine 2 or more flow measurement principles. Based on the technologies utilized, it can be generalized from the table that electrical impedance tomography and gamma density meter methods provide encouraging results and work exceptionally well together. It can be observed that Emerson Rogza 2600M and Krohn oil and gas flow meters have no radioactive sources and have relatively higher uncertainty measurements than other MPFMs. Pietro Florentini's FlowWatch HS and Weatherford's Red Eye MPFM both utilize hybrid models combining a variety of measurement techniques along with radioactive sources. They have robust operating range and low uncertainty in measurements. MPFMs help monitor productivity of oil extraction by calculating the fraction of hydrocarbons being extracted. They also help an organization to predict the lifetime of an extraction project by estimating the oil production by simulating the extracted output through years of production. Conventional meters offer less uncertainty in measurement compared to inline metering flow meters. However, it shall also be noted that the cost of installation of conventional flow meters exceeds that of inline multiphase meters by almost 50%. Even though most oil wells prefer to use inline multiphase metering due to its cost benefits, considering the reservoir accuracy required, it would be better to opt for conventional methods, as is the case with challenging reservoir management in high hydrogen sulfide conditions in Kazakhstan, which require greater levels of accuracy. Thanks for the wonderful opportunity.
Yeah, thank you, Pratik. This was the last talk of this session. Can we have some questions? We have a couple of minutes. Okay, Pratik, just a quick question. When you have these flow meters placed, do you also worry about what kind of environment they are placed in, so that because they would come with a lifetime and all, in terms of some of the meter itself?
Yes, sir, absolutely. So a lot of these multi-phase flow meters have radioactive sources which have a definite lifetime, and most of them will be around for about 15 to 20 years, and they provide simulations for the results that we will obtain from them for about 10 to 15 years.
I see. I see. And the accuracy keeps going down with time? Would you say that?
Yes, sir. As the amount of radioactive material decreases, the effectiveness of the sensors and meters would obviously decrease.
And people who are handling would be okay with it?
Yes, sir. That's why they simulate up to the time period or the lifespan of the measurement time they require, and then they update and reinstall with new technologies.
I see. No, those who are handling this radioactive material.
Yes, that's a concern here, as handling would be a quite challenging task due to the safety issues, and also it needs to be located outside of the residential complexes.
Yeah, that you mentioned, but yeah. Okay. Thank you, Pratik.
Thank you, sir.
Yeah, thank you. With this, we will end the session. I thank you all for attending. Very good evening. Hope you enjoy the rest of the talks as well. Okay. Thank you. Thank you all.
Hello.
Tu es trop grand pour comprendre des choses aussi petites. yeux est trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Hello, my name is Arun Shah, and I'm going to present my conference topic on experimental and numerical investigation of water jet in aircraft. I would like to thank the Mechanics and Fluid Power 2020 for giving me this opportunity to present my thing. Now, the application of a water jet or fuel jet in cross flow has major application in automobiles and gas turbines, particularly in combustion and afterburners. The better atomization of the fuel leads to better combustion since due to the atomization, it has more disintegration and all the molecules get sufficient air for combustion. And it also leads to the use of lean premix and pre-vaporized combustor because it is burning there. So the lean mixture could be used, and that lean mixture will lead to production of less NOx. And the use of this high velocity cross flow is just for to promote the disintegration, and it leads to enhance the atomization. Now, due to the effect of cross flow, the circular cross section of water jet gets deformed into kidney shape just because of the production of counter rotating vortex sphere on the cross section of the liquid column. And with the downstream of this liquid column, the liquid column is getting disintegrated, and the first disintegration is called primary breakup. And after the production of ligaments due to primary breakup, these ligaments get further disintegrated to smaller droplets. This is known as secondary breakup. Now, the fundamental physics behind this whole disintegration of water jet to the effect of cross flow is the parameters that is responsible for whole this process is the jet diameter, the air and jet velocity, the air jet density and surface tension, and jet viscosity. Since they are huge parameters, so these are clubbed into some dimensionless numbers that are liquid to air momentum flux ratio, aerodynamic Weber number, and Reynolds number. So these are the three parameters that on which the whole process is getting blended on. Now, the objective. Now, the experimental test facility has been developed. It's integrated high-speed image shadowgraphy for observing all the interactions. Again, a 3D numerical model has been developed to visualize and to study it numerically. And at last, inside this 3D numerical model, high operating conditions and different operating conditions have been used for existing and compared it with existing correlations. Now, this is a typical experimental setup that has been developed in the lab test facility. Air compressor has been used to provide the cross flow, and this water tank has been used to supply the water. So the direction is perpendicular to each other for both gas and liquid. A nitrogen cylinder is used to pressurize this water tank to form a steady liquid flow, and for air compressors, it is coming from a small diameter pipe. So a diffuser, honeycomb, settling tank, and converging section has been used to make it uniform. The diffuser is used to expand the air. The honeycomb section just decreases the turbulence. The settling tank again provides the space to settle down settle down the air, and the converging section just converges the air flow through the cross section that is required, and it is a test section. Now, shadowgraphy setup has been used to observe all these interaction and record it. A high-speed camera that has the capacity to record at 4,000 fps has been used to study to take temporal recordings. And a LED array and diffuser section has been used for production of a uniform light source. Now, these are the parameters that has been used to for this whole experimental process. The water jet velocity has been increased from 1.3 to 2.2 meter per second, but the air cross flow velocity has not been changed. It has been kept constant. So the Weber number has been kept constant, and Q value, liquid to air momentum flux ratio, has been increased from 142 to 394. The Weber number has been kept constant because of the experimental test facility limitation. Now, this
Hello.
Hello. Good evening, everyone. This session will be chaired by Professor Lakesh Chandra Mondal from IIT Kanpur. Thank you.
Hello.
Yes, sir, we can hear you.
Yeah, so this is Alokesh here. So I think there are total 5 presentations, right?
Yes, sir, 5 presentation.
Yeah, all the presentations are pre-recorded already, right?
Yes, sir. Yes, sir.
Yeah. So each presentation is 15 minutes.
Yes, sir. 12 minutes it's the presentation and 3 minutes is for question answer session.
Okay. Okay. Fine. So the order, I mean, this video will be played by you people, right?
Yes, sir.
Yeah. So that's fine then. I mean, I think it's already time. We can start the first presentation.
Okay.
Yeah.
Hello everyone. My name is Ninad Patil from VJTI, Mumbai. The topic of my presentation is Dynamic Wind Load Analysis on Heliostat. Let me start with the basic introduction to the topic first. Power plants that generate electrical energy by means of concentrated sun irradiation are known as concentrated solar power plants. In figure 1 and figure 2, solar power towers are shown. The concentration of solar irradiation is done by a large number of mirrored collectors called heliostats. This diagram shows main components of heliostats. Note here that facets are nothing but mirrors which are supported by these trusses. Heliostats constitute approximately 50% to the capital cost of the plant. Therefore, it is important to reduce the cost of heliostats to as low as possible. It is essential to provide reliable data for dimensioning the structure and components of heliostat. Objectives of the present work are to compute wind loads and vortex shedding frequency on 10 meter by 10 meter size heliostat and to analyze effects of fluttering plate on load parameters. This is the list of topics covered under following presentation. Let me explain these topics one by one. Let us recall some theoretical concepts here. Vortex-induced vibration is related to internal dynamics of the fluid, that is, the shading of vortices. T vortex is the time period of vortex shading. This T vortex is proportional to the ratio L is to U, where L is characteristic length and U is free stream velocity of fluid. This means that when we increase the velocity, the frequency of shading increases. This is called as the Strouhal law. If the period of forcing is equal to the period of free oscillation of the solid, a resonance is established. Vortex-induced vibrations occur not only in cylinders but on all bluff bodies where there is an oscillating wake as soon as the Reynolds number is high enough. These are dimensionless flow parameters which can be used to determine the forces on geometrically similar structures. Since facets of heliostat are most likely to contribute in wind loading, structure of heliostat can be considered as a simple flat plate placed inclined to airflow. Inclined angle theta and different load parameters acting on heliostat are defined here in this figure. CD is drag coefficient in x direction, CL is lift coefficient in z direction, and Cm is moment coefficient about y-axis. Various experiments are conducted on heliostats in the past. Peterka performed experimental analysis and provided range of minimum to maximum loads and stated the potential impact of fatigue loads. Then Moya conducted ANSYS mechanical analysis on heliostat and provided various mode shapes along with its frequencies. Vasquez and others identified potential critical operating conditions due to vortex shading vibrations. It is observed that fully coupled analysis to evaluate dynamic wind loads and vibrations is needed for accurate design. Solver validation. Two-dimensional simulations are performed on the case of airflow over flat plate. Geometry of fluid domain is as shown here. Wind tunnel experiments over flat plate of length 0.08 meter was performed in the past. Similar test setup conditions are maintained for present numerical simulations. Results of these validation tests are tabulated here. It is observed that the present test results of dimensionless force parameters are within acceptable range of errors when compared to values in the literature. Also, numerical simulations on geometries with different scales shows same results for dimensionless numbers. Therefore, numerical simulations can be performed on scaled down heliostat structure to predict results for actual prototypes. To achieve first objective, that is to analyze dynamic wind load parameters on 10 meter by 10 meter heliostat, we assumed elevation angle as 20 degree and wind flow speed 40 km per hour. Methodology decided to compute load parameters. Step 1. Fluid domain is scaled down, keeping Reynolds number same, and numerical simulations are performed over the scaled down model. At step 2, dimensionless force parameters are computed for this scaled down model. At last, these dimensionless numbers are used to compute force parameters on actual size heliostat. The given heliostat problem is scaled down to 1:4 model. Domain dependency test results in the optimum domain size of 45 times L in x direction and 15 times side L in z direction. For grid generation, the dimensionless first layer thickness y plus is kept equals to 1 and the SST K omega model was selected for turbulence modeling. These are some other fluent setup details used for simulation. Note here that the side of square-shaped heliostat model is assumed as the characteristic length L and the reflecting area, that is L square, is assumed as the reference area for further. Convergence criteria is set at 10 raised to minus 5 for all residuals. Results of transient analysis on 1:4 heliostat model are as shown here. Strual number is estimated from lift coefficient data. Finally, dynamic wind load parameters for actual prototype of heliostats are computed using above dimensionless parameters. Drag is estimated to 4 kN with fluctuation of plus minus 0.3 kN. Lift minus 9.6 kN plus minus 0.9 kN. Note here that this force is in downward direction. Moment about y-axis as 8.3 kN meter plus minus 0.1 kN meter. Vortex shading frequency F equals 2.604 Hz approximately. Second part of current work is to get pattern of change in load parameters with respect to fluttering of plate at various frequencies. Generally, wind flow causes fluttering of heliostat. This fluttering causes changes in pattern of wind flow around it and affects load parameters. In this test, qualitative analysis is performed on 1 meter by 1 meter plate placed in a wind flow at inclination angle of 20 degree. When numerical simulation is performed on rigid plate, it gives vortex shading frequency F equals to 5.3 Hz. Fluttering motion is provided to the plate boundary using user-defined function. Macro used is define CG motion, which provides motion of a particular dynamic zone in ANSYS fluid. Deflection of ends of the plate while fluttering mode is assumed as 1 mm. Various simulations are performed with different fluttering frequencies eta, and effects on drag coefficient value CD is analyzed. Here CD average is the average value of fluctuating CD, while the CD amplitude is nothing but largest fluctuation from average value. It can be observed from these two graphs that when fluttering frequency eta of plate reaches vortex shading frequency F, the time averaged force parameters increases in magnitude and fluctuation about average value is also increases. Conclusion: different RANS turbulence models are tested to determine dynamic wind loadings on heliostat, and SST-K omega turbulence model is selected as the useful model for transient flow analysis. Next, methodology of simulations on scaled down model is tested, and it is found that this methodology can be used to avoid simulations on large size fluid domains. At the next stage, final results are computed for 20-degree inclination, which includes fluctuating values of forces along with vortex shading frequency. This will be helpful in further design process like dynamic structural analysis. The critical condition of resonance can be predicted on the basis of vortex shading frequency data. Simulations on fluctuating plate in a fluid flow provide information regarding its effects on force parameters. Note here that in current work, results are presented only for single orientation of heliostat. Other orientations with various other wind flow conditions can be analyzed in future. Also, these results can be used in early stage of determining loadings, after which actual experimental investigations will be needed to determine load parameters accurately. These are some of the references used during the. Thank you very much for listening.
So let us thank the presenter. I believe the presenter is present. So
Yes, sir.
is
Thank
there
you so
any
much.
question from the audience, please? If there is no question, then I would like to ask some questions. It's a nice presentation. So I just wanted to know if the simulation was 2D, right?
Yes, sir.
Okay. So the thing is that in 2D simulation, that drag coefficient as well as the leap coefficient, don't you expect that CD and CL will be different, compared to 3D simulation, because you have considered that it's a square plate, right? I mean, the
Yes.
simulation square plate. So since it's square plate, so the flow will be highly 3D. I mean, in actual case, but your simulation is 2D, so your frequency or Strahl number, whatever you are calculating, 0.1775, I believe, or near about to that value.
Yes.
Although it is correct to the 0.18 as you have mentioned, but I think that CL/CD may not be the exactly same. Do you have any comment on that?
Yes, sir. Actually, 3D analysis will give more accurate results. I agree to that. But on the basis of the computation power, it was chosen as 2D to just for the computation power was requirement for 3D was high, and it may give the quite quite deviated results, but it will give some idea regarding the range of that vibration frequency.
Okay. Okay. So no, that is one thing. Another point, somewhere you have mentioned your frequency is about 5.6 or so. Can you
Yes.
just go to that? Yeah. So and previously you mentioned that the frequency is less than a hertz. So I do not catch these two things. Could you please again explain this?
Actually, these are two different parts of the current work. One part was performed for 10 meter by 10 meter size plate, which gives 0.6 hertz frequency, and the other part was conducted on 1 meter by 1 meter plate, which gave the frequency around 5.3 hertz.
Okay.
So
Okay.
the other part was related to the effects of fluctuating plate.
Okay. Okay. So that is one thing. And in the case of the flutter, you have given one oscillating frequency on the delta. That's what you are saying,
Yes.
right? When
Yes.
that frequency is matching with the shading frequency, you are saying there is a chance of flutter, and it can increase the all other parameter, for example, CD value, CL value, and so on, right?
Yes. Yes. Actually.
Yeah. So in that simulation, you see, flutter can happen only at some particular beyond a particular velocity, right?
Yes.
So in the simulation, whether this oscillation has been given in that flutter velocity or just less than that fluttering velocity of the plate.
Actually, the oscillation has been given manually to the plate at different at various frequencies, and the objective was to just check how the drag coefficient values or lift coefficient values varies with the different fluttering velocities. So that was the objectives.
So essentially, I mean, your objective is to check that you give a fluttering frequency equal to the shading frequency. What happens to it?
Yes, yes, actually, and also the manually feeded frequency was varies less than the fluttering frequency, vortex shading frequency also, and it was observed that the drag coefficient values were very much less when the manual feeding frequency was less than the vortex shading frequency, and when it reaches equal to the vortex shading frequency, the values get increases very largely.
Okay. Okay. Yeah, it's a nice work actually. So good. I mean, it would have been good if experimental data is also available. So anyway, as you said that in future it may be done. So that's good.
Yes, yes.
So anyway,
Thank
you very much for this presentation. So if there are no other questions, then let us thank the speaker once again, and let us go to the next presentation, that paper number 185. And the title of that presentation is Numerical Analysis of Wave Drag Reduction in Cascade Fins by Altering Leading Edge Shape by Prabhu et al. So let us listen to this. Okay, please start this presentation.
Hello, This is the presentation for FMFP 2020-185 paper, that is the numerical analysis of wave drag reduction in cascade fins by altering leading edge shape. Grid fins are an important mentionable configurations emerging in modern aerodynamic field. They have a high strength to weight ratio compared to the planar fins, and the truss structure ensures lower weight and cost. Grid fins also have a smaller chord which facilitates lower hinge moments and which increases the control effectiveness and the usage of smaller and lighter actuators. Grid fins do not stall in the conventional sense, and their functionality is up to 45 degrees to 60 degrees as compared to the planar fins. However, grid fins in their application in supersonic regime have shown to have high drag and lower aerodynamic efficiency. An improvised grid fin, namely the cascade fins, are developed to reduce drag and do not consist of cross members. The multiplanar cascade fins are parallel to each other and are supported by end plates on each side. As the aerodynamic efficiency in supersonic regime needs to be enhanced, a targeted numerical study has been conducted on wave drag reduction by varying the leading edge of the cascade fins at Mach 2. Fluent was used for CFD simulations, and the ANSYS measure was used for domain meshing as well as the geometry meshing. No major work on cascade fins in the supersonic regime is available in the public domain. Hence, a benchmarking process was conducted for the cascade fin geometry in the subsonic regime, and for the supersonic regime, a supersonic flow over the wedge has been considered. The results from these two benchmarking studies are compared to the established results. For the subsonic study, they are compared to the experimental results, and for the supersonic study, they are come to the results from NASA. The cascade fin geometry is modeled in SpaceClaim, and the fin geometry has been geometrical parameters have been taken from literature for which the experimental results are available. The domain dimensions are considered with respect to the chord of the fin, and it is ensured that the flow doesn't interfere with the geometrical wall as well as the domain walls. The body of influence is also added for higher mesh refinement in that area, which is closer to the geometry. For the subsonic benchmarking, the cascade fins were subjected to 40 meters per second free stream velocity. The overall mesh elements were around 500,000, with skewness less than 0.9, and the Y plus value chosen as 1. The turbulence model used for the simulation was K omega with SST, and a pressure-based coupled solver with second order upwind scheme was used for higher accuracy and faster convergence. The mesh adequately captures near wall flow, as we can see from the velocity contour, where the separation is captured by the mesh. The CL and CD values, when compared to the experiments, show lower error and higher agreement for lower angles of attack. For the supersonic benchmarking, the validation is done with the analytical results available on a wedge at 15 degrees when subjected to a flow of Mach 2.5 at standard sea level conditions. This is done in order to ensure credibility of the results obtained when cascade fins are subjected to similar supersonic flow conditions. A 2D structured grid is employed, and the mesh is adapted based on the pressure gradient to capture shock. A density-based solver was used, and inviscid wall conditions were applied on the wedge, along with second order upwind for flow discretization. As seen from the top right corner mesh Mach contour, the adapted mesh captures the shock with a higher resolution. The Mach number and the non-dimensional pressure are plotted across the wedge, and the CFD results as well as the analytical results are compared and are in well consonance with each other. There is an observable overshoot for the CFD results due to the inviscid model which is employed. The error for both the graphs is below 2%. and the oblique shock wave angle for the analytical and for the CFD results is similar, which is respectively 36 degrees, 36.94 degrees. Wave drag is associated with a structure at supersonic relative velocity, and it varies significantly with the change in structure of the flying object. Hence, the leading edge of the flat plate being the members of the cascade fins, are varied. The shape variation of the leading edge in general consists of blunt, which is the semicircular and ogive, and the sharp. Two analyses of the leading edges were done here, where the elementary analysis consisted of the blunt 45 degrees sharp and semicircular leading edge, and the advanced analysis consisted of the 20 degree sharp, 20 degree ogive, 15 degree sharp and 15 degree ogive leading edges. The coefficient of drag with these different leading edges was obtained in order to arrive at the conclusion of optimum leading edge of cascade fins, which offer the minimum wave drag under supersonic conditions. For the cascade fins in supersonic conditions, the optimum grid based on the grid independence of CD value was taken with a cell count of around 6 million. The mesh was adjusted to the value of y plus to be less than 1. The skewness value was maintained below 0.9 and the mesh was adapted based on pressure gradient to capture the shock wave. The grid fins were subjected to a flow of Mach 2 and the boundary conditions were applied as ideal gas and Sutherland viscosity. A density-based implicit formulation with second-order upwind discretization scheme, the velocity contours of elementary and advanced analysis constituting the respective leading edges is shown here. It is seen from the velocity contours that there is higher velocity in the pressure in the far field as compared to the velocity around the airfoil. This is mainly caused due to the shock wave generated due to the cascade fins. The variation towards the end of the trailing edge is significant when compared to that of the leading edge. This behavior is mainly attributed to the shock-shock interaction. The shock waves are initially formed at the leading edge with a significant drop in velocity, and these shock waves interact with each other and further go on to impinge on the inner surface of the cascade fins. The shock waves reach the inner surface of the cascade fins and the shock wave boundary layer interaction takes place. This interaction of the shock wave and the boundary layer plays a significant contribution in the drag of the cascade fin. As per the initial analysis performed, the blunt leading edge exhibited maximum wave drag. However, 45 degree sharp leading edge displayed a higher wave drag than the semicircular leading edge. Since the study was conducted under the conditions of Mach 2, the angle of deflection of 45 leads to a detached shock wave, hence leading to a higher wave drag. So smaller deflection angles, that is 15 degrees and 20 degrees, were selected for sharp and ogive leading edges with a view to reduce drag. The strength of the shock was analyzed from the reduction in velocity and increase in the pressure across the shock wave. Analyzing from the velocity contour, the strength of the shock waves observed at the leading edge were varying significantly. For the ogive leading edge with deflection angle 20, the strength of the shock was significantly higher than the leading edge with a sharp leading edge with a 15 degree deflection angle. The strength of the shock with respective leading edges is listed here in the descending order. Consequently, strength of the shock is higher. The interaction of the shock wave with the boundary layer leads to a larger separation region. 20 degree ogive leading edge with its higher strength of shock wave leads to a larger separation region, resulting in a greater wave drag. The overall wave drag of sharp leading edge was found to be lesser than the corresponding ogive leading edge. When the pressure components are compared, the 15 degree sharp leading edge has a lesser pressure component than the 15 degree ogive leading edge. However, the viscous components the viscous component of 15 degree ogive is less than the viscous component of its counterpart 15 degree sharp leading edge. The similar behavior can be observed for the 20 degree ogive and the 20 degree sharp leading edges. with its pressure component less for sharp leading edge, and the viscous component greater for the sharp leading edge when compared to the ogive leading edge. When the overall wave drag is compared of all the leading edges, the 15-degree sharp leading edge displays. It is evident from the study that wave drag associated with the cascade when in supersonic regime can be effectively reduced by adopting the suitable leading edge shape. It is also established analytically that the stronger shock wave result in a higher wave drag. Consequently, due to the higher shock wave strength, the interaction between the shock wave and boundary layer results in a larger region of separation, which effectively increases the drag. The lesser wave drag is obtained by employing a sharper leading edge with 15 degrees deflection angle as compared to that of the 20-degree sharper leading edge. The leading edge can be considered as a part of overall design. Thank you.
Hello.
Hello. So I believe presenter is present here, right? May I know the presenter name, please?
Yes, sir. My name is Amok Kulkarni.
Okay. So it's a nice presentation. Now the floor is open for questions. Audience, please, if you have questions, raise your hand, or you can ask the questions directly. Okay, it appears that there are no questions. So, okay, there is a question. Yeah, please go ahead.
Hello, I want to ask if dynamic mesh was used to capture shock.
No, only the mesh was adapted with respect to the pressure gradient. So the analysis was performed. Yeah, steady state analysis was performed.
Okay, fine.
Yeah. Thank you.
I have a question here. So the pressure component, as you have mentioned, that CP. So that CP at what point?
Sir, it is the.
Yeah, please proceed.
Sorry.
Yeah, proceed, please.
Sir, the CP was for zero angle of attack, and it is mainly at the tip at the leading edge.
So that CP comparison for different leading edges you have shown at the leading edge, right?
Yes. Yes.
Okay. So essentially, you'd like to tell that due to the sharp, leading edge, the separating regime at the trailing edge is less. That's the reason that wave drag is becoming less.
So mainly due to the sharp leading edge, the strength is reduced, and as the strength of the shock is reduced, consequently there is lesser interaction. There is lesser interaction at the trailing edge, and the shock wave as well as boundary layer interaction is also reduced. So as initially, if we reduce the strength of the shock wave, the other effects are also mitigated.
Okay, but why
so
that
reduction?
Yeah, I understand that. So, but why viscous drag is or viscous component is increasing?
Sir, there is also the velocity near the members, near the geometry, and the velocity in the far field. There is also a difference in that. So as there is change in the strength of the shock, the velocity near the boundary layer, there is a change in the velocity near the boundary layer, which for the sharp leading edge may that might be the reason for the increase in the viscous component.
Okay. All right. Thank you very much for this good presentation. Now let us go to the next paper, the paper number 190, and the title of this presentation is Experimental Study of Leading Edge Tubercles on Propeller Performance. So I believe the presenter is present here. So please start this presentation.
This is the presentation for FMFP 2020-190 paper, that is the experimental study of leading edge tubercles on propeller performance. Recently, there has been a growing interest in the new type of flow control device, one which can be found in the natural world. Those are the tubercles. The tubercles are the protuberances which can be found on the flipper of the humpback whale. These tubercles or these protuberances are on the leading edge of the flipper of the humpback whale. These were initially noted by the biologists as humpback whales, for their size, are incredibly agile and are capable of underwater acrobatics. On further investigation, they suggested that these tubercles on the flippers are responsible for the whale's agility. And now it is pretty well documented that the application of humpback whale tubercles on wings delay the stall, as these tubercles maintain lift in the post-stall regime, and the wing thus has a higher functionality at higher angles of attack. These long flippers can be compared to a high aspect ratio wing, which generates the forces such as lift, drag, and moment for fast taking overs. The most researched tubercle geometry parameters are the amplitude and the wavelength. The amplitude is selected based on the chord of the wing, and the wavelength is selected based on the span of the wing. We get a sinusoidal shaped leading edge along the span, which continues along the span of the wing. A representative figure is shown on the top left corner, where we can see the flipper platform with different cross sections, as these different cross sections have different chord lengths which extend along the span of the flipper. These different chord lengths are mainly responsible for the sinusoidal pattern along the span of the flipper. Another major geometrical parameter is the maintenance of thickness to chord ratio. As the amplitude varies, the thickness to chord ratio is kept constant. So the chord which is chosen at the trough and the chord which is chosen at the crest are different, keeping the same thickness to chord ratio. There have been many attempts to explain how the tubercles work, and there are the widely accepted theories are that the tubercles act in a manner similar to that of the vortex generators, and the tubercles act in a manner of wing fences, where the flow is compartmentalized along the chord into the troughs of the wing. As the flow strikes the leading edge of the wing, it is separated by the crest of the crest on the leading edge, that is the tubercle, into counter-rotating vortices which flow along the chord. These vortices, by the addition of leading edge, increase the boundary layer momentum, which delay the stall, which has a similar functionality to that as the vortex generators. Here on the bottom right corner, we can see the chord-wise vortices. The propeller chosen was APC 10x4.7 propeller, where the propeller dia is 10 inches and the propeller pitch is 4.7. The propeller blades are made up of an Epler E63 airfoil, which is located at the root and at the center span, and blade tip consists of the Clark Y airfoil. The propeller was modeled in a CAD package, that is CATIA V5, and the thickness to chord ratio was maintained. As to the bottom right corner, The airfoil were scaled according to the chord length, thus maintaining the thickness to chord ratio. According to the literature, the flipper amplitude and wavelength for the propeller were chosen such that the amplitude is 13 to 20% and the wavelength is smaller. Reducing the wavelength may lead to compartmentalization of the flow with respect to mitigating the tip stall. Such a configuration was chosen. So the modified tubercle wavelength was 5.56 mm and the modified tubercle amplitude was 3.63 mm. The propellers were 3D printed using selective laser sintering SLS technique. Firstly, the CAD files were converted to .stl files, which are suitable as an input for 3D printing. This method was chosen to maintain a pretty adequate surface roughness as well as the stiffness of the propeller blades. In this particular case, nylon 12 PA220 was used. Wind tunnel at Defense Institute of Advanced Technology was used for conducting the experiments. However, in the present study, only static thrust. The wind tunnel is an open return type with 8 meters per second, and the motor. From the test, the thrust, current, power, and the coefficient of thrust and coefficient of power are compared for the baseline as well as modified propeller. As it is significantly evident that for lower RPMs, the coefficient of power is less, and the power requirement and the current drawn is less. It can also be noted that the thrust for the same RPM is reduced. At lower RPMs, the power requirement is reduced by approximately 28%, and as the RPM increases, the power requirement reduces to around 7%. For a minimal percentage reduction in coefficient of thrust, we get a higher percentage reduction in coefficient of power. But the uncertainty in the percentage reduction from 2000 RPM to 5000 RPM is to be further investigated.
Okay, that's all for this.
Hello. Yes, sir.
Okay.
Apologies for the poor quality.
So anyway, is there any question? Any question? The floor is open for questions. So if there are no questions, I would like to ask, some queries essentially. So it's a good experimental work, I'll say rather. And yeah, it's interesting that the tubercles, how it performs in the propeller blade. It's a very good investigation. That's what I would like to mention here. This is one thing is not very clear how these tubercles are helping in thrust generation. Is it increasing or decreasing? That is not very clear to me. Can you just come again, please, on that?
Yes, sir. So mainly when tubercles are applied on a wing, there is the literature states that there is decrease in lift, but there is also a decrease in drag up until the stall regime. But after the stall regime, there is maintenance of lift, and there is also like maintenance of drag. There is no overshoot of drag. So if a similar concept can be applied for the propeller blades, so here we can see that there is reduction in thrust, but also there is a reduction in drag, which is why the current drawn is quite less. And mainly there is reduction in thrust because due to the tubercles there might be the boundary layer might be turbulent. So even for the lower angles of attack.
Okay. But essentially, it's not expected to be, because you are adding tubercles, because that is generating your steam-wise vortices, which is essentially energizing the boundary layer. So maybe at very high Reynolds number or very high RPM, that might happen.
Yes,
Okay.
and sir, mainly here, as there is maintenance of the chord to thickness ratio, we can see if we take a cross section across the span, so there is a sort of visible groove. So the air is expected to flow along the grooves, and there is less span-wise flow. So that is the reason. That might be one of the reasons for the maintenance of for the reduction in drag and for the maintenance of the performance.
So yeah, that's good. I mean, I was thinking that you didn't change the wavelength as well as the amplitude, right? For the propeller, you have only one wavelength and amplitude of the tubercles.
Yeah, so during the study, the other propellers, there were some problems with the model, so we tested on the models which were available.
Okay, it would have been good actually if you could, compare your data with another baseline case, although we have compared here, but along with, other wavelength plus, the amplitude of the tubercles. Anyway, I would like to thank, it's a good work. Okay, let's go to the next presentation. That is paper number 222, it is, right? So the title of this presentation, tip vortices over wing surface using oil flow visualization. This is also an experimental studies, it looks like. So let's listen to this. Okay, please play this.
Today, I am going to present on the topic tip vortices over wing surface using oil flow visualization. I am Vasant Kumar from IIT Madras. Co-authors of the paper are Aritwas Roy and Rinkum Mukherjee. We divided our work in two phases. Initial is the experimental phase where we carried out our oil flow visualization, and the numerical phase where we did the analysis of blended winglet design. Now, the primary differences between a 2D airfoil and 3D wing are the tip vortices. Whenever the high pressure air from the lower surface meets the low pressure air from the upper surface along the tips, one could clearly see the contours of the tip vortex being formed. Induced drag again is a phenomenon which is unique to a finite wing. Whenever the span goes to infinity, tip vortices vanish and the induced drag goes to zero. So in this present work, we did experiments on finite wing with cambered as well as a symmetric aerofoil as a cross section. We found the dependence of the vortices formed on angles of attack as well as Reynolds number. Finally, we explored the idea of effectiveness of winglet for a short spanned wing in low Reynolds number regime. What we had as an application in our mind was unmanned aerial vehicle. The experiments were carried out at low speed wind tunnel at IIT Madras Aerospace Lab, and the test section dimensions are 2 meters, 2 meters and 0.5 meter. The operating range of the wind tunnel is 0 to 30 meter per second. This is the actual model of wing. The cross section is either 0012 or 4415. We also had the pressure ports to measure the surface pressure, which the surface pressure measurement was used for validation of oil flow results. We used in our experiments were mixtures of titanium dioxide, oleic acid, and pump oil. We ensured that the mixture was sprayed as uniformly as possible, and we repeated experiments for different angles of attack in pre-stall regime and for two different Reynolds numbers, which corresponds to 10 meters and 20 meter per second. 10 meter per second and 20 meter per second. We were able to time each of the runs so that the oil settles down and mimics the flow pattern. Coming to the validation of our oil flow results, This is the surface pressure measurement for a finite wing with the NACA 4415 as a cross section. This is the region of a laminar suppression bubble, suppression transition and reattachment point. We can clearly see that the suppression bubble starts somewhere at 0.3 chord length, beyond 0.3 chord length, and ends beyond midspan. And this is the oil flow results. Here, this is the region of laminar suppression bubble, and the position of laminar suppression bubble matches well with our surface pressure measurement. With that as a validation of our oil flow results, we went on to measure the cone angle. When we say cone angle, what we mean is this is the furthest line from the tip vortex, from the tip region. This furthest line, we took it as a lateral height, and this is the cone angle. We repeated our experiments for 0, 3, 6, and 9 degree angle of attack, and for two different inflow velocities, 10 meter per second and 20 meter per second, corresponding to 0.085 million and 0.1 million Reynolds number. The sample result for our from our oil flow visualization experiments for NACA 4415 airfoil as a cross section. So here what we see is the region of laminar suppression bubble is visible, as well as the stall that is happening at the root region is also visible here. But what we are interested in is the tip cone angle. With increase in angle of attack, the extent of this lateral height is shifting, and we wanted to quantify these results. We did image processing of the results, and we found the following. So with increase in angles of attack, the tip cone angle is also increasing till the point of stall, beyond which the angle is decreasing. What we mean by this is that with increase in angles of attack, the tip vortex is becoming wider and wider. And as far as Reynolds number is concerned, with increase in Reynolds number and tip vortex, this cone angle is decreasing. And what we can infer is that the spirals, the tip vortices are becoming tighter spirals with the increase in the inflow velocity. And this concludes the initial part of our presentation. And the next part is the numerical analysis. We modeled the wing to the exact dimensions of the physical wing that we used for our experiments with a span of 0.4 meter and a chord of 0.063 meters. We used SST omega turbulence model for the simulation, and half span was simulated to reduce the computational cost. And we ensured that the mesh is fine and wall Y plus values are within the acceptable limits. Comparing the oil flow results with our numerical results, this is the oil flow for NACA 0012 airfoil as a cross section, and we can see that the flow has stalled at 11 degrees. Most of the oil droplets remain intact over the entire span except for the trailing edge, except at the tip where the flow has reached the lower surface and entered the upper surface. So from our numerical analysis, what we see here is that the tip cone angle here also is increasing with increase in angles of attack. Flow has stalled at 11 degrees and 11 degree angle of attack. We confirmed this by plotting CL versus alpha. The graph showing CL versus alpha is from the numerical analysis. Here you can see that at 11 degrees, the value of CL is maximum, beyond which CL dips. So this corresponds well, this matches well with our experimental result where the flow is stalled at 11 degree. With that as a validation of our numerical results, we went on to design the winglets and did the analysis on the blended winglet design. So the computational domain as well as the turbulence model were retained for the case with winglets, and we did analysis on two winglet designs, blended winglet designs, and what we found was the stall angle for the case with and without winglets did not change much, and we did so we carried out our analysis in pre-stall region where aircraft performance or the unmanned aerial vehicle performance matters. So this is the winglet design 1, where the winglets are a bit steeper and makes almost 90 degree with the z-axis, and this is the winglet design 2 with the bit of a shallow angle with the z-axis. We termed this one as a winglet 1 and this as a winglet 2. We'll be following this nomenclature for rest of our presentation. This is the flow field for a winglet design 1, and so final here. In this case, what we see is the tip vortices that was very clearly visible in 6-degree angle of attack without winglets is not so prominent with winglets. Also, the region near the trailing edge is much disturbed, as well as the root region is having some disturbance in the flow field. And coming to the taking a deeper look at the flow field over the wing with the winglet design 1, what we see is the region of circulation is found because this winglet is much more steeper. There is a region of circulation here, and with increase in angle of attack, this region is going into the surface of the wing, and at the region of circulation has come almost to the surface of the wing, and at 11 degrees the flow from outside the winglets, outside the wings, have breached the winglet barrier and has entered to the surface of the wing. So this is the region of a stall. So flow field for the winglet design 2 is shown here. The difference is between the winglet design 1 and winglet design 2, the tip vortices. Because this is not steeper, we could see some tip vortices being formed here, but the characteristics of the wing did not change. We could see the disturbance near the trailing edge as well as the root region. Taking a closer at the flow field, what we see here is that since it's not steeper, the flow did not have the space for a circulation. It is trying to move in, and it's just it's not able to complete the circle. This is a pattern is repeated again here at 3-degree and 6-degree angle of attack, where the flow has the region where it is trying to go in is becoming steeper. So here the sea-like structure is a bit shallower, and here it is sharper. 9 degrees, what we are seeing, 9-degree angle of attack, what we are seeing is a trend which is continuing, and this circulation like structure has come very close to the surface, but the difference is at 11 degrees the flow has stalled clearly in this case. In 11 degrees in the winglet 1 case, we saw some lateral flow from the sides. In this case, there is no lateral flow, but the flow here, there are regions where the flow is completely separated from the wing. Coming to the performance of wings, what we see here is wings with winglets perform well in terms of the lift characteristics. There is a slight edge in the CL value of winglet design 1 over the winglet design 2. On the other hand, because winglets add to the surface area, there is also a drag penalty. This is reflected in our the next two graphs, CL power 3/2 divided by CD, where we see that the maximum value of the CL power 3/2 divided by CD coincides for all three cases. And in terms of LBD ratio, wings without winglets is actually performing better compared to the other two cases. This is due to the drag penalty that we discussed. Experiments from our oil flow visualization shows that the cone angle increases with increase in angle of attack, which means that the tip vortices are becoming wider, and decreases with increase in Reynolds number. The tip vortices become a tighter spiral with increase in the inflow velocity. For the winglet design, what we found is for NACA 001 airfoil, our winglets perform well, give a better lift characteristics. There is a drag penalty with the low Reynolds number aerofoil, as well as with optimized winglet design, we could have improvement in the effectiveness of winglets, and we need to test out more scenarios like the effect of the altitude and other phases in the flight to conclude the effectiveness of the wing blades. These are my references.
Thank you. So if there is any question, please, the floor is open for questions now. Audience, please.
Hello. Yes, sir. I have one doubt.
Yeah, please.
So if I am correct, you have used SST omega for the numerical investigation.
Yeah.
So like you have used y plus value between 1 and 5.
Mostly it is 1. Near the trailing edge, it has become 5 because it is. It was along the edges where the mesh was becoming coarser. So only along the trailing edge, it was becoming 5. Otherwise, it was almost 1 throughout the space, throughout the entire span.
Okay, but I think for SST omega y plus value should be less than 1. Correct me if I am wrong.
Yes, you're right. I mean, I agree that because we were trying. One of the thing is, sorry, I mean, this again has got to do with the COVID. I did not have access to Fluent other version. I had to use academic version. So the maximum number of elements were 5 million. So irrespective of whatever I meshed, the final meshing, I was not able to achieve it. At the trailing edge, it was going beyond 5. So I wanted to report that. That's all. But throughout the wing, it was actually 1. So the result that I have discussed, because it was matching with our experimental result, I was able to publish this with some confidence. Yeah.
Okay, I agree with you because there is some limitation with the student version, so it's fine. Okay, I am fine.
Yeah. Okay, thank you. Since I'm not. Hello. Sorry, I'm not able to hear.
Hello, sir. You should unmute yourself.
Sorry. My microphone was actually muted. So anyway, is there any questions? No. So I have a question. I have just wanted to know in your flow visualization, as you have mentioned that your flow is separating at, laminate separation after that turbulent reattachment. Even after that, we can see that white patches of, that mixture, that oleic acid and pump oil. So that mixture, the white, that white flash from your mixture. So I do not understand what is that.
At 11 degrees, what we are seeing.
Hello? Am I audible?
Can you hear me? Yes, sir. Can you hear me?
Yeah, I can hear you.
Hello. Yeah. Sir, at 11 degrees, what we are seeing is the stall angle. At stall, what is happening is there is a tip vortex is being formed, sir. But other regions of the wing, it is not at all because there is no disturbance, sir. At 12 degrees, we can see a complete stall. That what we saw in our results, like 11 degrees, CL max was being recorded. That's the stall angle. Beyond which complete stall is happening. Beyond which there is no movement of oil at all, sir. So we took 11 degrees as a point where that wing is being stalled.
Okay. So another thing at stall, your one simulation shows, some sort of sources on the wing. At 11 degree, if you see the vectors, the whatever vector plots you have shown in the cross-stream plane, it appears that there are some sources on the wing. I do not know what are those, small sources which is coming at at 11 degree.
Okay, sir. I thought that I did not investigate because I thought it was a stall because post stall I don't know how the flow patterns might look like on the wing surface. We were assuming that that could be the kind of a flow pattern. Again, we have to take a closer look at that, sir. and
Okay.
see.
Okay. Okay. Let us
Next.
thank the speaker and for this nice presentation and nice work. So we have now the next presentation, the paper number 235, 236, and the title of the paper, Design of Mixing Tube to Improve Thermal Characteristics of an Ejector. So let's hear this presentation. Let's start that.
Hello everyone. The title of the conference paper is Design of Mixing Tube to Improve the Thermal Characteristics of an Ejector. And it has been authored by me, Ashu Saraswat, Lakshminder Singh, Professor S.N. Singh from Department of Applied Mechanics, IIT Delhi. This particular slide pertains to the outline of the presentation. First, there is the introduction, then literature review, followed by objective of the present study, then mathematical formulation and methodology, followed by performance parameter, result and discussion, then first, we will be starting with the introduction. What is an ejector? Ejector is a mechanical device that is used to enter in the ambient cold air to mix with the exhaust hot gases. Basically, the ejector is installed at the exit of the gas turbine engine to suppress the infrared signature. An ejector diffuser has mainly two parts: ejector and diffuser. Ejector uses the energy of the primary fluid to enter in the secondary fluid, that is ambient air, to mix up with the hot exhaust gases. Entrament to the secondary fluid appears that happens through along the standard distance and the slots that are present on the diffuser. So basically, this one is the ejector, and the second part is this one is the diffuser. So objective of the present study is to correlate the dimensional parameter different vortex generator with the aim of achieving uniform thermal distribution. So we can list down the objectives behind the current study are as follows. First, to validate the numerical methodology with the data available already, and then to conduct the gradient independent study, then to carry out the baseline study with no taps or any other vortex generator, then to introduce the vortex generator taps at the periphery of the mixing tube. Then we will check the effect of taps count and the orientation on the mixing of the ambient fluid and the exhaust gases. And then we will introduce the streamlined body with the baffles at the center of the mixing. This slide will be giving idea about the mathematical formation and the methodology. Here in the present study, we have used two equation dominance model and the basic laws of fluid mechanics. Here we have used the fundamental equations like continuity equation, momentum conservation equation, energy equation. And the turbulence model is required to overcome the closure. This is the computational domain in the boundary condition. Here the outer cylinder shows the plenum. This one is the nozzle, and this one is the mixing tube. Here's the schematic of how an ejector works. Through this entry nozzle inlet, hot exhaust gas takes the entry into the nozzle. Then from the standard distance, cold ambient air gets entered, and mixing takes place inside the mixing tube. And as a result of mixing, there we obtain the colder gas mixture at the exit of the mixing tube. Here's the geometrical dimensions. We have taken length and diameter of the nozzle as 50 mm, and we have kept all other dimensions as a function of the D nozzle. Here is the list of boundary conditions that we have used during our current study and the solution methods we use for our investigation. Here's the performance parameters on which we have analyzed our study. First one is the mass entrainment ratio. It is the ratio of entrant mass flow rate to the mass flow rate exiting the nozzle. Second one is the thermal mixing. It helps to know the flatness of the temperature profile, and it is defined as the ratio of the local temperature to the nozzle inlet. In the subsequent slide, we will be discussing about the resultant discussion. First, we will start with the validation study. We have used standard K epsilon, realizable K epsilon, SST K omega, and we have compared the results obtained through these three models, WS models, with the experimental results. So finally, we have finalized SST K omega for our subsequent study. Then we conducted gradient independent study. We started from 3.5 lakh and we went up to 47 lakh mesh. So the results obtained from 24 lakh mesh and 47 lakh mesh were coming out to be similar. So we have finalized 24 lakh. So here's a no voltage generator case, baseline case. So here we have not used any kind of vortex generator. So this one is the temperature contour and this one is the velocity contour. So implication that we can draw from the baseline cases, we have obtained the non-uniform temperature all across the mixing tube. Hot and cold air don't get mixed properly as clear from the contour. So we need some kind of vortex generator to mix up the gases properly. So first we will be starting with the cylindrical tabs with the dimension of 7 mm dia and the 10 mm height that are separated at 90 degrees to each other like this. So we have changed the position of the cylindrical tabs from 1D nozzle, then we moved to 0.5D nozzle, 0.25 and at the entrance of the mixing tube. So the temperature obtained after the simulation has been listed down in this particular table, and the air entrainment ratio is shown in this particular table. So what we can see, the air entrainment ratio has been decreased when we compare it with the baseline. So this is the temperature profile. What we can see, the temperature profile has been flattened up. That means there is an improvement in the mixing at the exit of the mixing tube. But when we compare the air entrainment ratio with the no water generator case, it has been decreased significantly. Now we have elongated the cylindrical tabs. We have increased the height from 10 mm to 15 mm, and we have kept at 90 degrees to each other. So the temperature obtained is higher all across the exit plane, and the air entrainment ratio has been found to be decreased when we compare it with the baseline case. Next, we employed the conical tabs along the periphery of the mixing tube. So the results obtained after this study was same as the cylindrical tabs of height 10 mm. So the temperature profile has got flattened up little bit, but the problem is the air entrainment ratio has been decreased when we compare it with the baseline case. So next we have thought upon to install the streamline body with 4 baffles placed at the center of the mixing tube. So when we compare it with the baseline case, so temperature obtained is higher throughout the exit plane, and the air entrainment ratio is also decreased. So air entrainment rate decreased by 5%, that is bit towards the higher side. Then we modified the streamline body. We installed four more baffles at the end of the mix, at the end of this streamline body, and we rotated the plane of these 4 baffles by 45 degree, as it is clear from in this particular figure. So what we can find is like the temperature still is higher all across the exit plane of the mixing tube, and the air entrainment ratio is also decreased when we compare it with the baseline case. Now we have changed the baffle position. We moved the baffles, 4 baffles towards the in the direction of downstream to the flow of exhaust gases. So this one is the temperature contour and this one is the velocity contour. So what we can find is there is a temperature. The temperature has been decreased all across the exit plane of the mixing tube. So it is clear from this particular graph, and the velocity, exit velocity at the center has been decreased. This one is the pressure contour when there is no water generator, and this was the pressure contour when there was streamlined body with a modified position of the baffles. So we can see like there is a increment of the air entrainment ratio also. It is 0.2% when we compare it with the baseline case, and the mixing has been improved a lot, and lower temperature observed all across the radial plane, that is around Celsius. So finally we can conclude our discussion. So basically we have chosen SST omega turbulence model. Then we have used different kinds of vortex generator such as cylindrical taps, conical taps, and streamlined body. Then we have installing the cylindrical taps of 510 mm caused marginally improved mixing of the exhaust and ambient fluid, but the air entrainment rate decreased by 2.2%. There is no effect of location of taps observed when we moved when we varied the position location of these taps from mixing tube inlet. When we varied the height of the taps from 10 mm to 15 mm, there is increased blockage, but thermal mixing and the entrainment decreased significantly. Finally, we have used three configurations. Starting two configuration didn't offer any improvement over baseline case. So these three configuration are basically corresponding to the streamlined body. But the third configuration with some design modification offers enhanced performance. Air entrainment got increased by 0.2%, and the mixing also improves with a center line temperature at 601 Kelvin. So basically we have 15-degree lower temperature observed all across the. So these are the list of the references we have used during this study. Thank you. Thank you.
Okay, thank you very much. So now the floor is open for questions. Any question, please? If there is no question, then let me just ask one doubt rather. So the third configuration means which one you'd like to mean? The conical tab. That's what you are meaning?
Hi Mandal sir, yes, I meant the same. Conical taps, installing conical taps inside the periphery of the mixing tube, right sir?
Yeah. So how come it is? I mean, what are the, in terms of flow topology? Can you say what? I mean, why it is becoming effective rather than other, geometry, for example, other vortex generator? What you have used? Any thought on that? I mean.
Yes, sir. So it hasn't brought any kind of like special improvement into the thermal mixing. It brought the same kind of effect as we got from the first case. That was cylindrical taps of height 10 mm. Okay. So after that, we changed the configuration. We changed the geometry to the streamline body, sir.
Okay. So anyway, you have tested many cases. It's interesting. So that experimental data, have you compared your study with any of the experimental data which is available in the literature?
So we did the validation study from the experimental data only, but that will be our future work. We will be conducting the experimental study. Then we can compare it with that results.
Okay. All right. Thank you very much for this nice presentation. Is there if there is no questions, then let us thank this this speaker as well as all the audience who are present. So I think this is the last presentation from this session, right?
Yes, sir.
Yeah. So thank you very much then. So that's all for this session. All right.
Okay. At the end, we thank Professor Alakesh Chandra Mandal for chairing this session. Thank you all.
Thank you.
Vous allez toucher un enfant.
Tu es trop grand pour comprendre des choses aussi petites.
Vous allez laisser un instant.
Tu es trop grand pour comprendre des choses aussi petites.